In this video, I'm going to give you a comprehensive introduction to blockchain development in 2023. I'm going to personally take you over the shoulder and show you how to become a Web 3.0 developer step by step. I'm going to show you all this as a blockchain developer myself who's worked this technology on a daily basis for a very long time and has helped thousands of people become real-world blockchain developers. I'm going to show you how to build multiple different blockchain applications with real-world use cases like DeFi, NFTs, flash loans, metaverse, gaming, and so much more. And don't worry if you're a total beginner, I'm going to show you everything you need to know from scratch. And so if you're new around here, hey, I'm Gregory, and on this channel, I turn you into a blockchain master. And I spent a ton of time putting together this resource for you. And the only thing that I ask in return is that you smash that like button down below. Go ahead and tap it right now. That really helps these videos out so that more people can learn about blockchain, and subscribe to this channel. And if you like what you saw in this video today and you want to increase your skills and become a pro blockchain master, increase your salary past 100K, I can show you how to do that over at dappuniversity.com/bootcamp. You can sign up with the link down below. All right, so let's get into this comprehensive introduction to blockchain and Web 3.0 development for 2023. So this is a compilation of several different projects that I've put out before on my YouTube channel, but I've got a table of contents down in the description below that's going to help you navigate through all that. Okay, it should also populate the chapter markers on the YouTube video so you can browse around through that, but also reference that table of contents because it's going to help you find the bigger outline of things so you can jump through each project better. And so with that being said, let's jump in and get started. So we're going to create a blockchain-based real estate website inspired by Zillow, okay? So we're gonna call it Millo. And basically this is going to let you, list properties online with the blockchain and let people buy them directly with their blockchain wallet. So you can see we have a luxury penthouse in NYC. Here, we'll click buy, okay? We also have an entire process to go through a real estate transaction, like escrow, like lending, like inspection, all that type of stuff, where we streamline this entire thing with blockchain with non-fungible tokens or NFTs. And so let's take a look at a diagram of how this full stack application is going to work. Okay, so basically a user is going to connect with their wallet like MetaMask. Okay, you can see that on my screen here. And essentially they will talk to this website. All right, we're going to code this website out in, JavaScript with React.js. Okay. And then this website is going to talk directly to the NFT smart contract that we have created for this application, okay? So this is our full stack React app, and it's going to talk to this, okay? So this is the blockchain side of things, and each property is going to be represented by an individual NFT. And when we click the buy button here, it's actually going to put the property in escrow so that it has to be approved, by other parties and funded before it can actually finalize the transaction. And the ownership of the property will change based on the NFT, to the seller. And so let's dive in specifically to how the blockchain side of things works. Okay. So we are fundamentally going to create an NFT to manage our properties. Okay. It's going to be an NFT collection that manages all of the different properties. All right. So we're going to create that non-fungible token with Solidity, the primary programming language for Ethereum and other EVM compatible blockchains. Okay. We're going to develop that with the HARDHAT development framework. Okay. We're going to write tests for it. We're going to deploy it to the blockchain. And we're going to use the ERC 721 standard, which is the standard for non-fungible tokens or NFTs. Okay, so we'll create a fully ERC 721 compatible NFT in this video. But now let me also talk about the pictures for the NFTs. Okay, so whenever you look at the NFTs on here, you see like the image of the property, and you see these other things like the purchase price, the type of residence, bedrooms, bathrooms, all this extra information about it. So this is what's called metadata for the NFT. So all these, attributes are metadata. And then also this picture right here is a form of metadata. And so we don't want to put this information on the blockchain itself, okay? So we're going to use something called IPFS, and that's pretty standard for NFTs. That's called the Interplanetary File System, okay? So basically, IPFS kind of works. This is not the actual IPFS. Hold on. IPFS kind of works like a blockchain. Okay, it's not really. It's basically just a decentralized, file storage system. Okay, so basically, it's just a distributed network of nodes that store files in a censorship-resistant way. Okay, and so that's what we're going to use this for. Basically, put our pictures on IPFS. We're going to put the attributes of the properties on IPFS, and that's going to essentially store a reference to each of those inside of our NFT smart contract. I'll just show you a quick example of that, what it looks like. So here's an example of like some JSON data. This is the metadata for the NFT. You can see the purchase price, type of residence, number of bedrooms, bathrooms, all that type of stuff. This is for the actual IPFS metadata. for this property that we saw right here, okay? And then for the image, you can see a link to it on IPFS with the link right here. And then here's an example of the hosted image, okay, on IPFS as well. All right, now finally, let's look at basically the escrow process and how a sale will work. So again, we're going to have this real estate NFT. All right, let me actually move this font down so you can see a little better. All right, that's the NFT we're going to code first, where essentially we just create a smart contract that governs the property. But we're going to create the second contract that actually facilitates the purchase. This will be an escrow contract, where essentially you have a seller, all right, that will put the property in escrow, and the buyer can put in a down payment. All right, then you have all these other parties involved, like a lender, an inspector, an appraiser, and they, they actually have to go through and sign off on this transaction that it's valid before the ownership of the NFT can actually be transferred, okay? So we'll code all this out, we'll write tests for it, we'll show you how it works, and we'll put it in this full stack application so that all this can be done directly through their website in a decentralized way that can completely streamline this process. All right, so let's go ahead and get started here. So let's start coding. There's only a few dependencies that you need in order to get started on this. You, of course, need a terminal, okay, so that you can execute commands in your terminal. You need a text editor. You can use whatever text editor you'd like. I'm just using Sublime Text because it's my preference. You need a MetaMask wallet installed so that you can make transactions on the blockchain, okay? But in terms of actual developer dependencies, the biggest one you need right now is just Node.js. Okay, so you can go to your terminal, see if you have Node installed, do Node-V. Okay, I'm using version 16.14.0. You can use whatever version you'd like, but if you're just brand new, I highly recommend sticking to my same Node version to reduce the possibility of any problems that you're going to run into. Okay, so if you don't have Node installed, you can install it with the package manager, or you can just go to the Node.js website directly and then download it for your machine. Okay. So let's go ahead and get started with the code. I'm going to put a link to this down in the description below. This is the GitHub repository for the final code solution, okay? I've created a starter branch for this particular project. So we're not creating every single thing from scratch, okay? We're going to start off with a little bit of a template here today so we can get moving quickly. The biggest thing is I want to show you how to do this with real estate NFTs and create this full stack website with React, okay? So go ahead and grab that link down in the description below. All right, copy it. I'm going to go to my terminal, and I'm going to do git clone. All right, and then I'm going to say -b. So that's going to clone a specific branch. So Git has branches. It's just different versions of the code. I can see my branch here called starter code. So git branch -b starter code. All right, and then I'm going to put it in here. All right, and then that's going to clone into this Millo directory. So I say cd Millo. All right, now I'm on this branch starter code, which is exactly where we want to be. So once you're inside of here, we can go to open it up in our terminal. Okay, you can see that it's got some placeholder for some contracts inside of here. So this contracts directory, we've got some front end already configured inside of our project here. Okay, so it's not created, it's just we got some configuration set up so we can get moving quickly. We've got a directory for the test, okay, and we have our package.json, which is what we really want, which are all the dependencies for our project. So let's go ahead and install those. We can go to our terminal and do npm install. All right, that's going to populate our node modules directory here, and then pull down all the dependencies that we need. So what are some of those dependencies that we're going to use specifically for this? Okay, so we're going to use HARDHAT for creating the smart contracts, okay? So you can see that down here in the dev dependencies, all right? So HARDHAT is a smart contract development framework that's going to let us, create smart contracts. It's going to let us write tests for them, put them on a blockchain, and all that type of stuff. So HARDHAT's a really great tool. We're going to use ethers.js, all right, for talking to the smart contracts in JavaScript, okay? So ethers, comes inside of HARDHAT as well. Okay, it's pretty standard. So ethers, I'll put that up here. All right, ethers is our JavaScript library for interacting with Ethereum and interacting with smart contracts. So that's what we're going to use for that. And then finally, we're going to use React.js to build out this client-side website. Okay, and again, React is just a JavaScript framework for creating user interfaces. All right, so now let's get into coding our first smart contract, okay? So what we're going to do is create a smart contract specifically for the real estate NFT, all right? So we can go inside of this realestate.sol file. Okay, so realestate.sol is our first smart contract file. Okay, capital R, capital E. That's the convention for naming Solidity files here. .sol is the file extension. And you can see here we have at the top our Solidity programming language version. We just do pragma Solidity with a caret version 0.8.0. And then we use the contract keyword here. And then we give it any arbitrary name that we want to. In this case, we're going to call it real estate, just like the file name. And so all the code for the smart contract will go inside of here. And of course, to say the obvious, this is the Solidity programming language that you are looking at right here. Okay, so what we're going to do instead of creating a complete NFT from scratch is we're going to use a third-party library to help us create the NFT quickly. So we're going to use the OpenZeppelin library for doing this. So OpenZeppelin is a great project for open source smart contracts. NFTs are basically a solved problem, and just for the sake of getting started quickly, we can essentially use somebody else's audited NFT code to get started quickly. That's exactly what OpenZeppelin is for. So we already have OpenZeppelin inside of our project. We installed it with our NPM packages. So we can just import the OpenZeppelin dependencies into our file like this. So we can import the smart contracts like this, and then we can inherit from them in our smart contracts by saying like contract game item is ERC721 full. We'll do a very similar type of process, okay? So I'm going to import them like this. If you want to grab this from the final code solution, you can. But basically, I'm going to say import OpenZeppelin contracts utils counters, okay? ERC721 and then ERC721 URI storage. So this is going to help us create our NFT. So we'll say real estate is ERC721 URI storage. Okay, that's the same thing as this right here. And that's basically going to let us get all the behavior that we need to create our NFT. So we'll do a little bit of boilerplate setup inside of here. Basically, we're going to say using counters for counters.counter and then counter.counter private token IDs. Basically, this is going to allow us to create an enumerable ERC721 token so we can create them from scratch. So let me make a quick note of that. All right. So basically, whenever we create this NFT, we're going to mint them from scratch. So when we put the NFT in the blockchain, we deploy the smart contract out there. The smart contract out there. There's not going to be any properties whenever we create it. All right, we're actually going to create them manually from scratch, one by one by one, by calling the mint function. Okay, and that's going to create like property 1, property 2, property 3, and we'll do that after we've deployed the contract to the blockchain. That's why we're basically going to make this an enumerable contract where we can, create them. We're going to create a mint function. All right. And we'll also override the total supply to support that. But the first thing we need to do is basically give our contract some settings. All right, so ERC721 tokens, NFTs, take a name and a symbol, okay? And we can configure those settings at the constructor function. Again, this is the function that's run once and only once whenever the contract is created or put on the blockchain. Okay, so we can create our constructor. We can just copy this from the documentation. All right. And you just use the constructor keyword, ERC721 full, okay, game item, this, all right. So I'm going to modify this. So ours is going to be just ERC721, all right, just like this right here. And we're going to call it real estate. And we'll just use real. All right, we don't need this. We don't need the public. And we can just take off the function body because we don't need to execute any code inside of there. All right. And then next, we're going to create the mint function. All right. So this is what's going to let us, actually create tokens from scratch. We'll say function mint public returns UN256. All right. And basically what we're going to do inside of here is let somebody mint with a specific token URI. So this is going to be the actual metadata. All right. And then essentially inside of here, we're just going to create the NFTs from scratch like this. Okay. So we're going to update the token IDs. That's why we use this right here. Basically, the token ID is going to start at 0, and then we're going to increment it. We're going to add 1 each time. And then we'll turn a new item. All right. We'll mint it with the internal minting function from the library here. We'll set the token URI and return the new item ID. And then finally, we'll need to reflect that in the total supply, which is here. We'll override the total supply function to basically see how many NFTs have been currently minted. So I know I went through this part kind of fast, all right, and that's really to be intentional because I want to focus on the actual real estate escrow contract, which we'll focus on next, okay? So, NFTs are kind of a solved problem in this case. I want to focus on the actual purchase behavior, and we'll code that out much more step-by-step with tests, okay? But for now, I just wanted to get an NFT up and running quickly, all right, so that we can just have that NFT to work with. Because again, we're gonna go back to this process where we have our NFT contract here, and then we have this escrow contract that facilitates all of these different purchases. So let's go ahead and get started on that now. All right, so now let's move on to the second smart contract, the escrow contract. And this is where we'll get a little more in depth, a little more step-by-step, and actually the coding of the Solidity. Because this is way more custom, from scratch, okay? So again, what we're going to do here is create this escrow process where, a seller can list a property, a buyer can basically, signify their purchase intent and create a down payment. Lender can get involved, an inspector can get involved, an appraiser can get involved and go through all this process to actually transfer the ownership, okay? So what we're going to do first is create some settings in this smart contract. We're going to create some state variables, okay? So opening up the file here again, what do we have? We have the programming language version at the top. Okay. We have this interface for an ERC721 token. We'll come back to this. Don't worry too much about it right now. We'll explain interfaces when we get there. But right here, we have the actual smart contract itself, the contract keyword escrow. Okay. So this is the contract we're going to create. We're going to put all the Solidity code inside of here. So what we're going to do first and foremost is store some settings. Okay. So we're going to use state variables for this, and we're going to keep track of some different blockchain addresses, okay? So like the lender, we want to know who this is, who the seller is, okay? Who the inspector is, all right? All that type of stuff. So at the top, we're going to say address, okay? Public lender, all right? So what is this? So, basically Solidity is a statically typed programming language, which means you have to declare the address type. You have to declare the variable type whenever you're declaring a variable. And that's why we use address here. That's just the data type of a blockchain address like you'd see in MetaMask. Lender is just the name of the variable we're creating. Again, this is a state variable, so it's going to get saved inside the smart contract on the blockchain. So once we set it, it's going to stay that way on chain. And then public just means that this variable is now visible outside the smart contract, and that Solidity is going to give us a special function for free where we can access this value and we'll be able to see it outside the smart contract. So we can do the same thing for the inspector, all right? All right. And then we can do the same thing for the seller. But we change this to address payable type because the seller is the person who's going to receive cryptocurrency in this transaction. So we must make their address payable here because we're actually going to transfer Ether to them. And then essentially we're going to say address public NFT address because we want to store the smart contract address for the NFT for this particular real estate transaction. Okay. So next what we want to do is actually set all these variable values. So we're going to do that inside of our constructor function. Again, this is the function that's run once and only once whenever the smart contract is deployed to the blockchain. We can create a constructor like this, a constructor. Okay, we say address, NFT address, address payable, seller, all right, address inspector, and then address lender. All right, I'm gonna kill my sidebar over here, and then we'll do some curly braces here. All right, and then open up a new thing. And what we're gonna do is set these function arguments, these variables that are passed in to these values here. So again, these are state variables. All right, and these are function arguments, which are going to be local variables inside this function. So I'm using underscores as a convention just to prefix those so that there's no naming conflict. All right, so how we set this is like we just say NFT address, which is the state variable here. We can access this value and also set it inside of here. So we can say NFT address. Because it's a state variable, it's accessible everywhere inside the smart contract. Whereas this, function argument's only accessible inside this function, so we can read it right here. And we basically are just saying, hey, take this NFT address that we passed in and assign to this NFT address here. And whenever we do that, it's going to save it forever on the blockchain. So same thing for seller, inspector, and lender. We'll just do those like right here. All right. So basically seller, we're going to set to this seller. All right. Inspector to this inspector, and then lender to this lender. And while I'm here, I'm going to format this code, all right, to be a little more readable. Instead of having it being way long ways like this, we're going to break it up in multiple lines. All right, so I'm going to do this. All right, and then I'm going to do that. All right, and so that's going to be our first bit of functionality, is just creating the contract with these specific settings and then actually passing in the NFT address that the escrow contract keeps track of it, okay? So we're going to test all this out. As we built the smart contract, we're going to write tests in JavaScript, okay? That's the great thing about HARDHAT, is it comes with the testing framework already installed. So if you open up this escrow, if you go to test folder, look up escrow.js, we can actually write tests in JavaScript that automatically check all the behavior of our smart contract, okay, without having to check everything by hand, all right? So I've already set up the testing environment here. I've got this expect from Chai, which is an assertion library. You'll see that we've got ethers pulled in. We have a helper here that helps us convert currency to tokens, all right? And then we have this function called describe escrow, and this is really where we're going to put all the tests for the escrow smart contract itself. So inside of here, what we're going to do essentially is we're going to start off with something called describe. Let's just do this. Let's start with a simple test example. We can say it. We can just say returns, NFT address. We'll just say it saves the addresses. All right, so this describe is describing the smart contract, and we can write a test example with this it function, and we can just tell it the behavior that we're looking for. We can say it saves the addresses. All right, and we can just pass in a function here. I'm gonna use the async await pattern inside JavaScript, so we're gonna make asynchronous function calls, so we need to do that. I'm gonna call await on those. So what we're gonna do essentially is we're going to deploy the real estate contract, all right? So we'll do that first. Basically, this is the real estate contract here we created. We can do that with ethers.js, all right? So essentially, ethers lets us just get the real estate contract factory from HARDHAT like this. We can just say ethers get contract factory, all right, real estate. We can say that to a variable like this, a const real estate equals await, all right? And then that's going to basically get this compiled contract inside of HARDHAT, but now we need to actually deploy it to the blockchain like this. We say real estate, equals await, real, let's do this capital, await, real estate dot deploy. All right, and then essentially, we're going to, check. We're gonna just first let's just check the address. So we can say console, or we can let's do it this way: console.log. Let's just say real estate address. All right, let's do a quick smoke check. Make sure that's all set up and working properly. All right, so let's do npx HARDHAT. So this is how we run HARDHAT commands. So we can basically run HARDHAT like this, HARDHAT tests, and then it'll run the tests. But because we installed HARDHAT inside of our package.json file here, we actually want to run it with the HARDHAT version that's saved to our node modules directory, and that's what we're using npx for. So we'll say npx HARDHAT test. HARDHAT test. Okay, awesome. So that's how we run the test. It'll pick up that file automatically, run the test runner, and we can see our contract address was logged to the console here. So that's it's working for now. Okay, so it saves the addresses. Basically, all we've done is deploy the real estate contract and logged the address here. All right. So now what we want to do is essentially mint an NFT first. Okay. So we saw this here where we can call this mint function, and we want to pass in a token URI. All right, so we can actually create an NFT once we've done it for a property that we want to list on our, Millo website here. So we can use this, IPFS URL right here. All right, you can grab this from the final code solution if you want to. I'm just going to copy this and put it in my file here. All right, so I'm going to go to, I'm just going to put it here for safekeeping for 1 second. Take out this console logging statement. But in order to mint it, what I'm going to do is say, mint here. And here we can say, deploy real estate. All right, I'm going to say let transaction equals await real estate mint. All right, I'm going to paste in this URL for the metadata. All right, because that's what we need to do whenever we mint the property. It takes in a token URI, okay? And this is going to be the URI for the metadata that has the image inside of it. It's got all the attributes, okay? So that's how we'll mint it, just like this. All right, we'll do real estate mints. But from HARDHAT perspective, we only want to do the minting from the seller's perspective, okay? So we want to basically call this mint function as the property seller. So how do we do that? Well, HARDHAT will let us essentially act on behalf of specific accounts in this list. So basically, we can get all the accounts saved to our HARDHAT project like this. We can do await ethers get signers. Okay, and that's going to log out all the addresses that come for free inside of HARDHAT. Okay, so basically, whenever we run our HARDHAT tests, we can essentially get an array of signers. So let's just log that. So say const counts. Or just say const signers. All right, I'll say console log signers. And then let's comment out this for a second because we don't want to do it just yet. But let's run the tests again. You'll see what's inside of there. All right, so you can see Ethers returns these 10 different signers. So signers are really just like people, like fake people on the blockchain. Actually, it's 20 signers. And it's like 20 different MetaMask accounts, okay, that HARDHAT gives us for free behind the scenes, and they all have cryptocurrency inside of them, okay? So I can do like console signers.length to prove that it's 20 here. I believe it's 20. Yeah, 20, okay. And so each of them has an address as well, all right? And they'll let you sign transactions, put them on the blockchain. So what we're going to do is we're going to set the buyer and the seller in this case. So we could just say, or const buyer, and we could say, signers 0. All right, this is a 0-based index array. We say const seller. We could say signers 1, all right, because it's returning an array when it's reading out each account one by one, all right, and setting the buyer as the first one, the seller is the second one. Again, 0 index, so 0 is 1, 1 is 2. And so we could do that like that the long way, or we could essentially do parallel assignment inside of JavaScript like this and just do it like this. We just give it an array and say buyer, seller. All right, that's going to assign them inside the array. Okay, that way we don't have to do it one by one. And then we can essentially save these at the top like this. We can do let buyer seller. All right, let's actually do it outside of here because we'll change these and we'll access it out later. All right, and then also we can do the same thing for real estate like this. We can say let real estate. All right. And so the reason I did this is because we want to actually mint the NFT on behalf of the seller. So if I want to do it from the seller's perspective, I can say connect seller, all right? And then that's going to actually do this mint function on their behalf, okay? So transaction equals await real estate connect seller, mint the NFT with this metadata, all right? And then we're going to say await transaction wait. All right. And then we're going to do npx hardhat tests. All right. So it's still working. All right. Nothing to really see yet here. But then now we have put a real estate NFT on the blockchain. We've minted a single property. All right. We have a buyer and a seller that we set up here. Now we actually want to deploy this escrow contract and then save the NFT address. Now that we have it, it's actually put in the blockchain, save the seller, inspector, and lender. So let's create some more accounts here. So buyer, seller, let's do inspector, lender. All right. And then do inspector, lender here. All right. And then let's deploy the escrow contract. So we have the real estate contract. We've minted an NFT. And then now let's do const escrow equals await ethers get contract factory, just like we did here. And then let's do escrow. All right. And then we can do, let's set a variable for escrow here. And let's say escrow equals await escrow dot deploy. And then let's put in the values we need. All right, we need the NFT address, the seller, inspector, and lender. All right, so what we're going to do is just pass those in, and we'll say real estate address for the seller. All right, we'll do like this. We'll say seller address. Okay. So whenever we do this, this is the entire signer. It's not the actual blockchain address itself. You can get the address by doing seller.address. All right. So inspector.address and then lender.address. Okay. So now let's do that. Let's do npx hardhat test. All right. So that's still working. And then finally, let's just make sure that it checks the NFT address. So we can check that like this. We could say, let me just give myself some space. You can see it. Let's do const result equals await escrow dot NFT address. Okay, so basically what we're doing is we're reading this variable value right here, NFT address. Again, it's a blockchain address. It's public, so Solidity gave us a function called NFT address. And we can call that on the smart contract like this. We do await escrow NFT address. We save that to the result. Again, we're using the async await pattern in JavaScript. It's an asynchronous function. So instead of using like some crazy like callback function, we're just awaiting the result. Okay. If we didn't do this, it would return the promise, but you want to get the actual answer. So we wait for the promise to resolve. Okay. And then we can check it. We say expect. All right. We're pulling in expect here from Chai. Okay. Expect result to be equal. All right, real estate dot address. All right, and then we can also check that it returns the seller. It's basically the same thing here. We could say, const escrow seller. We want it to be equal to the seller address. Let's not do const. All right. Let's see here. Let's do let. All right. And then, so that we can check both of those. So I want to do a little bit of refactoring because I don't want to do all this inside of one big test. All right. So let's actually move. Let's reorganize this. So basically how we should do that is this should be its own, like this is one test example right now, like describe escrow. It says it saves the addresses. And what we want to do is actually have a specific test example for this and a specific test example for this. So instead of saying it saves the addresses, we're going to create a test example that says like, let's do it like this. We'll say it. Well, first of all, we're gonna have a special test example that says like it returns NFT address. All right, and we can say async. All right, and then we want to have a special function that basically says it returns the seller. okay, which basically we're just checking all this stuff. We're saying in terms of NFT address, seller, inspector, lender. All right. Seller returns the inspector. All right. And then, it returns lender. All right. And we want to put all these inside of a special describe block. So we say describe escrow. We're going to say describe deployment. All right. And that can be a function like this. All right. So we're going to move all this stuff inside of here. Okay. And in each of these, instead of, we want to do all this stuff to set up these tests. And so we're going to take all of these and then basically put them inside of a before each function. All right, so we'll say this before each. Okay, say async. And what this is going to do is essentially run all this code before each of these test examples run inside this deployment description here. So you can basically take all this stuff. We've got all this stuff set up here. We can just copy all this, all right? Or just cut it all out and then put it inside the before each. Oops. All right. And basically here you go. So we've done all that. And then now we can say describe deployment. And for return the NFT address, basically we can just cut this out. All right, move it inside of there. And say we can say const result here. All right, see what I'm doing? I'm just organizing the code we already wrote into a much better test suite. And then we can say returns the seller. We can cut this and just say const results. Let's go ahead and take that out. All right, let's just run the tests and make sure the exact same tests are passing, but it should be 2 test examples now, all right, instead of the first one. To npx HARDHAT test, see if we got any issues. All right, still working. Now let's go ahead and add the other ones. So I'm just gonna copy this, put it inside of here. So this should be inspector, and then inspector, and then lender. All right, so let's save that. And boom, it passes. All right, so now that we've created the basics of this escrow smart contract, really just the constructor function that, tracks the settings for the smart contract. It also, we've got some basic tests set up. We're going to be, positioned to move more quickly throughout this because now we can write tests to make sure that the code that we're writing in Solidity is actually doing what we expect, okay? So now let's go ahead and work on the first bit of functionality, which is listing a property, all right? So essentially what we can do is create a function here called list. We'll say function list, all right? We'll call this public, all right? And inside of here, what we're gonna do is essentially just take the NFT out of the user's wallet and move it into escrow. And we're going to do things like, set the price for the NFT or the property in this case. We'll put in the escrow amount, which is required, essentially like, a down payment or earnest money, okay, whenever the transaction is going to get completed, all right? So let's start off with the first bit of functionality, which is moving the NFT out of the user's wallet and actually putting it into escrow, because that's the whole point of a real estate transaction with escrow is that the ownership is put in by a neutral party and then everybody else has to sign off and do what they're supposed to in order to, make this happen. Again, if you have seller, basically the seller lists the property, they're going to put it into this escrow contract. And this is not perfectly how a real estate transaction happens in the real world. We're just kind of modeling this so you can see how it works in a simple fashion, okay? Typically the buyer deposits for earnest money, and then you have this appraisal, inspection, all this type of stuff, right? So let's start off with the first thing, which is actually taking the NFT out of the user's wallet. So what we're going to do is use first of all, we need to know the ID of the NFT. So again, we created an NFT right here with this mint function. This is going to be the NFT with the ID of 1, all right? But you could have multiple properties, like property 1, 2, 3, 4, 5, 6, okay, from this collection, and we need to know which NFT it is. So the first argument inside this list function is going to be uint 256, and we'll say NFT ID. All right, that's going to be the property that's getting listed. And the first thing we can do essentially is just transfer the NFT out of the seller's wallet into this escrow contract, and it'll stay there until the sale is complete. So we want to say, so how do we do that? Well, we coded this NFT in a different file here. Okay, so we could import this file into our contract and call the transfer from function, which is the function that is part of the ERC 721 standard that moves NFTs between wallets. Okay, you can see that here. All right. So all ERC 721 tokens, including the one that we have created because it's the Open Zeppelin version, has this transfer from function, okay, which basically says, here's the from address, here's the to address, and the token ID, all right? And because we know the seller's address and we know the smart contract address, we can just move the token out of the seller's wallet into our wallet once they've approved it, and then now we will have the thing in escrow. So we need to talk to our real estate contract, call this transfer from function that was provided with this library, and move the NFT into our escrow contract. So how do we do that? Well, again, we could try to import this, okay, but we're going to use something called an interface. I said I would come back to this earlier, and I am now. So essentially, an interface is sort of like a skeleton for a smart contract that just tells you the types of functions that are on side of it, okay, in Solidity, so that we can talk to those types of smart contracts. So really, we just want to say, hey, we use this I prefix as a convention for interfaces, and we're saying, hey, here's the basic interface for an ERC 721 token. This is not the complete smart contract code, but we're going to tell you there's this smart contract out there that has a transfer from function on it. And so we're going to use this thing called an interface to just communicate with that. We don't need to know anything else about it like any other functions. We just care about this particular function right here. So what we can do is basically say ERC20, all right, and then we can pass in this NFT address, right? And now what this is going to let us do is get a version of this NFT inside of our project where we can call the functions, in this case, the transfer from function. All right, we can actually call the transfer from function on our NFT because we have the address and the interface, all right? And then we can pass in basically the seller's address. So in this case, that's going to be the person calling the functions. That can be message.sender. All right. And then who's it going to go to? It's going to go to this actual smart contract. That's who's going to get the ownership. So we can get the address of the contract that we're coding inside of with address this. Okay. So this is literally the smart contract in this case. It's a global variable inside Solidity. And we just make sure that's an address like this. Okay. And then we're going to pass in the NFT ID, which is going to be what we passed in right here. Okay. So you can see that, again, the NFT ID is this. This is the address from, our address to, and token ID. All right. So now let's write a test for this. Okay. Let's write a test to make sure that this basic functionality of listing works. Okay. So inside of the test, we're going to go down here, and after describe deployment, we're just going to copy this block and then say describe listing. All right. And so I'm going to take out all these test examples. I'm just going to start with this first one here. And what I'm going to do is say it, I'm going to say it updates the ownership. Okay. And so here what we're going to do is we're just going to check that the owner of the NFT is now the smart contract instead of the previous owner. And so how do we do that? We can say expect wait real estate owner of one. That's the first NFT we created. And we can say to be equal and then pass an escrow.address. That's going to be the address of the smart contract for the escrow contract. Okay. So let's just run the test and see if that passes. Okay. So we got a little issue here. We got a compilation issue. So I said ERC20. That's my fault. It's a stupid mistake. I'm thinking of ERC20 tokens. Sorry, everybody. ERC721. All right, run the test again. Okay, so it didn't work. That's okay, and I'll tell you why in a second. But let's just go back and look at this. Okay, so how do we get owner of, first of all? All right. So owner of comes from the ERC721 spec. Okay, again, we're going to get this function for free because we just pulled in a library, but you can see the, owner of address, owner of function. Basically, you can put in the token ID. It will return the Ethereum address or the blockchain address of the wallet that owns it. Okay, so in this case, the ownership hasn't changed. All right, so why is that? Well, you can see, we run our test. The test is correct, but the behavior isn't actually working. Well, that's because you can see inside the contract, we're doing this transfer from function, which moves a token from one wallet to another. But, we haven't done a critical step on the other side of things, which is approving the token. Okay, so transfer from lets you move tokens from one wallet to another. But really, anybody can theoretically call this transfer from function. I mean, that's what we're doing inside of this smart contract here. Okay, so we have to have the owner's consent to move tokens out of their wallet to this smart contract, okay? So how do we do that? Well, the owner of the token itself can call this approve function right here, all right? So the owner must call approve before we can actually call this transfer from function and move the tokens out of their wallet into this contract. So that'll be a required first step. So we can do that in our our before each function here. So essentially what we'll do is we'll have the seller, approve the property. We'll just say approve property. And we'll say transaction equals await real estate .connect seller. And we'll say approve. And we'll say escrow address. And we'll do token ID 1. All right. So await transaction await. All right. And then now we need to actually list the property as well. So we'll say list property. And now we can say transaction equals await escrow connect seller lists. So this is going to have our list function here. We pass in the NFT ID. All right. And we'll say await transaction dot wait. Now it should pass if I didn't make any mistakes. All right. So it updates the ownership. So now after on listing, it updates the ownership. Okay. So owner of 1 is now the escrow address. All right. So awesome. So next thing we want to do is actually, so I'll put a comment inside of here first of all. Put a comment and basically just say transfer the NFT from seller to this contract. Now we want to do is update the listing status. So basically we want to store a special place inside of our smart contract to say like, hey, this particular NFT, is it actually listed? So what we can do is create something called a mapping inside Solidity. So this is like stores key value pairs. So we can say mapping. All right, we can give it a key value of uint 256, and then bool, which is a true or false value. Say public is listed. So I'll dig into mappings a little more. So the key, it's just a data structure that gives a key and a value. So a uint is an unsigned integer. So basically it's a number greater than 0, all right, with no decimal places, all right? So sign means like a minus sign, right? So it can't be negative. So basically, yeah, that's what a unsigned integer is of 256 bits. And then a Boolean is just a true or false value. So basically, this will be like the NFT ID, like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and this will just be like true or false. And that will basically tell us, is the property listed? Again, this will be public. All right, so we'll have a function for free called isListed that we can check for outside the smart contract. But we can update this mapping right here. It's kind of like a little database. We'll just say, is listed. All right, and then we say NFT ID. and then we just say true. All right, so that's how we assign values to a mapping. We give it the mapping name, we give these brackets, all right, pass in the key, which is the NFT ID. In this case, it's just 1, and then we assign that to true. All right, now we can check for that inside the test. We can say, you know, it updates it as listed. All right, so instead of updates ownership, above that, we can just say, you know, updates as listed. Okay, so basically we can just do this. All right, and basically just say const result equals await escrow is listed 1, and then expect result to be equal to true. All right, so it updates it as listed. Okay, next we're going to store some other values on the smart contract. Basically, we're going to store the purchase price, the escrow amount, and the buyer ID. And we're going to store those inside of a mapping, just like we did here, because we want to do this on a per NFT basis. Okay, so essentially, we're going to create some more mappings like this. We're going to say purchase price, escrow amount, and buyer. So purchase price can be the amount of cryptocurrency and ether that it cost to buy the house. So the UN256 is the ID of the NFT. The price is going to be the price of the home. You know, the ID of the NFT and the escrow amount and the ID of the NFT and then the address of the buyer. Okay. And so now, what we're going to do is put all this here. We're going to basically say purchase price, NFT ID equals purchase price. Okay, we're going to pass that in here. That'll be UN256. Okay, we're also going to pass in a buyer. All right, and then also an escrow amount. Okay, and we're going to break this up in multiple lines here. Okay, so we're going to do this. All right. And then we're going to save those inside of here. Save the purchase price like that. We're going to add the escrow amount like this. And then we're going to save the buyer like this. Okay. And now we can check for those inside of here. All right. So we can check that it returns the buyer like this. All right, returns the buyer like this. Okay. Returns the purchase price like this. And finally, it returns the escrow amount like this. All right, so what we're going to do here, I'll just pause the video and in a still frame if you want to make sure that that's all correct inside your code editor. All right, let's just run the test first, make sure they pass before you start doing that. Okay, all right, so we got a little issue. Let's just save this really quickly. All right, so I forgot to pass in the new arguments here. So whenever we list the property, we want to add some more stuff here at the top. Okay, so basically, whatever we call lists, we want to add also the buyer address. Okay, and then the tokens. All right, 10, and then tokens.5. Okay. So tokens, what that does is it takes the, we're going to say basically it costs 10 ether. Okay. To list the property, and we have this tokens helper here, all right, which basically takes the value and converts it to ether for the smart contract, and same thing for the for the escrow amount. All right. So now I'm going to run the test again, make sure it passes. All right, they passed. So now if you want to pause the video, make sure that this all looks correct, then you can do that now. Okay, so one final thing I want to do on the escrow list function essentially is make sure that only the property owner can do this, okay? Because you don't really want some random person to list the property, okay? So inside of here, what we're going to do is basically create a modifier, okay? Basically what we can do is put this inside of here at the top. We can create this called modifier here. And we can apply this to our function and say modifier only seller and require the message.sender is equal to seller. So only seller can call this method. And then we can add this modifier to it like this. Say only seller. And we also make this function payable so that they can send in, Ether with this function if they would desire. Okay, awesome. So now let's rerun the test, make sure it still passes. If you want to write a specific test to check for this, that only the owner can call this function, only seller, you could do that. I'm not going to do it for now, just for the sake of time. But now we have our basic listing functionality finished. All right, so now that we've listed the property right here, we need to go through the rest of the process in the life cycle, like buyer deposits earnest money. We update like an appraisal, inspection, okay, appraisal, inspection, lender approval, like lender adding funds to the contract, okay, transferring the ownership and the seller getting paid. That's the whole life cycle here, or at least we're modeling that way, okay. So next what I'm going to do essentially is create a function to deposit earnest money into the smart contract, and that's going to be from the buyer's perspective, okay. So basically what we're going to do is have a way to deposit that, okay. So basically inside of after listing, we're going to minimize this, actually go to the contract first. And we'll create a function inside of here. It's just called deposit earnest. Okay. So what we're going to do, I'm just going to go ahead and add it like this. Okay. So basically we say put under contract. Basically only a buyer can do this. We get a payable escrow function. So we have this function called deposit earnest. We'll give it one argument to UNT56 of the NFT ID that's going for sale. Public payable, so they can send in Ether with the transaction, and we'll make sure the only buyer can do this. Okay, so we need to add in a modifier for only buyer with the NFT ID. All right. So basically, we can go here at the top of our only seller, and then create our this and say only buyer. All right, and pass in an NFT ID. Say message.sender needs to be the same as the buyer of the NFT. Okay, so again, we store the buyers. We can read out this buyer mapping right here, and then the NFT ID, and make sure it's the same as message sender, who's the person calling the function. All right. So public payable only buyer, and then require message value is greater than or equal to the NFT ID, the escrow amount. All right. So basically, essentially, the escrow amount is the amount that you have to put in for escrow for the buyer to, get skin in the game for the transaction. Sort of like a down payment in this case, sort of like earnest money. We're kind of blending those two concepts together. So if you're familiar with real estate, this isn't going to be like an airtight strategy here. We're just kind of modeling how you could do this with blockchain. So anyways, they're going to put some, down payment, earnest money, whatever you want to call it. I know there's different things, like I was saying before, but we're just kind of lumping those together as the same concept, even though they are different in the real world for the sake of this tutorial. So anyways, message.value is the amount of Ether that gets sent in with the transaction, and we just want to make sure that's greater than or equal to the required escrow amount to put the property under contract. Okay. So, Well, let's just see here. That's what we're going to do here. We got everything that's required. So basically what they're going to do is send Ether just directly to the contract whenever that happens. And we want to make sure that it's the correct amount, and that Ether amount is going to get stored in the contract during this process. So basically, the buyer does that. They're going to send their down payment directly to the escrow contract, and the real estate NFT is owned by this. Now the buyer's funds for the escrow amount is owned by the contract as well. And then what's going to happen is the lender will be able to add their funds to this contract later, and whenever the property is actually sold, the sale proceeds will go to the seller, and the NFT will go to the buyer, and this real estate contract, escrow contract, facilitates that entire transaction. So now we deposited earnest money. Let's go actually do that in the tests. Okay, so we can write, instead of describe listing, we can say describe deposits. Okay, and then inside of here, we can say it updates contract balance. Okay, and then we say async. Okay, and then what we're going to do is we're going to say const transaction equals await escrow connect buyer. Okay, deposit earnest value 1. And then we'll say the metadata, the value is tokens 5. That's the actual escrow amount. We'll say await transaction wait. All right. And then we'll also say we're going to wait for it and check the balance. Say const result equals escrow get balance. And then that's going to actually get the balance of the Ether balance of the contract. And at this point, that should now be equal to 5 Ether, okay, that we deposited here. So save that, run the tests. Okay, so escrow get balance is not a function. Let's actually implement that. So on the contract at the bottom, what we're going to do is create a special function that helps us get the current Ether balance really quickly. So we can write it in our tests. So basically, we're going to do a couple things. We're going to do this. We're going to do get balance, all right, which essentially is just going to be a function, okay? And it's going to be public view. It's going to return uint256. And what it's going to do is just return address this balance. So this address, this is the address of the current smart contract, and dot balance will just give you the Ether balance, and we can call this get balance function to just quickly return this. While we're here, let's also implement this receive function. Okay, so this is what's going to let the smart contract actually receive Ether. So like with the lender, for example, could send funds to the smart contract and increase the balance. You need this in order to accept Ether to the contract. Okay, so we'll go ahead and do those same two things while we're here. Let's rerun the test, make sure it still passes. And boom, there you go. Awesome. All right, so now we've got the ability for the buyer to deposit the earnest money or the down payment, depending on how you want to think about that. Okay. So now we want to talk about the actual, inspection, right? The appraisal type process. Okay. So what we're going to do is basically model the inspection. Okay. Property inspector wants to sign off that the property is okay and passes inspection before this can happen. So what we're going to do is essentially create a mapping for the inspection status, okay, at the top. So we have, just below the buyer, we're going to create a mapping called inspection passed. So that's going to have a key value pair. Essentially, like the uint256 is going to be the property ID, and then Boolean by is going to be true or false when the inspection is passed. By default, it's going to be false because that's what mappings default to. So we can create a function to update it though, okay? And then we can basically do that like this. Basically, we'll just say, actually, let's do it up here. Update inspection status, that'd be a function. Okay, we'll give it NFT ID and then a Boolean true or false on whether it's passed. Be a public, only the inspector can call this, and basically we'll take that inspection pass mapping, pass in the NFT ID here, and we'll just pass in the value whether it's passed or not. Now, we only want the inspector to call this function, so we need to make an only inspector modifier. Okay, so at the very top, we'll basically just say below only seller, we'll say only inspector. Okay, message.sender is going to equal to the inspector address, which we saved here. Only inspector can call this function, and we apply that to the function right here. Okay. All right, so now let's write a test for that. We'll go here. All right, and after deposits, we'll copy that and look for inspection. So we'll say deposits. All right, we'll say inspection. And basically, instead of this, we'll do this. Const transaction equals await escrow connect inspector. Update inspection status 1 is true. All right, we'll wait for that transaction to finish. Do await transaction wait. And then we'll just say const results equals escrow inspection passed 1. And we expect that value to equal true. All right, so let's save that. Let's go to our terminal, run the tests. Okay, so we got a little issue here. Unexpected end of input in the thing. So it's because we chopped this off. All right, save that. All right, there you go, it passes. So we can do deposits and it updates the contract balance for the inspection. So I think I need to change this, updates inspection status. Save that. Yeah, awesome. There we go. Okay, so now I want to do one final thing before we actually facilitate selling the property. Okay. We want to have basically an approval process. So like, you know, if we want an inspector to sign off on the sale, an appraiser, a lender to just basically say, yeah, we approve the sale. We want to have a special function for that. So essentially what we're going to do is create a mapping called approval. All right, but it's going to be a nested mapping. So you can add it here. So we'll say mapping, the key of the NFT. All right, and then we'll say the approval. So you can put a mapping inside of a mapping. And so this is going to be the mapping of the address of the person who approved it and whether that's true or false. So we just on a per NFT basis. So we pass in the ID of the NFT. That returns a mapping, okay, of the address that, you know, of the person who's approving and then whether it's true or false. All right, so we can create a function to update that mapping like this. We'll just say approve sale. All right, so we'll say approve sale, passing the NFT ID and message.sender will be the person who calls this. And then we'll just set it to true. And we can require this approval whenever we do the sale, which we'll see here in a second, but I want to go ahead and just test this out. All right, so then we'll go to describe inspection. We'll say describe approval. I'll say updates approval status. And then for this, we'll take this out. And then we'll replace this with this. Oops. Basically, we'll say let transaction equals await escrow connect buyer approve sale. And we can do the same thing for the seller. All right, basically, we can just do this. Do it 3 times. And then we'll say for the seller, and then also the lender, and we can check all those, okay? So we can just say expect, you know, await escrow approval 1 for the buyer address to be equal to true, that the buyer's actually done it. Same thing for the seller, and then same thing for the lender. All right, so let's save that, go back to our terminal, run the test. Okay, so I've done let multiple times here, so that's not going to work. All right, so approval, that updates the value there. Okay, so now we've done pretty much all that we need to do. With one final exception, we need to actually facilitate the sale of the property. So basically, we've added the ability to list the property. We had the ability to deposit earnest money, to do an inspection. We had the ability for approval for the lender to approve it. Now we need to go for, you know, basically like the lender sending the funds over and transferring the ownership so that the NFT goes to the buyer and the funds go to the seller. Okay. So we're going to do all that inside the contract with one final function like this. All right, basically we're going to go inside of here and then create a function called finalize sale. All right, this will be uint256, NFT ID, public. Okay, and so what do we want this function to do? Well, we want it to require the inspection status. Okay, you could add more items here like appraisal, etc., etc. Require the sale to be authorized. Okay, require the funds to be the correct amount. Transfer the NFT to the buyer and transfer funds to the seller. Okay, so we can require the inspection status like this. Basically, we can just say, require inspection passed NFT ID. Again, we're, doing that here. Right, and then only the inspector can call this. Okay, we want to require that approval from multiple parties. Basically, we want to require that the buyer has approved this transaction. So we can require approval, NFT ID, and the buyer, okay, of the NFT ID. We want to require the approval of the seller. So we can say require approval, NFT ID, seller address, and then approval of the lender. So we can say require approval, NFT, lender. And then finally, we want to make sure that this contract is fully funded. So basically, we can do that like this. We can get the address, this, dot balance, all right, is greater than or equal to the purchase price, all right, of the NFT. All right. So that's basically going to make sure that all the funds have been sent to this contract, and we can require that. All right. And then that's going to check that all this stuff has happened before we'll actually, do the transaction. So we're going to do more stuff inside of there, but let's actually make sure all this stuff happens before we do things like, transfer the NFT to the buyer and transfer the funds to the seller. Okay. So inside the escrow.js, let's do that. All right, we'll take a little more time on this one. Be very detailed. Say describe sale. Okay. And then we'll say async. And then inside of here, we can use it before each function, and we're going to go through all these steps. Okay. So the first thing we're going to do is go through this deposit earnest feature first. Okay, so we'll say let transaction equals await escrow connect buyer deposit earnest. Okay, we'll say value 5 tokens. All right. So sorry, let's see here. That's going to make sure that we got the earnest deposit. That'll help us satisfy the condition of the balance. Okay. The next, we're going to update the inspection status. All right. So like transaction await escrow connect inspector. Update inspection status 1 is true. All right, we're going to approve the sale from the buyer like this. All right, we're going to say escrow connect buyer approve sale 1. All right, then do await transaction wait. All right, that's going to satisfy this. We'll do it from the seller and then the lender. Okay, and then we'll say let's just do here. We'll do connect seller, approve sale. All right, and we'll also do same thing for the lender. Lender, approve sale. All right, so that's going to check off all these boxes. All right, now finally, what we want to do is, essentially send, more money to this smart contract from the lender, all right, to fund the deal. Okay, and then essentially what we're going to do is, we're going to send the transaction from the lender like this. We'll do await lender send transaction. We'll say to the escrow address. The value is 5 tokens. So now we have deposited 5, and then we'll add 5 here for the entire purchase price. And then finally, we'll finalize the sale like this. Say transaction equals await escrow connect seller finalize sale, and we'll pass in the NFT ID 1 and wait for that to finish. And now we'll check to see what happens. Okay, so we'll just say, it, just works. Okay, we'll change this in a second. But let's just run this, make sure the before function actually works properly and that we're satisfying those conditions. Okay, let's save that, go to our terminal, npx hardhat test. All right, so it works, so quote unquote. So really what we're doing is just putting these require statements, make sure that the property is going through all the proper conditions, that it's got all the inspections, it's got all the approval, and then we mimic those inside of this process here. Now we just say it works. What now we want to do is actually check for other behavior. So what we want to do is say that, on our diagram here, that it actually, transfers the ownership of the NFT to the buyer, and it gives the funds to the seller. So how can we do that? Well, inside of our real estate contract, we'll essentially go inside of here, and we'll say, we'll basically send the ether to the seller. So we'll say payable seller, and we'll say call. So call is a function that we can use to send any message we want to that address, but we'll use to send ether in this case. We'll say value address this is how much balance, and then we'll do it like this. Okay, and then we'll say bool success. All right, this is kind of a long-winded way of just transferring ether from the smart contract to the seller. Okay, but it will return a success value, which we want to check. We'll say require success. All right, so that's going to send ether to the seller. Okay, so we can check for that. Basically, we can just say check. We can just basically check that the escrow balance is now 0. So say updates the balance, expect escrow balance to be equal to 0. All right. And then now what we want to do is actually transfer the NFT ownership to the buyer. So we'll do that like this. We did that with IERC20 transfer from. So we can literally just copy this same line here. Okay. And then paste it down here, but let's kind of change the operation. So instead of doing it from here, the NFT is going to own it. All right, I'll take off this comment. Or the escrow is going to own it. So we'll just say address this, transfer from address this. We don't require any approval because the contract already owns it. And then we're sending it to the buyer. All right. And then let's go ahead and update that in the tests to essentially check that. Say it updates the ownership. All right. Let's say it's basically expect real estate owner of 1 now to be the buyer address, because after the sale, it transfers the NFT ownership to the buyer. All right, so that works. Awesome. So that should be pretty much it for the behavior in the test that we want to check for. There's a couple of things I want to do in the contract before we wrap up here. Basically, we want to now say that the NFT is no longer listed. All right, so right here, we'll just say is listed, NFT ID is false. Okay, but then the finalizing should take place. We also want to go ahead and add some basic behavior for canceling the transaction. Okay, so I'm not going to really code this out in depth and not run a bunch of tests against it. You can do that for an exercise if you want to, but you want to handle cases where a sale gets canceled. Okay, so basically, like if inspection status is not approved, you could refund the transaction or sell it, send it to the seller. Basically the stuff like that, right? And you could add your own custom logic to this. And if you want to do that in tests, you definitely can. But I'm just going to add these here so to get you some ideas going for you. And I'm going to move this code to the bottom here. Okay, just so we're a little more organized. All right, now I'm gonna run the test again, make sure everything still passes. All right, and there we go. All right, so now that we have successfully completed the smart contracts and written tests for them, now what we want to do is actually put the smart contracts on a local blockchain. So what's cool is HARDHAT gives us a way to run a blockchain on our computer without having to talk to the internet, okay? So basically, we can just say npx HARDHAT node. All right, what that's going to do is start a local HARDHAT blockchain on our account. our computer. That's going to give us these, 20 accounts with 10,000 fake Ether inside of them. So when we were running our tests before, essentially that's what HARDHAT was doing behind the scenes every time we started our tests. But we didn't have to have this blockchain running, which is pretty nice. But now that we're actually going to put the smart contracts on this local blockchain so we can start building out our website, we actually want to have a blockchain running, and that's exactly what this npx HARDHAT node command does. So now what we want to do is create a special script that takes these smart contracts that we created and takes them off of our computer and then puts them on our local blockchain. So we can do that with scripts inside of HARDHAT. If you go to this HARDHAT, so this file browser over here, you can look at this scripts directory. You can see deploy.js inside of here. So this is a boilerplate script that you can run inside of HARDHAT, and we can put all the code for it inside this main function. And this is where we're actually going to take the contracts off our computer and deploy them to the blockchain. So let's go ahead and do that right now. Inside of here, what we're going to do is we're going to do something kind of similar from our test. Remember inside of our tests, we did this, get signers from ethers, buyer, seller, lender, inspector. We're basically going to do that again inside of here. So we're going to paste that in here, set up accounts. All right. So buyer, seller, inspector, lender, do ethers, get signers. Again, we have access to ethers inside of here because we're using HARDHAT. All right, and now what we want to do is basically get the real estate contract factory like we did inside the test. So const real estate equals wait ethers get contract factory real estate. All right, that's literally what we did here. All right, basically we can just even copy the same thing and then paste it. But we'll say const real estate, lowercase real estate. All right, and then now we want to get, wait for it to actually deploy for real. So we'll say await real estate dot deployed. And now what we want to do is actually mint some NFTs. So, I've got the metadata for those here. Inside the metadata directory, you can see one.json. These are already uploaded to IPFS for you. So you don't have to upload this on IPFS. Again, you can just copy these links. You can see them right here, right? You can see this. All right, I've got this link posted in here. And you can see that it's, for one.json, you can change this to two.json, which would be the ID of the NFT here. Change it to .3. Okay, so I've already uploaded these for you. And so I don't want to reinvent the wheel for you, make this a little bit easier, but these are already on IPFS. So we can just add them to our real NFTs whenever we deploy them, okay? So we're going to go ahead and log this to the console. We'll say, deployed real estate here. All right. And then now we're going to say we're going to mint 3 properties. So we're going to do this inside of a for loop. Okay. So for loop in JavaScript just lets you loop through a set of numbers and do something in that number of times. So we're going to say transaction equals await real estate connect seller, which we pulled out here, and then mint. And what we're going to do is paste in the IPFS URL, all right? But then we're going to basically take the I value, which is the current number that we're iterating over into this for loop. We're going to add 1 to it, and that's going to be the NFT ID. So basically, if we do that for 3, so JSON 1, 2, 3, ID 1, 2, 3, you can grab this IPFS URL if you want to from the final code solution. But basically, you can, go to IPFS. .io and then put this into your browser and then do one.json and it'll pull up the metadata. You can see if you put in your browser and do 2.json, it'll give you the metadata for NFT number 2. Same thing for NFT number 3 because we've already uploaded them for you. Okay. So we'll mint 3 NFTs. All right. And then we're going to just deploy the escrow contract like this. Okay. So we'll say const escrow equals await ethers get contract factory, capital E escrow. Then we'll say const lowercase escrow equals await escrow.deploy. Okay, real estate.address, seller.address, inspector.address, lender.address, and then get the deployed contract. Okay, and then we're going to approve the properties from the seller. So just like we did the for loop here, we're going to add a for loop here that basically just says let transaction equals await real estate connect seller, approve escrow address, and then the value of each property. So 1, 2, 3. All right. And then finally, we're going to list the properties like this. We're going to say transaction equals await escrow connect seller list property 1, buyer address tokens 20, tokens 10. And then we'll do that for 2 more like this. We'll just say seller list 2, buyer address tokens 15, tokens 5, list 3, buyer address tokens 10, tokens 5 for these different amounts. And then finally, we'll just say it's finished. Okay. So I know we went that kind of quickly, but if you want to study this script even more, you can check out the final code solution and look over that a little more slowly. I just want to go ahead and move on to the front end part, but this is required to get the contracts off of our computer onto our blockchain. And it's basically the same thing we did right here, okay, with a little bit of extra steps. Okay, so let's save that. Let's go ahead and give it a whirl. Let's go to our terminal here and then make sure our blockchain's running. And then a new tab, we're going to say npx hardhat run scripts / deploy.js. We're going to say -- network localhost. All right. So I think I misspelled hardhat. I do that all the time. Hardhat. Try that again. All right, so tokens is not defined. Let's just do that. We need a tokens function here. So let's copy that from our project. We need to add it here. All right, time. All right, awesome. So it worked. So I'm gonna reset this again. I'm gonna restart my hardhat node just to make sure I didn't do anything when I messed the script up. So I'm gonna clear all this out, run it one more time. So npx hardhat run scripts deploy.js -- network localhost. All right, now it's minting 3 properties is finished. You can see all the transactions here. Here is the contract. Okay, here's the mint, escrow, approve, lists. So that was finished. Okay, so now you can see the deployed real estate contract is here. Okay, so now that we have compiled those and deployed them, I want to show you that, HARDHAT has put your artifacts inside of here, your contracts, escrow.sol. It has an ABI, okay, like this. And then also the same thing for real estate. You've got an ABI inside of here. You've also got your addresses saved. So what I want to do is go ahead and update some of this for our front end before we start building out the front end application. So basically, if you go into our source directory, this is going to be for our client-side application we're going to use next. We're going to make sure those ABIs are inside of there. Okay, so this is going to be the exact ABIs for the smart contracts for the escrow. Again, it's the exact same ABI as is listed inside of this file. And same thing for real estate. So basically, we're going to create a React app in the next section. So if we need to make sure that our ABIs are inside of there. If you modify your code in any way, you want to update your ABIs from this directory. Again, this artifacts directory, contracts, real estate.json, basically taking this ABI and copying it and putting it inside of this ABI right here. All right. Same thing for escrow, right? So the other thing is we have this config.json here. All right. So inside of our source directory, we have the addresses for the smart contracts that are deployed to HARDHAT. Okay. So the nice thing about HARDHAT is it's going to give you the same contract addresses every single time. So you shouldn't have to update this. Okay. So you can see this right here. That's the same address here. And then you could log the escrow address if you want to as well. You could just go to your deploy script and then say, you could do this here and basically just say, deployed escrow contract at escrow address. All right, and let's do a teardown exercise. Let's restart the node, npx hardhat node. All right, and then let's redeploy the contracts. Oh, I misspelled that. Let's see here. All right. All right, so deployed a real estate contract here and an escrow contract here. So this should be A6E0 and 0FC9. All right, let's go to our config file. Let's do it again. Let's restart. I think it's because we already ran this. Hold on. Got a fresh node. Let's do it one more time. Oh, sorry, that's this npx hardhat run scripts deploy. All right, yeah, AA3. All right, and then F0512, F0512. All right, so that's the whole idea. Is you want to make sure that the real estate address here is here, and then the same escrow contract that's here is here, because we need to save all this stuff in our front-end application so we can talk to those smart contracts whenever we start creating out the React application in the next section. So let's go ahead and do that. All right, so now what we're going to do is go ahead and start building out the client-side application. Okay, so the first thing we want to do is go ahead and open up a new terminal tab here. All right, make sure your blockchain node's running. All right, make sure you deployed your contracts like we did in the last section. All right, but now we're going to start our web server with npm run start. Okay, and I've already got this running here, but this is the old copy, so this should reboot. You should have a new browser open automatically. All right, and then you should be able to see your website there. So this will take us just a second, but boom, there you go. You should see this white page pop up. This is welcome to Millo. All right, that's our, Zillow clone here. All right, and you'll see all these kind of linter warnings inside of there. That's fine. That's because we have some boilerplate code. All right, so what we're gonna do is keep that running, keep our blockchain running. We're gonna open this in our text editor. Okay. And we're going to go to our source directory, and this is where all of our front-end files are going to live. So we have a React application inside of here. Okay, we've got this app.js file. Okay, this is some boilerplate code for the React app. Okay, we've got some libraries imported up here, like ethers. We've got some React hooks imported, like use effect and use state. We've got these other components in the components directory. We've got a placeholder for the home. For navigation and search, we'll dig into that. We got the ABIs for our smart contracts. Okay, the real estate ABI is here. All right, and the escrow ABI is here, and then our config.json file right here, which has the smart contract addresses that are deployed to the blockchain. Okay, and so we can see all that inside of our app.js. The app.js file is mounted inside of index.js right here. And we're also importing our CSS file, okay, which we wrote right here. So basically, we've already got some CSS preloaded. We don't want to spend a ton of time focusing on CSS in this tutorial. So I've gone ahead and just added the CSS for you so you don't have to write it from scratch, okay? Again, I just don't want to spend a ton of time on CSS. I'd rather focus on the blockchain side of things. So we've already got the CSS imported for you. And now we can basically go inside here at app.js and start editing things. So you can just edit this and see how it works. You can just add an exclamation point here at the end of welcome to Millo, exclamation point. All right. And you can see our changes were automatically detected here. So now what we want to do is also configure MetaMask. Okay. So what I'm going to do is go to MetaMask and make sure that's installed and go to add a network here. And then you want to make sure that you add the HARDHAT network. You can call it HARDHAT. Okay, you can do your localhost address. All right, you can literally copy this from HARDHAT and put it in here. Okay, it's already in use, so it won't work. Chain ID is going to be, let's just see here. Oh, it's in the project. Let me find it. The chain ID is going to be this. You can see the HARDHAT chain ID inside your config.json, so just copy that. Okay, go back to your MetaMask here, add it here. All right, currency symbol is ETH, and block explorer, you can just leave blank. Again, I've already done this, so it's not gonna let me save it because I've got a conflict here, but just click save, okay? That should take you back to your MetaMask, okay? And then you should be able to see that new network HARDHAT in your dropdown. Just go ahead and select it, and you should be connected to the blockchain. Now, let's talk about how to import your accounts. So you can go here to HARDHAT, all right, where you started it up. You can see these errors here. That's okay. Go find your accounts. And what I'm going to do is I'm going to import them one by one. So I'm going to take this private key, okay? I'm going to copy it, and I'm going to go to my MetaMask here. I'm going to go to import account, all right? And I'm going to paste in the private key, click import. It's already done it. All right. So I've already done it. It's going to give me an error. But if you haven't, it'll import it. And you should see it here. Now you can also go to your settings and then let's do this. Account details. You can rename it. I've renamed mine to HARDHAT 0 because it's the first HARDHAT account in the list, right? It's called account 0. So I call it HARDHAT number 0. All right. And then what I recommend, you're going to need to use multiple accounts in this tutorial. So go ahead and do this for the first 5 accounts on the list. 0, 1, 2, 3, 4. That's 5 different accounts. And whenever you've done that, we can look for like HARDHAT. I've got 0, 1, 2, 3, 4, 5 even. So maybe go ahead and do 0 through 5. And you'll see all those accounts are inside of there and you can switch between them and you can see the Ether balance in each of them. Okay. So now you got your project connected to the blockchain. You got your HARDHAT accounts installed. Let's go ahead and start coding out that front end. All right, so now let's go ahead and connect our project to the blockchain. So what I'm going to do is create a new function inside of my component here inside of React called load blockchain data. So let's say const load blockchain data. All right, that's going to be an asynchronous function. Okay. And inside of here, what we're going to do is we're going to go ahead and pull our connection from MetaMask. So MetaMask injects something into our browser called window.ethereum. All right, so you can even visualize that here. Let's see here, we got a problem. Let's just take this out for a second. All right, let's open our developer console so you can do inspect element or inspect, and you can see this pop up down here. You can click on the console tab, okay, and that will give you a JavaScript console. So we can see this global variable inside JavaScript called window, all right, and you can do window.ethereum, okay, and this essentially is our connection to the Ethereum blockchain that's injected by MetaMask. So window.ethereum in this case is the connection to the HARDHAT blockchain that we have running right here, okay. So we want to connect to this so that we can pull in the smart contracts and start creating a Dapp. All right. So inside of here, let's go into our load blockchain data here. Uncomment that again. So basically, need to change this. All right. And what we want to do, let's just save this. If we can look at the error. So really what we need to do here is just assign this. So essentially what we're going to do is create something called the Ethers provider. So again, Ethers is the library that connects our project to the blockchain. So by default, like our app is not going to talk to the blockchain on its own. That's what we need Ethers.js for. So we're pulling in Ethers at the top. And in order to create a connection to the blockchain, we can use something called the Ethers provider. So we do that like this. We just say const provider equals new Ethers providers Web3 provider, and we pass in this window.ethereum right here. Okay, so we can do that, and we can say console.log provider. Okay, and we can see it renders, and now okay, that's not working just yet. Let's just do that. That's okay. Okay, so first of all, we're loading the blockchain data. We're not calling it yet. Okay, so essentially, how do we do that? Well, with React, we're using a functional component here, and we can use something called a React hook, all right, which is going to let us do that. So we're going to use the use effect hook, okay, which is essentially going to get called whenever this component renders to the page. So we can say use effect, all right, and then pass in a function like this. And inside of here, we'll call load blockchain data, because here we just defined the function. We're not calling it yet. And then essentially we want to do this at the end. Pass in an empty array. That's going to detect any changes, but we don't care about that. So let's just save it. And then now you can see that we're logging the Web3 provider to the console. And so this is going to give us everything we need in Ethers to talk directly to the blockchain. Awesome. So with that, we can do things like get the account from our MetaMask. So we can get accounts like this. Basically, we can say const accounts equals wait window.ethereum request. We can say method eth request accounts. All right. and we can essentially log those to console. So console log accounts. All right. And then now we can see our account from MetaMask right here is logged to the console. All right. So great. Now we're cooking with fire. So what we want to do is basically save this account to the component state. Now let me talk really quickly about React component state. Okay, so React, uses components to organize our code. All right, so this here is a React component. We have some other components inside of here like home, navigation, and search. We'll get to those in a minute. But this is our main component. Basically, a component is just a place where you can, reorganize and reuse code and render them onto the page. But our components also have a state, okay? So a state is really just like, kind of like a little database inside of each component. So for example, you can see like this component here is a to-do list, and it has items on it, like item 1, item 2, item 3. All right, so where do those items go in this to-do list? Well, they go inside the component state. It's like a little database that exists inside of this component. Now, this example here is with a class-based component in React, but we're using functional components. So just like we did the use effect hook here, we can do a use state hook, which is here, and we can read and write from the React component state like this. So essentially we can do a component like this. We can do this. We can create functions for reading the account and setting the account like this. So we can say account and then set account equals use state null. So what it's going to do, it's going to fetch the component state and give us two different functions. One to read the account from the state and one to set the account to the state. And by default, we're going to say if the account doesn't exist, just return the null value. Okay. So then essentially we can write it to the state like this. We can do set account. All right, and say accounts is 0. Since it's an array, we can get the first item. And then we can do console log, account. Okay, and that'll actually read it from the state. So now we can prove that we can read it and write it from the state. So let's kill that. Back to our tab here. And now we can see, well, hold on a second. Let's do that. Let's just log it as account 0 first. All right. We'll read it in a different context in a minute. All right, good enough for now. Good enough for now. Well, let's actually create a component where we can use this account. So now we'll show you how to render another component onto the page and then use this information inside of there. So what we're going to do is take this navigation.js and build this out to actually handle the component and actually render the account on the page. So inside navigation, what we're going to do is we're going to sketch out some user interface here. All right. So basically, you can grab this in the final code solution below if you want to, but I'm just going to quickly sketch out some HTML inside of here. All right. So I've added some basic HTML for this navigation component. Okay. So we put a return inside of here for this function, and we've added a nav here. Okay. Inside of there, there's an unordered list, UL. It's called nav links for buy, sell, rent. Okay. And then this div here that is the branding. So it's got the logo pulled in. We've got that here. We have Milo as a site title. And then we have this button here that's going to show the account. So let's go ahead and render that component onto the page. Then we'll pass in the real account in a second. Okay. So up here inside of inside the app.js, we're going to just below this div, we imported navigation right here. And so we're going to render it onto the page. We'll just say navigation, and we'll do a closing tag like this. All right. And let's go look at our page again. And then boom, there we go. We can see we've got buy, sell, rent. We've got Milo as a brand in the middle. And then this button with our account inside of it, but it's not the real account. So that's just a placeholder. Let's actually fetch the real account. So what we'll do, we'll take this account here that we have requested, and instead of doing it here inside of load blockchain data, let's actually do it inside of our component, okay? So we're going to go to our navigation, and we're going to do this. And instead of just doing it automatically, we're going to have a button that lets us, connect to the account. So what we're going to do is we're going to use this here, this account and set account. We're going to pass them in to the component like this. We'll say account equals account, and then set account like this. All right. And we're going to take all this out. All right. And then we're going to create a function called connect handler. And we're going to put it inside of here. And it's going to do the exact same thing. It's say accounts, await, window, Ethereum request, get accounts. And we're going to set the account to the first account in the list. And then that's going to set it in the component state of the parent component. And we're going to pass it back in here with this account like this. All right. And whenever that finishes, we're going to render it onto the page. Now, we only want to do that if the account exists, and we want to have a button that calls this connect handler. So I'm going to take this out, and then I'm going to do this. Okay. So basically, this is going to be a conditional inside JavaScript that says if the account exists, show the account on the page, and let's truncate it. All right. We're just going to slice out the first few characters of it using ellipsis, and then do the last several characters of it. And but if it doesn't exist yet, we're going to let you connect to MetaMask. So you're going to click this button. All right. It's going to click the connect handler on click, and then it's going to load the account, save it to the component state here. It's going to pass it back down to the component, and it's going to show it on the page right here. Okay. So let's do that. Refresh the page, and then there's no account connected, but we have MetaMask installed, so we can just click connect, and boom, it will load the account, and you can see the first several characters of your account from MetaMask, just like they show you in the MetaMask UI with some dots in the middle, okay, and the last characters, and that matches the exact format there. All right, so now that we have loaded the account into the Navbar, I want to do one more thing here, which is I want to change and update the page if you change your account inside MetaMask. That's one of the reasons we're storing the account here in the app level. So I'm going to do this inside load blockchain data. The last thing is going to be this. So it's a window to Ethereum on accounts changed, okay, and pass in a function here. We're going to refetch the accounts just like we did, and then we're going to get the account and set account here, okay. So I'll pause that if you want to make sure that you've got the same code. All right, so basically you can see what that does is, we've connected, click connect. If we go to accounts inside of MetaMask, we go to HARDHAT, hat 1, and we click 1. All right, it'll automatically show the new account here. And then we can go back to our HARDHAT 0. Okay. And then it will go back 226. Awesome. All right, so now that we are done with the account section and the header, let's go ahead and look at our mock-up for our finished projects. We've got this part done. Now let's go ahead and add this search bar inside of there. So that's gonna be pretty straightforward. We already have a search component inside of here. All right, so this search.js. So really, this is just a placeholder for now, okay? This is kind of just a proof of concept mock-up, so we're not really gonna do any searching, but it's just gonna make it look like Zillow, okay? So you could add searching features here if you wanted to, but for now, we're just gonna add the search bar like this. Basically, just below navigation, we're just gonna type in search. Oops, search. I'm gonna close that. Okay, save it. And then, boom, there you go. Now, if I close this, it'll actually format correctly. But if I, load up the page, it's gonna overlap. That's okay. We'll just do that for now. So now we've got this implemented. And then finally, let's go ahead and scaffold out this section where we just show the homes on the page, okay? We're gonna go here and just create this div cards section, or I'd say welcome to Millo. We can take out the exclamation point from earlier. Okay. Let's, instead of saying welcome to Millo, let's say homes for you. All right, we'll do a horizontal roll here. Okay. And then we're going to have a div here. Div class name equals cards. And then inside of here, we'll just do this. we'll say div class name equals card. Okay. And then inside of here, we'll do a div that is the card image. Okay. Close that div. And inside of that, we'll do an actual image tag. Sorry. Okay. And then we'll just give it an alt home. Okay. Well, source, we'll just leave blank for now. And then we'll do a div. We'll say class name. It's going to equal card underscore info, 2 underscores. We'll give it a h4. And we'll just say, you know, this will be the price. We'll say 1 ETH. We're going to hard code this. We'll change it later. Okay. Then we'll give it the attributes. Give it a paragraph tag. Okay. And then we'll give it a strong. Give it 3. And we'll just say, this would be like 1, 2, 3. And we'll do space, beds. Okay. And then bath. And then square feet. Okay. And then finally give it the address. We'll say 1, 2, 3, 4 Elm Street. All right. So that should be the placeholder. Okay, awesome. So we got one home there, just a placeholder. We could copy and paste this a couple times to show some homes there. But now we're getting a lot closer to our mock-up, okay? So we've got the nav bar here. We've got the search bar. We've got the placeholder for the homes section. Now let's actually wire up the smart contracts so we can start listing the homes out on the page. All right, so now let's list the homes out on the page. What we're going to do is connect to the blockchain and get to the smart contracts and load them up into our app, okay? We've got the necessary pieces already. We've got the ABI. We've got the address from the config file. So let's connect to the blockchain like this. First of all, we want to, we've got the provider from Ethers. So we also want to create a hook to set the provider. So just above account, we can do provider and set provider as use state null. And we can say set provider. And then pass in provider, okay? And then next we can get the network, const network. We want to tell it what network we're connected to. In this case, it's HARDHAT. So that's the network ID that you see here inside your config file. So config here, this is the network ID. So different blockchain networks have different IDs, like the Ethereum mainnet's 1, like Arinkeby, I think is like 4, you know, et cetera, et cetera. So HARDHAT's that one, 33, whatever. So we get the network like this, await provider, get network, okay? And we want to save that, okay? And then use it, save as the variable. We'll use it when we read the contract. So we want to get the, basically we want to get the network because we want to find where the contract's deployed with this config file. So this config.json's got our address. We want to fetch this based on this network. We can get the address for the real estate contract, okay? So, you know, like the, basically we can read the config file already like this. So we can say like config, config, and then pass in network ID, dot chain ID, okay? And then get the escrow address, the same thing for the NFT address. Okay, .real estate address. So these are the two addresses, and we can console log those. You can just console log these so you can see that they're there. Let's just comment these out for a second. can see that they're logged to the console. So I pulled those straight out of our config file. Those are our smart contract addresses that are deployed to the chain. Okay. So let's actually create, JavaScript versions of this with ethers.js. So we can do that with ethers like this. We can say new ethers dot contract, capital C. And we can pass in the address for real estate. So we'll just copy this, put it in here. We need the address. We need the smart contract ABI. Okay, so we have that right here from the real estate ABI. Again, we pulled this in from our ABIs right here, real estate.json. So we take this, we paste it here. And then finally, we give it the ethers provider, which we did here. Okay, and then we just say const escrow. No, this is real estate, excuse me. Okay, I'll move this over so you can see it. And yeah, now we're able to actually get that as a JavaScript version of the contract, so we can call its function. So the first thing we want to do is get the total supply of the homes. Okay, so we can do that like this. We can just say const total supply equals await real estate total supply, and then let's just go ahead and console log that. It's going to tell us how many homes are in existence. Okay, so you can see this number here. Let's just do toString. All right, so there's three. There's 3 total homes that we can list. All right. And so now what we want to do is load the escrow contract. Okay, so we've got the real estate contract. Let's do a JavaScript version of the escrow contract. 2 smart contracts in this situation. So we'll do this, say const escrow. So ethers contract config network chain ID, this one, escrow address. And then we'll pull in the escrow ABI right here. Okay. And then this time we're actually going to save it to our state as well. So just below provider and set provider, we'll do escrow set escrow equals useState null. And then we'll load the escrow contract and do set escrow. Escrow. Okay. All right. So now we've loaded both smart contracts. Let's just go to our page and make sure everything's still working. Yep, we're good. Don't worry about this right now. It's still working. So now what we want to do is list out all the homes on the page. Okay. So we have loaded the real estate load total supply. And what we want to do is basically store all the homes so we can list them out on a page right here. So basically we're going to say, const homes. We're going to load them into an array. All right. So because we're stored, let's see, real estate. Because we basically have stored our NFTs inside of a mapping, we can't get them all. So we need to figure out how many there are and then loop through all the NFTs and fetch them out one by one. So we have the total supply, which we saved here. So basically we can say, we know there's 3 NFTs, ID of 1, 2, 3. So we can loop through those numbers 1, 2, 3 and fetch each NFT out individually and save them inside this array. So we're going to do that with a for loop inside JavaScript. So basically we're going to say for var I equal to 1. And then as long as it's less than or equal to total supply, we'll keep looping and then we'll increment by 1 each time after. So what we'll do is basically, we'll say const URI equals await real estate token URI. For I, this will be, number 1, the first time this runs, number 2, the second time it runs. We'll fetch the URI, okay? And then we'll get the metadata. So we'll get the response metadata from IPFS. And then we will push that into our homes array and we'll populate this for all the homes. And then finally, we'll set the homes with a useState hook, just like this. All right. And then we'll do set homes right here. Set homes, okay. And then now we can do console log homes to see if they've all been loaded. All right. So if I go back to the page, you can see here that there's an array, 3 different homes with all of the metadata. All right. So you can see here's home number 1. The address, you got the attributes, got the description, luxury penthouse, heart of NYC, ID 1, IPFS, luxury penthouse, okay, et cetera, et cetera. All right, so we've actually successfully loaded this from the blockchain. So now what we want to do is loop through all these homes and put them on the page right here. So we've got all this loaded up. Let's take out the console log. All right. And down here, let's loop through them all. So underneath this cards, let's evaluate JavaScript inside of here with curly braces. So that's the cool thing about React is you can mix JavaScript and HTML in the same place. You can see we've done that here, but now we're going to evaluate JavaScript here. We're going to say homes.map. So map is a function inside JavaScript that lets us loop over the array. We're going to access each home like this, and then also the index, which is basically just the position inside the array. Okay. And we're going to render all this content onto the page. So we're going to take everything inside this card. Okay. Take that out and we're going to put it here. All right. And then we're going to essentially give each home a unique key. React requires that. So we'll say key equals index. All right. And now that's just going to show us 3 of these cards on the page with no data, no special data, but it's going to show 3 of them. All right. So let's kill this. Wait for it to load. It might take a second for it to load for you. Give it just 1 second here. All right, so I realized I made a mistake here. It's a subtle thing in JavaScript. We need to make this a parenthesis instead of a curly brace because that's going to have an implicit return value. So let's just do that here. All right, so just convert that to a parenthesis and this to a closed parenthesis. So let's save that. Let's go back to our page here and then boom, there you go. Awesome. So now we actually see 3 different cards rendered onto the page. Yeah, I was saying wait, don't wait around forever. That was my mistake. Yeah, I just had to change that little thing in JavaScript, okay? So now let's actually fill in each of these homes individually to show the real home attributes. Like this is just hard-coded stuff here. But we are actually, rendering 3 homes. We should fill in all their data, okay? So let's go to the image. So for source, we can do home.image, all right? And then boom, there you go. We see 3 different pictures of the properties we want to buy here. Okay. We can do, for the price, let's do curly braces here and say home.attributes. And then we say 0.value. Okay. And then boom, there we go. Say 20 ETH, 15 ETH, 10 ETH. All right. So that's working. Let's do for beds, we can do this same type of thing. Let's just copy this, paste it here, and then let's say attributes 2 value. All right, now we see 2 beds. Same thing, let's just copy this here. And we'll change this to 3 and then 4. All right, now we can see these as unique values. So 2 beds, 3 bath, 4 beds, 4 bath, 3 beds, 3 bath, and the square footage is unique for each one of them. Now, finally, let's get the address, okay? So we'll just take this out and do home.address. All right, so boom, now you can see the unique address for each one. Okay, so we are pretty much finished in terms of the initial layout. So you can see, here's the mock-up, here's this. We got one discrepancy here. We need to capitalize for you so that it looks the same. For you. All right, so now it's looking the exact same as our mock-up. Slight sizing difference because this is a screenshot and this is a real website. Okay. But yeah, awesome. So now let's move on to actually finalizing the purchase and all that stuff. So what we're going to do is click on each of these properties. It's going to pull up a special tab for us to actually do the purchase. So let's go ahead and knock that out right now. All right, so now let's go ahead and work on purchasing the home. So the first thing we want to do is click on one of these homes, okay, and then have a pop-up that shows the home so we can go through the purchase, okay? So let's do that first. Let's click on a home, make a pop-up up here. So what we're going to do in order to make that happen is we're going to use an on-click handler. So inside of this card here, we're going to say on-click, okay, and then we say equals this, and then we're going to do this. Say toggle prop, and then we'll give it the home. Okay, so this is not a function yet. Let's create it. So up here, we're going to say const toggle prop. And we'll pass in the home. All right. And then we're just going to say console log home for now. So let's just make sure it's talking to it. All right, let's click on a home, and boom, it'll show us the home. So now what we want to do is actually have a special property inside of our a special state that tells us whether this is, you know, open or not. So the first thing we're going to do is use a React hook, okay, to set the individual homes. We have set homes and homes here, but now we're going to do singular. So we're going to say home and then set home. All right. So what we're going to do here is basically just say set home, home. All right. And then we're going to have a toggle, which basically is going to toggle the component, whether it's open or not. And so we'll say, it's below home, we'll say toggle and set toggle, use state false. Okay. And inside of here, we're going to say, you know, if toggle, question mark, say set toggle, false. Otherwise, set toggle, true. Okay. And then down here, what we're going to do is check to see if the toggle is active. So we'll say toggle, question mark, and this, and we'll just render home. Okay. And we already have this home component imported here. All right. And now we just got, you can see components home.js. We have a placeholder for the home right here. Okay. So let's go back here. And we already got a problem here. That was my fault. I'll take this question mark away. That's my fault. I made a stupid mistake. All right, let's do that. And then let's close this. And let's click on a home. And now we can see this overlay has popped up. All right. And a home should appear. Now, it's not doing anything yet. That's okay. We can see our screen kind of goes dark. It actually is popping it up. We just haven't filled out any of the HTML inside this home component yet. All right. So you can see this home function accepts some different arguments, like the home itself, the ethers provider, the escrow contract, and the toggle prop. So let's go ahead and pass those down. All right. So right here, we'll just add those like this. We'll basically just say home, and then, you know, the lowercase home, and provider is provider, and account is account, and then escrow is escrow, and then toggle prop is toggle prop. Okay. And now those should be inside of our component. And so now what we want to do is start filling this thing out. All right. So now inside of here, let's start filling this out. First thing we're going to do is create a new div inside of here. Okay. We call it home details. All right. We're going to close this as well. It'll put all the content inside of here. So next we're going to add basically an image for the home. So we'll do a div for home image. Again, this is going to pick up the CSS we've already written in that CSS file, so you don't spend much time writing CSS yourself. And we're just going to go ahead and add an image tag inside of here with the home.image. Oops, all right, this. So we'll just do image, source home.image. So we got home here. Okay, so let's just save that. Go back to our thing. So toggle pop is not defined. Toggle prop, sorry. Okay, let me just fix that. So I think I called this prop. This should be pop. Sorry, everybody. Yeah, toggle pop-up, basically. That's all I do. All right, so let's do that. Click on this, and now we can see we have a pop-up that's just got the home image right there. So now we can fill this out even more. Okay, let's go ahead and create a way to close it. All right. So down here, just below the home details, we're going to add this button that basically closes the pop-up. So basically we'll add a button down here like this that basically just says, button toggle pop. It'll, once we click it, it'll make it go away. And we can have an image here that just says close. Okay. And actually we want to put this inside the home details as well. Like this. All right, so now we see this X here. And click it and it goes away. Awesome. And that X is coming from this close, which is just an X that we've saved already inside the project, imported right here. Okay, let's keep going here. Let's figure out some more attributes. So below the home image, we can create a new tab, or new div, excuse me, called Home Overview. All right, and then we can close that div. And inside of here, we can give it an H1. We can give it the home name. So home.name, save that. Click on home. You can see luxury penthouse. That's working. Fill in some more details, like this. The home, just like we did on the home page. So we can give it a paragraph with some strong attributes, home attributes, 2, 3, 4, beds, bath, square feet. And then we can also give it the home address and a paragraph below that. And then just below that, we can give it the H2 for the ETH value. All right, so boom, there we go. We can see some description here. Luxury penthouse, 2 beds, 3 bath, 2,200 square feet, address, 20 ETH purchase price. Okay. Now we can let's give it a button to buy. Okay. So we're going to change this in a minute, but now we're just going to give it another div here. Right here, we'll just give it a div. We'll give it this button. Okay. So this button will basically just be the buy button for the, oops, sorry, home. Take out all this stuff. We're not going to do any on clicks yet. Okay. We'll just give it a basic button. All right, we're going to change this in a minute. So I'm going to give some space. That's obvious. But we'll just give it a div, home buy. All right, you can save that. And then now you can see this buy button comes up where we'll click it and we'll actually do the purchase in MetaMask. Okay. And then we'll have a button here to contact agent. Just like you'd see on Zillow or something. By contact agent. And then we'll give it a horizontal rule and another H2 for overview. And then we'll give it the home description like this. Home.description. And we'll give it another horizontal rule. And we'll give it like facts and features. Okay, we'll fill those in a second, but let's just take a look at what we're doing here. Yeah, it's gonna look better. Luxury penthouse, buy, contact agent, overview, luxury penthouse located in the heart of NYC, facts and features. Let's give it an owner list here. So we'll say UL. And basically we'll map over each of the home attributes and add a list item like this. Okay. But basically we'll just do that in one go. We'll say home attributes, map attribute index. We'll give it an LI, key index, strong attribute trait type, and then attribute value. That's from the NFT metadata. All right. Boom. There you go. Facts and features, purchase price, type of residence, condo, beds, bath, square feet, year built. Okay. All the metadata you want to see on a Zillow property. Okay, so you can click buy, contact agent, overview, all the details you want to know. Okay, so now we have successfully wired that up for each property. You can see how those values change for each one. Now let's actually facilitate the purchasing behavior. Okay, so now for the complicated part, we essentially want, the different accounts with their MetaMask to come here and approve the transaction. So like the buyer's going to click the buy button, right? but the lender can come in here and fund it on the same website. The inspector can, sign their approval on the same website, all in one place with their MetaMask wallet. So in order to do that, we want to contextually show a different button here based on who's connected, okay? So the first step in that process is fetching the different accounts from the smart contract to determine what we want to show you if you're the buyer, seller, lender, inspector, all that type of stuff. So let's go ahead and create a function to fetch those values from the blockchain. Okay, so above the return function, or return right here, we're going to do const fetch details, okay? And inside of there, we're going to get the buyer, okay? So we're going to get the buyer's address like this. Basically, we're going to say const buyer equals await escrow buyer home ID. And this will return the Ethereum address. Because again, we did that inside the smart contract. Let me just show you. You can see, we have the seller address, the inspector, the lender, and the buyer in the mapping here, okay? So the buyer's listed inside that mapping. So essentially, we can just go here and do escrow buyer and then pass in the home ID, and it'll tell you the buyer address, okay? And then we want to save that to the component state. So we'll say buyer, set buyer from use state, okay? And also, we want to also store the lender. So we'll do that there. Lender, set lender, inspector, set inspector, and seller, and then set seller. Okay, and we'll populate those right now. So we'll do the same thing here. We'll basically, do the same thing for the seller. So we'll do buyer. Also, we need to set the buyer like this. So buyer, seller, set seller. And we'll do lender, set lender. And then we'll do inspector, set inspector, okay? And if you remember, we did all those in our deployment script here. So you can go to scripts, deploy, and you can see which accounts. So buyers, account 0, account 1, account 2, account 3. And we save all those here, okay? Let's go back to our site, refresh just to be double safe, and then no errors. Okay, nothing in the console. We have the same error from before. Don't worry about this. Code should be still working just fine. Okay, so another thing we want to do is we want to keep track of each of these people's actions. Okay, so basically we want to see if the buyer's actually bought. Okay, so what we're going to do is do like this for the buyer. We're going to say, const has bought, await escrow approval, home ID, and the buyer. And we want to set that value. So we're going to say at the top, say has bought. Okay. And then we're going to say set has bought right here. All right. And then we're going to do the same thing for the lending, same thing for inspection, and same thing for selling. Okay. So do that for here. Has lended, set has lended. And then has inspected, set has inspected. And then has sold, set has sold. All right. And then we'll update all those for after the seller. We'll say has sold equals await escrow approval, home ID, seller. And then has lended. Basically, we'll go here. Has lended, escrow approval, home ID, lender. And then inspector. All right. Has inspected, inspection passed, home ID, set inspection passed. Now, finally, we're going to fetch the homeowner so we can keep the status of that. Basically, going to do const fetch owner. All right. And inside of here, we're basically going to say const owner equals await escrow buyer and get it for the home ID. All right. And then we're also going to set the owner up here. Okay. So we'll have owner, set owner. And then we'll update the owner right here. Okay. And then one other safeguard condition we're going to do inside of here, basically, we want to make sure that the home is listed. All right. So we're going to return if that's the case. All right. And now finally, we want to call these two functions. So we've done fetch details and then fetch owner. We want to use effect. All right. And we want to call those two functions. Fetch details and fetch owner. And then we also want to detect is has sold changed, okay? Which is here. If has sold changed, we want to fetch all this stuff over again. That's what this does. If this variable changes, then it'll recall these functions on use effect. All right, so now that we have loaded up all that information, we can show a different value here based on who's connected with MetaMask and what they should be doing in the transactions. Like if you're the lender, you can see like a lend button here, like approve and lend, approve inspection, all that type of stuff. So let's go ahead and make that contextual. All right, we'll go back to our back to our code here. And right here where we see this buy button and contact agent, okay, we'll do this, all right? So basically we're gonna evaluate JavaScript inside of here. We're gonna say owner. Oops, sorry, not oneer, owner, question mark. All right, and then we'll give this a conditional. So that'll be the first condition, second condition. All right, so we'll break this up in multiple lines. So if they're the owner, we'll do this. Otherwise, we'll do this, okay? So if they're the owner, we're gonna give it this div. All right, owned. Okay, and then basically we'll say, oops, sorry. Inside this div, we'll say, owned by this owner, right? We'll slice the address and display on the page. Okay. And then otherwise, in this other condition here, we're going to add a new div. Okay. And now we're going to see if the account is equal to the inspector, question mark. If that's the case, then we'll do this. I'm sorry. Okay. And we can do like, yes, if not. So if they're an inspector, we'll do this. All right. And then basically, otherwise we'll say, account equals lender, question mark. All right, and do a new condition here. All right. Oops, sorry. And then we can do another thing here and say account equals seller, question mark. And say, and if not, otherwise, we'll just do this condition. So now we can detect if it's the inspector, if it's the lender, if it's the seller, and everybody else will show, we'll show this buy button. So let's go ahead and take that buy button, and then let's put it inside of here. Okay. And then we'll put the contact agent here, take this out, take this div away. So just below this. Nest that inside of there. Okay. So if none of these accounts, we'll show the buy button. Now, if it's the inspector, okay, we want to have a button here that says approve inspection. Okay. If it's the lender, we'll say approve and lend. All right. If it's the seller, we'll say approve and sell. So now let's go check our page, make sure nothing's broken. So account is not defined. Okay, so let's get the account here. So we need to pull it from up here. Basically, we need to make sure we're passing in the account here. So we'll do account at the top, there, component, home, provider, account, escrow, toggle pop. And the same thing here, home, provider, account, escrow, toggle pop. All right. So now let's go back to our page. So we misspelled account on line 98. Let's fix that. All right. And then now it should work. Okay. So now we can see that we have the buy button. Okay. So let's look at our deployment script. So the first count in the list is a buyer. So they should be able to buy the property. That's fine. Second account should be the list, should be the seller. All right. So if you go to MetaMask and then go to HARDHAT 0 or HARDHAT 1, click on that. You can see it changed to approve and sell. HARDHAT 3 or HARDHAT 2. We can now see approve inspection as the inspector, and then HARDHAT 3, approve and lend. All right. HARDHAT 4 is, let's connect, and then you see it's buy. Okay. So, you know, basically every single account that is listed, the button is now contextual. Okay, awesome. All right, so now what we want to do is click these buttons with each individual MetaMask account to process the transaction. So again, you know, we have to go through this to essentially, you know, do every single step in the real estate transaction. So I'll pull this up on my whiteboard here. Again, we need to basically act as multiple different accounts, essentially to fund the deal, approve the inspection, approve it as the buyer and the seller, and then, you know, in the smart contract, actually facilitate the purchase and transfer of the funds and also the NFT for the real estate. So let's do that. Basically, we want to click a button for the inspector, click a button for the buyer, for the lender, click a button for the seller, okay, and then click a button for the buyer. So we want to create some functions up here. So just below this, I'm going to drop these in. So we'll do a buy handler, an inspection handler, a lend handler, and a sell handler, okay. So I'll stop my screen right there if you want to copy those down. And then now what we want to do is call each of those respectively, all right, down inside of the thing. So for this one, for the inspector, the button here, we want to say, you know, on click, and we want to do inspect handler. I'm going to call that function. And also we want to disable this button if the inspection's already happened. So we'll say disabled. We'll say and has inspected. Okay, so we're going to use this in our state up here. Okay, so we've got that for each different property. So I'm going to copy these and put them on each of these. All right, we're going to change that. So for lender, we'll say lend handler. Oops, lend handler, and then also has lended. And for sell handler, then has sold. And then inspect handler, or sell handler. Oh, sorry, buy handler, my fault. And then has bought. So now when we click these things, they should be firing off the functions, okay? So now we need to actually wire these functions up to do each phase in the transaction. Okay. So for buying, what we're going to do is basically do all the calculations underneath the hood. Basically say const escrow amount equals await escrow amount, home ID. So we're going to see how much we need to do. And the buyer's basically going to deposit the earnest money directly into the contract and approve the transaction. So it'll be two transactions. So the first thing we want to do is get the signer, all right, from the buyer. Basically, signer equals await provider gets signer. All right, that's the current account we're connected with MetaMask. We'll let them deposit the earnest money first. Okay, so basically the deposit earnest like this. Transaction equals await escrow connect signer, deposit earnest, home ID, and the value in that transaction is going to be the escrow amount, which we fetch from the contract. They'll send that to the MetaMask wallet when we do the transaction wait, and then they'll call a second transaction, which is the approval step. So they'll approve the transaction, say await escrow connect signer approve sale, and then home ID transaction wait. All right, so I'm going to format this. I'll bump these over actually. All right. And then finally, we just want to set has bought to true so that it disables the button when they buy. Okay. So same thing for inspection handler. Basically, we're going to do a similar process. We're going to get the signer, which is the first account from MetaMask. Okay. All right. And we're going to update the status like this. Basically, we're going to say transaction equals await escrow connect signer, update inspection status. And then we're going to set has inspected to true. All right. And then we're going to do the same thing for the lender. Basically, we're going to get the signer. Account signer equals await provider get signer. And they'll approve the transaction first. Okay. So just like we did the approval here, we'll say lender approves, transaction equals await escrow connect signer approves sale. And then they're actually going to send in the funds for the funding the deal. Like this. Say we get the amount, lend amount is escrow purchase price minus the escrow amount. All right, so basically we say how much did the buyer put down and what's the home purchase price. We factor in the difference, and then they actually send Ether directly to the escrow contract with this amount. And we say set has lended true. All right. And then finally for the sale handler, I'll just pause that in case you want to see it. Hold on. All right. And then finally for the sale handler, we'll do a very similar process. We'll get the signer. The seller will approve the transaction. All right. And the seller will actually do the finalizing the sale. So they will actually facilitate the transferring of the NFT to the owner and new owner, and then they will get the funds into their wallet, and we'll say it has sold to true. Okay, so I'll pause that if you want to see that as well. All right, so let's go through it. All right. So right now, we can see, let's go ahead and change the owner. So let's go look at our accounts in MetaMask, and let's look at the deploy script. So the current owner should be the seller, so it should be account 2. Okay, so if we go here, let's go ahead and switch that account. So the HARDHAT 1. All right. Oops, sorry. Okay, so actually the owner, sorry, the NFT contract currently owns it, so we're not going to see that right now, so my fault. Well, we'll see that update after the NFT has been sold to the new owner. So let's go back to the buyer account. So we'll just make that HARDHAT account 0. Okay. And let's go through each step. So we'll be the buyer of the account 0, click buy. All right. Let's, it'll ask us to deposit 10 ETH for Earnest, click confirm. And then next transaction will pop up to do the approval, confirm. And then we should see success inside of our HARDHAT account. Okay, approved sale, contract interaction. Awesome. So now let's go to the next account, which is going to be, let's see here, we've done buy. Let's do inspection. So let's look at our deployer address. So inspector is the third account. So 0, 1, 2. Do this. 0, 1, 2. All right, let's see approve inspection. Click confirm. Well, let's make sure that was green. All right, contract interaction done. Now let's go to the lender. So 0, 1, 2, 3. All right, so approve and lend. Let's approve first. All right, confirm. And then second transaction comes up. This will be fund 10 ETH. All right, so both those were successful. And then let's finally go to the seller account. HARDHAT 1. All right, approve and sell, 2 transactions. First transaction to approve. All right, and second transaction to finalize the sale and transfer the ownership. All right, boom, done. Now we can see that the transaction has taken place, and now it is owned by this new account. So we can go to our account here and make sure that this is the right one. And we can see that 2266 has now the address. It's owned by that. So we have the NFT. Our balance has gone down, and we can check the seller account. Received the ether. So yeah, the seller received the ether for the sale. So boom, we've done it. We've successfully done a real estate transaction on the blockchain with smart contracts with cryptocurrency. So that brings us to the end of our tutorial here. So I hope you liked this video. Of course, there's a lot of things you can do to improve upon this. You could add searching functionality. You could deploy this project out to a test network. You could deploy the website live to the web so that other people can do this. But this gives you an idea of the power of smart contracts and how you can completely automate this process with blockchain. So let's do a quick introduction to the Solidity programming language before we start, coding out some complex smart contracts. Just as a primer for anybody who's brand new, or in case you want a refresher on exactly what Solidity is and how it works before we get started. So, Solidity is an object-oriented, high-level language for implementing smart contracts. So basically what that means is that, Solidity is the primary language for writing Ethereum smart contracts. It's high level, okay, which means you don't have to do a lot of low-level system interactions, okay, as a developer. It's object-oriented, so smart contracts are basically the building blocks used for blockchain-based applications. They can talk to one another. They support inheritance. It's also a pretty beginner-friendly language, okay, on the grand scheme of things, right? So if it's similar to Python or JavaScript or C++. So if you're familiar with any of these languages, you're probably going to pick up on a lot of things with Solidity pretty quickly. But if you don't know any programming languages at all, it's relatively beginner-friendly, which means that you can pick it up pretty fast on the grand scheme of things. It's also statically typed, which we'll see as we start coding out the smart contracts. It supports inheritance, libraries, all that type of stuff. It's a Turing-complete language, so that it's a fully featured programming language so that you can write pretty much any app that you want to with smart contracts. Although it doesn't always make sense to write every app as a smart contract, which we'll see. It's definitely a capable programming language. All right, so the best way to learn Solidity and how to create smart contracts is just to jump in and start doing it. And the easiest way to do that is to create your first smart contract step by step and do it all in your browser. So that way we don't have to install anything on our computer to get started and just see how Solidity works. So head on over to remix.ethereum.org. So this is a Solidity IDE, and really what that means is it's a place where you can write code for smart contracts, okay, and store them like in folders here, okay. You can edit the code. You can see some contracts inside here already. Here's an example, Solidity smart contract, and then you can compile the smart contracts inside this in-browser IDE, okay, and then you can also deploy them to a blockchain. It's got a fake blockchain in the browser, okay. If you want to, you can add your MetaMask wallet and deploy the smart contracts to a real live blockchain. So it's a fully featured IDE all in your browser that's going to make it really fast to start coding without having to install anything on your computer. So we'll do this for now just so you can see how it works, and then we'll move over to our development environment so that we can actually do things like test the smart contracts and add them to source control like you'd want to do if you were developing out real projects. But this will be a great way to get started. I use Remix all the time. I use the right tool for the job when it's appropriate. So go ahead and head on over to remix.ethereum.org. Let's create our first smart contract here. Okay. And we're just going to do this plus icon, and actually not this one. Sorry. We're going to do this right here. I get confused with the Remix interface sometimes. Like this is kind of ambiguous, but this is what you want. So click this. All right. Actually do it inside the contracts tab. There you go. And then we'll call this counter, capital C, OUNTER.SOL. So the convention for Solidity smart contracts is that you capitalize the file name because that's the smart contract name. You want to use the exact same name in the file as you do the smart contract. And then .SOL is the file extension for the Solidity smart contract. So inside of here is where we're going to create our first smart contract. So we'll do that like this. We'll just start off with some basic code. All right. We're going to start off with declaring the Solidity programming language version. We're going to use the latest version of Solidity for this tutorial. So we'll say pragma Solidity. Okay, that's how you tell the compiler which version to use. And then for now, we're just going to say use any version greater than 0.8.0, which is the latest major release for Solidity. You can see the documentation here. It's on 0.8.15. Okay, we're just going to say any version greater than 0.8.0, which is fine for tutorial purposes. When you're doing production smart contracts, I recommend locking the Solidity version at the latest version, but this will work for now. So we can create our first contract like this. Let me go and bump up the font here. That's probably not the best way. Let's just do it like this. Like this. There we go. Awesome. And we'll say counter. So contract, capital C, counter. And then we'll use the curly braces like this. Okay. So that's how you create the smart contract. You use the contract keyword. You give it the contract name, capital C, counter, just like I did with the file name here. And then inside these curly braces, okay, this is where all your code is going to go. Because anything you do for the smart contract is going to go inside of here, and anything else is outside the smart contract's scope. So what do we want this counter contract to do? Well, we want this to be a simple contract that illustrates just how smart contracts work in the first place, show you the basics of the programming language, like how to create variables, basic data structures, basic functions. We're quickly going to move beyond this to much more complicated real-world use cases here in a minute, but this is just going to give you a quick primer. So what we're going to do is create a smart contract that essentially is a counter. So it's going to store a numerical value, and then it's going to let you increase the count and then decrease the count. Okay, and then also we'll say store a name and set name. Okay, so really, this is supposed to illustrate how CRUD works with smart contracts. So if you're a programmer already, you'll understand this. If you're not, basically CRUD stands for create, read, update, delete. And that's going to show you how the smart contract performs those actions, and it's going to give you an introduction to how the functions work for smart contracts so that you can perform these types of things. So let's look at a quick diagram for that. So I'm going to pull up my diagram on my screen here. If you were to create this as a CRUD app, inside of a web application, let's say, you would have a user that's connected to a browser, and that, browser will connect to a website, and then that website will connect to a server, all right, some sort of backend, which call this backend. And just a simple example, let's say the server stores the application code in like Python, JavaScript, or PHP, okay, and then you'd have a database where all the data for the application is stored, maybe with MySQL or MongoDB, okay. So let's take out the website and the browser side of the thing, and let's just pretend we were building this as a backend application, like an API, for example. Well, your user would connect directly to the API on the server, and this is where the business logic for the application would live. Let's say you're doing it in Python, right? You'd write like a class or something that lets you, store the count in the database, all right? And then read the count from the database, and then you have some sort of business logic and maybe API endpoint that would let you update that count and also fetch the current count with maybe a GET request and like a POST request, okay? So how's it different with blockchain? Well, basically, the blockchain will work like this. User would have a wallet that can connect to a browser, and that browser would connect to a website that would just connect straight to the blockchain. And you'd have all these nodes that talk to one another, and these nodes store the programs and also the data at the same time, okay? So the smart contract is going to be, the thing that has the business logic and also has the create, read, update, delete logic inside of it that writes data directly to the blockchain. So you can kind of think about like a smart contract as a little microservice in itself. It's not a perfect analogy, but if you understand the Web 2.0 world, that's kind of what you're doing here, okay? So, we're essentially going to create a small, blockchain microservice-like thing. That's really what we're doing here. It's a building block, okay? And it's going to actually read information from the blockchain, write information to the blockchain, and it's going to have a public interface where anybody can do that. So it has these characteristics of, you know, a microservice, but the blockchain itself, the public ledger, is actually the database where the data for the count is actually stored. So we could do that like this. So if I were to save a count on a blockchain, I could do it with a state variable, okay? So I could do it with a state variable called count, okay? And you can declare a state variable inside Solidity like this. And because Solidity is statically typed before, like I was saying before, you have to give the type whenever you declare the variable. So I can say uint count, which stands for unsigned integer, okay? So what does that mean? Well, integer, of course, is a number like this. And an unsigned integer means it has to be positive. It can't be negative. So this is a minus sign. That's a signed integer. So an unsigned integer means it cannot have a sign in front of it. So it must be positive. Okay. So uint is count, unsigned integer count. All right. And this is now a state variable that I've declared, which basically means that this variable value is going to get stored directly on the blockchain. Okay. So whenever I read this information from the blockchain, it's going to actually, after I read this variable value, it's actually going to read the information from the blockchain like a database, okay? So I could initialize this variable and say the count is 1. All right, now if I were to put the smart contract on the network, it would store this unsigned integer count 1, all right? And if I were to read it out, it would show me that the count is 1. So I can read the value, right, from the chain like this. I can just say uint count, uint public, count equals 1, and it'll actually store that on chain. Okay, so I can show you this. Like I can go to compile here, compile counter. All right, and then I can go here and deploy it. All right, that's the compilation step. Click compile. All right, it'll compile the code down. And then if I go to this is deploy. I'm just going to click Remix London. So okay, this is basically just the fake blockchain that's in our browser, JavaScript-based blockchain that's going to let us deploy. Okay, you can see it's got an account here with 100 fake Ether in it. We can pay the gas fees, the transaction to do the transactions, and we can just click deploy, and then boom, there you go. We can read the count. It's 1. All right, so that's really a simple smart contract. Technically, that is a contract with really simple behavior. All it does is store this value on chain. Now, it's not very useful. Okay, it's not very useful. We want to actually create some functionality to update this count. Okay. So let's do that. And then we'll go through and explain some more of the steps in deploying the contracts here in a second, but that's just a quick example. So, what I'm going to do is, so anyways, I just want to show you how state variables work, show you that Solidity is a statically typed language that you have to declare the type before you do the variable name. And whenever I do this public here, that's a modifier. So what that does is it tells Solidity that I want to be able to read this count outside this variable value outside the smart contract itself. So public basically just means make this public so I can fetch the value later. And the Solidity compiler, what it does, it actually gives me a function called count. Whenever I go here, I can actually click this count and it'll show me what the count is. And if I took this off and redeployed the contract, right, and just let's do it again, compile and deploy. Like, see, this contract doesn't have a count function available. Right, so it's useless for me to just store this value on chain and not be able to read it later. Okay, so I'll show you another type of variable value. So we can do multiple data types. So we can say string public name, and we could call this. Let's just say here we'll call it my counter. Let's make these double quotes. So string is just a group of characters inside of quotation marks here. All right, and we can say string public name and then string public count, my count. Okay, you can do all different types of data types in Solidity. You can use arrays, you can do mappings, which we'll see later. All right, we can do compile and then deploy, and you can read it. All right, here's the name, right? My name, and then count is 1. Okay. So again, these are just values that are stored on the blockchain. We give it a name, we give it data type, and we say public, which lets us read it outside the smart contract later. All right. So now I want to talk about the constructor function with smart contracts, which is the function that gets called whenever you put smart contracts on the blockchain. All right. So constructor function is run once and only once. Okay. And it's what lets you initialize smart contract with certain values. All right. So we can do a constructor like this with a keyword constructor. All right. And then just give it a function that looks like this. All right. And inside of here, we could initialize these values. So instead of setting my name in line here, we could just say name equals my counter. All right. And we could say count equals 1. Okay. So the constructor function is a special function with a keyword constructor that's run once and only once whenever we put the smart contract on the blockchain. So I could do that like this, click compile, and then I could go here and then click deploy. I can see the count name. All right. And then let's see here. We can also do arguments inside the constructor. So this is how you do arguments inside of a function. We can pass these in upon deployment and just say, instead of hard coding what the values are going to be, we could let the deployer set the values like this. We can say string memory name and then uint initial count. All right. And then we just do like this. And then count is initial count. All right. And so what this is going to do is let us pass these in whenever we deploy the contract to the blockchain. So let's just kill this and go here, click compile, deploy, and let's see here. You see this deploy function? Okay, this is what's going to run the constructor function, and you can see that it already has populated the constructor arguments. So if you click this drop down, it's going to show you each thing that you can pass in. So we can call this, foobar. Okay, initial count is 5 or something. Click transact, and then you can see deployment here, and we can read count is 5 and name is foobar. Okay, so that's how a constructor function works. You can give it arbitrary arguments that you can pass in. And one thing I'll note here is that I'm using underscores for my function arguments. That's just a convention that I use. You don't have to do that in Solidity. There's nothing special about this in the programming language, but sometimes I'll name, variables the same. And these local variables, we don't want to have naming conflicts with the state variables, okay? And so I'll use underscores just to differentiate those. Some people don't like that convention. I do like it. I just stick with it. So, I think I'll say about variable scope inside Solidity is that public variables, state variables you can read anywhere inside the smart contract. But local variables, you can only read inside the function names themselves or inside the functions themselves. So if I created a new function down here, which we'll see in a minute, I couldn't access this name value. And I cannot access this name value. I couldn't say name equals, name. It wouldn't know what that is. You can only read local variables inside the functions themselves. Okay. So let's go ahead and create another function. All right. To show you how it works. Okay. Let's use a function to increment the count. Okay. So function increment. All right. Let's see here. And they'll say like this. All right. That's how you create a new function in Solidity. You just give it the function keyword, and then you give it the function name, and you add the the parentheses here and the curly braces. Okay. Any arguments for the function will go inside of here, just like the constructor. And then any code that you want for the function will go inside of these curly braces. All right. So what we want to do is basically increment the count. So we're going to take this count and say count equals count plus 1. Literally, that's what increment's going to do. It's just going to take the count and add 1 to it. Okay. So you're reading the count from the state variable, you're adding 1, and then you're updating the value. Okay, so that's increment, just increases count by 1. All right, so we can compile this. All right. we need to do a couple other things. Sorry. So after this, we need to do a couple other things. Number one is we need to make it public. Okay. So that's the visibility of the function. So we set the visibility of variables like this, public. This gives us access to the variable outside the contract. We have to set function visibility so that we can know whether we can call this function outside the contract or not. So we could call this private. We could call it internal. We could call it external. Okay, lots of other things, but we're just going to call it public for now. All right. And we're also going to give it, let's just see if we can get away with that for now. I've got some other code I'm going to add to it, but let's just see if it gives us any issues. It does not. So we can do that. And then we can, let's just see here. Let's delete our other contracts and then do name, my account, and then additional account is 1, click transact. And then we'll click the count, say it's 1, and we'll click increment, and then we'll look at the count. Now it's 2. All right, so you can see it going up every single time. All right. So that is our first function. Use a function keyword, give it the name, and then you give it the visibility, and do count plus 1. So another thing I'm going to do here is, instead of doing count plus 1, I'm going to do a shortcut inside Solidity, where I can just take away all this, and then just say count plus plus. All right. So this is called the increment operator, which basically just takes the value and then increments it by 1. Right? You might have seen this in other programming languages, and Solidity supports this. We don't even have to reassign count here. It does the exact same thing. So I'll just illustrate that. Compile. My contract 1, transact, count is 1, increment. All right. All right. So you can see that. So another thing I'll do is add a return value. Okay. So say returns. We can do here. We can do return count. So whenever we get the return value of the function, we can get the new count. And we have to specify that in our function here. We say returns, and we can say uint new count. All right. And then let's do this. Let's compile. All right, I'm going to say my counter 1. And then count, increment, count. Awesome. Oh, sorry, increment, and then count. Awesome. Okay, so now let me stop and explain this too. So you can see the account here. Like you can see the blockchain that we're connected to. You can see we're connected to this account. Here's all the accounts we've got. And you can see that these accounts have 100 fake ether inside of them. Okay. And you can see that the ether value is going down. So why is that? Well, that's because whenever we are putting smart contracts on the network, we're creating transactions. And anytime you create a transaction on a blockchain, you have to pay a gas fee. Okay. So this gas fee is in some amount of cryptocurrency. And you can see that because we've paid to put smart contracts on the network, our cryptocurrency balance has gone down every single time. That's just because we had to pay a fee to put that contract on the network. That's called a gas fee. And we pay this gas fee every time we do any type of transaction. Now, a quick note about gas fees and transactions is anytime you write information to a blockchain, like you're putting a smart contract on a network, or you are sending cryptocurrency around, or you're calling a smart contract function that actually updates the state, like this increment count, you have to pay a gas fee. But if you're just reading information from the blockchain, like if I click this count and I'm just fetching the count, right? That doesn't cost me anything because reads are free, but writes cost gas. That's because the gas fees help prevent spam on the network. It's not spam to just read information, but if you want to sit here and click this increment button all day long, right, you have to pay a gas fee in order to do that because it's writing information to the chain. But reading information to the chain is free. But if you deploy the smart contract to the network, that's writing new information, and you have to pay a gas fee to do that. That's why you see the account balance going down. Like you can see, this is also 257, and then if I click increment, it's now like 574. It went down. Okay. So let's move on to our next function. We are going to do the opposite of increment, which is decrement. So we'll say function decrement. All right, we'll say public returns. We'll just say uint. We'll say new count, just like the other one. And inside of here, we're going to say count, but instead of plus plus, we're going to do minus minus. All right, then we're going to return the count. Okay, and so we can see this here, compile counter, let's deploy again. Let's just kill these. Say foobar 1. Okay, and then count is 1, and so increment is count. All right, then decrement, count is 1. All right, decrement again, count is 0. Now I want to show you something here. We're going to get an error if we click decrement again because the count is currently 0, and because the unsigned integer is public for count. Okay, we're going to click decrement again and then see this error. So you can see VM transaction reverted. Basically, you can't make the count go below 0 because it's an unsigned integer. And remember, you can't have a minus sign, so you can't make it go below 0. That's why we get an error if we try to decrement the count below 0. All right, so let's add a couple more functions just for practice to kind of see how the functions work inside Solidity. Okay, I'm going to create a special function to get the count, just to show you there's multiple ways to do this. Of course, you can create a public state variable here to, read the count just by calling count. But you can also, these are examples of explicit functions that write to the blockchain. Let's create some functions that explicitly read from the blockchain. We can say a function get count. All right, it's a public view, so returns uint. All right, so what is this? Well, basically get count is going to let us, we can't use count because that would be a naming conflict with this function here, but we can just say get count is a new function that we've defined. It would say public, and view is basically just means a function that's going to read information from the blockchain and it's not going to modify the state at all. So it knows you're not going to pay a gas fee in order to do it. And we compile it and deploy the contract over here in Remix. It's going to be blue. It's not going to be orange like these other ones. You can see these are semantically colored. The orange ones you have to pay gas fees for, and the blue ones you don't have to pay gas fees for because they just read. So view is going to just be a read function, read-only function, doesn't modify state, and it's going to return an unsigned integer, which is just the current count. So we can just say return count. Pretty simple. All right. So the next one we want to do is create one that returns a name. So we say function get name. All right, public view returns, and this was kind of funny. So we say string memory, and we'll say current name. Okay, and then we'll just return name. Okay, and then we'll click compile. All right, and then we'll just say, we'll just kill this. My contract 1. All right, and then we can see the count is 1, and we can increment count is 2, decrement count is 1. We also get count, all right, it's 1. All right, and we can see name is my contract, and we can also get name is my contract. So it's the exact same behavior, but these are examples of how you can do multiple strategies to accomplish the same thing. Either get it for free like this, or create a function that does it. But it also illustrates how you can just create reader functions. So if you want to create a function that returns some information, this is how you do it. And you wouldn't always just want to read a simple state variable value. You want to do more complex things sometimes, as we'll clearly see later in this tutorial series. But that just shows you how to get simple values for now. And the last thing we'll do is just show you how to create another function that updates the state that accepts arbitrary arguments. Okay, so right now this is just calling increment and decrement, and it just has custom behavior to increase and decrease the count. But let's create a function that sets the name. So a function that actually writes new information to the blockchain that accepts arguments. That's not a constructor function. So we'll just say function set name. Okay, and then like this. Okay, so we'll say public. Okay, so let's actually just update this name here, and we'll say name equals new name, and we'll pass in the new name as a function argument. So we'll say string memory new name. Okay, and we'll say public returns string memory current name. Well, let's say a new name. Okay. And then we'll say return name. All right. And then we'll say compile. And also the code for all this is down in the description below if you want to find out about any of that. Compile. Let's go here. All right, let's kill this. And we'll say, string my contract count as 1, click transact. We'll go here. Then let's say the set name. First of all, let's just look at the name. Name is, my contract. Get name is my contract. So new name is foobar. Okay, set name. And let's read it again. So foobar and then foobar. All right, so that is the overview of our first smart contract. So you've seen how to create a basic smart contract with Solidity programming language, how to put it on a blockchain. We showed you how to use state variables, how to create your own functions, how to create a constructor function that gets run, how to do read functions, write functions, functions with arguments, functions without arguments, public visibility, private, view, all that type of stuff, okay? So there's a lot that we've covered in this really simple example. And I showed you how to do everything in your browser, okay, inside of Remix. So that's an introduction to a lot of basic concepts inside Solidity. Now what I want to do is take this example and move it out of the browser into our development environment so that we can actually write tests for smart contracts and develop them like we would if we were maintaining a real project, okay? So that concludes this section. Now let's move on to testing the contracts. All right, so now let's start developing smart contracts on our computer. So we're going to use the HARDHAT smart contract development framework in order to do this, okay? So HARDHAT is a framework. Essentially what a framework is it's a set of tools that lets you create smart contracts that saves you time where you're doing routine tasks where you don't have to write all the code to do it, okay? You can do things like write tests for smart contracts, okay, which we're going to do here in a second. You can write scripts for smart contracts. You can deploy them to a blockchain, all from your project. Okay, and that's what HARDHAT is for. You can also do things like create client-side applications to talk to your smart contract with React inside the same project and make a HARDHAT talk to React and things like that. But for now, I'm going to show you how to essentially go from browser-based development to local development, which is definitely the next step that you're going to want to take if you're creating a real project so that you can commit your project to source code. Commit your project to version control, stuff like that. So we're going to use HARDHAT. You have one basic dependency, which is Node.js. So make sure you have Node already installed, okay? You can go to your terminal and type node-v to see if you have Node installed already. All right, I'm using 16.14.0. I recommend using the same version if you're a brand new developer. You can if you're a seasoned developer already, it doesn't matter. You're probably going to be able to figure out how to change Node versions, but just to eliminate the variables, I recommend using the same one as me. Your mileage may vary if you use something else. So let's create a new project. I'm going to go to my terminal here. I just keep all my projects in the code directory. Somebody asked me the other day, do I need to use the code folder? You don't have to. That's just where I keep my code. And you can create a new project like this. I could say make directory, say mkdir, and I'll just call it my Solidity project. You can call it whatever you want to. Okay, and we'll enter into that newly created directory like this. So we'll say cd my Solidity project. Okay, and then we'll create our HARDHAT project, going through the HARDHAT setup steps here. Okay, we'll just say npm install save dev HARDHAT. All right, we'll actually do npm init. I believe that's the first step. Okay. That's going to create a new node project. My Solidity project is fine. Enter, description, blank's fine, enter. I'm just hitting enter to move through the stuff. I'm going to do the author as this email. Okay. And then, yes, that's fine. So now we want to follow the HARDHAT instructions, which are, you need a package.json file in order to save the dependencies. So we'll say npm install --save dev HARDHAT. Okay, and then that's going to install the node packages on our computer here inside our node modules directory. All right, so that's done. That's going to put all the HARDHAT dependencies inside of there. Okay, and now we can start creating a new hardhat project like this, we can do npx hardhat. Okay, so what this does, npx is essentially a command that lets you run executables from your node modules directory. So you might see things like npm run, right? That's going to execute things from your globally installed node modules, but npx lets you execute things from your node modules directory, which is in your project is what I mean. And so that makes sure that you're using the hardhat version that's specific to this package install. So you can see the startup script here. Do you want to create a new project? I'm just going to do JavaScript. If you're a TypeScript person, you can do that. Click yes, yes. Do you want to add a git ignore? Yes. I'm just hitting enter. And then do you want to install this sample project dependencies? I'm going to hit yes. I'm just going to enter. Okay. And wait for this to finish. All right. So that's done. Okay. All right. So now I'm going to do is go ahead and open up my project in my text editor. I'm going to use Sublime Text. You can use whatever text editor you like. I have this subble command configured on my computer just to open up stuff quickly. You don't necessarily have to do that. You can use whatever text editor you like. But I'm going to show you a quick tour of the hardhat project. It comes with a sample smart contract inside of here. You can see this lock smart contract. Okay. You can see some tests inside of here. Here's a test for the lock smart contract. So, tests basically let you I'm trying to find tests without using the word test. They let you, they let you demonstrate the behavior of a smart contract and make assertions on that behavior to verify that it works the way that you expect. Okay, so you can see, we'll talk about testing here in a minute, but basically it's automated testing. So everything that we were sitting here doing in the browser a minute ago, we're sitting here clicking around all this stuff to make sure that the behavior is right. That takes a ton of time. Okay. And so if you were going to go check the smart contract code every single time, you'd have to go do that every time, but you can write code in JavaScript here that just, automates that entire process to make sure that the contract behaves the way that you want it to. So for example, we can look at the lock smart contract inside of here, just do npx hardhat test. All right. And it's going to run all the tests in the test folder here. And you'll see that it actually compiles that lock smart contract and then runs through these checks to make sure that it works the way that we expect. And you can see the developers, which we'll do here in a minute, just creates all these test examples. Okay. And then says it should do this, it should do this, it should do this, it should do this. Okay. So that's how it works. So let's go ahead and start doing that same thing ourselves. We're going to take the contract that we just created and we're going to put it inside of here and we're going to write a test for it. Okay. So basically, I'm just going to go into Remix and I'm going to take this, I'm going to copy everything, and I'm just going to go inside this lock here and I'm going to say new file. And I'm going to call it counter, capital C, counter.sol. Okay. And then I'm going to paste in the code from my other counter file. Okay. And I'm going to take out this white space here. All right. And then one more thing I'm going to do is I'm going to go to this lock file and see this license identifier here. I'm just going to copy it and then I'm going to put it at the top of my project like this. Okay. So this is just something that the compiler wants to do. It just wants to see the license identifier and we're going to call it unlicensed. That's fine. If you don't do that, you're just going to see this warning every time you compile your smart contracts and it's going to get really annoying. So now I've got the counter inside there. We're going to delete this lock. Okay, just click delete here. We don't need that lock file anymore. All right. And then we're going to go to this lock.js and click delete. All right. Okay. And I'm actually inside the test. We're going to create a new file. And we're going to call it counter, capital OUNTER.sol. sorry, not counter.sol. Sorry, we're going to do, let's just do it like this. Test counter.js. Okay, now you can see a new file here, counter.js. And this is where we'll write all the tests. Tests go here. All right, so one more thing I want to do before we continue on with this. All right, I want to actually install some more dependencies on our computer. I'm going to go to the final code solution here from the GitHub repository and go to the package.json file, okay? And I'm actually going to just like copy the package.json file and then paste it into my project to ensure that we have the same stuff, okay? So you can see package.json. I'm just going to do this, and then maybe don't call it Solidity tutorial, just call it the same project name. I'll just say my Solidity project. You just use your project name here. And of course, you'd have your own author email here. But I'm just going to make sure this has all the dependencies that I need to write my tests and develop my smart contracts. I'm going to go back here and do npm install again, just to make sure that those dependencies have installed and that they're in my project. Okay, so that's done. And that's going to save us. We don't have to do more project configuration after that. So now what I want to do is take this counter, okay, and then basically I want to write tests for it. All right, so I want to show you how automated testing works. So testing with HARDHAT is going to use the Mocha testing framework and the Chai assertion library. So basically, these are really popular JavaScript frameworks for writing unit tests and integration tests. You know, you can do things besides just blockchain with these, but they come bundled in frameworks like HARDHAT and also Truffle. So Mocha is the testing framework, and the Chai is the assertion library. That's what lets us write test assertions. Well, I'll explain that when we get there. But for that reason, you know, at the top of our file, the first thing we want to do is import Chai. So we'll do require const expect Chai. Okay, so basically Chai is the assertion library. Expect is something that we use to write test matchers. Okay, so I'm going to increase the font here so you can see this. And then we also want to import ethers.js, which is our library that talks to the blockchain. We can import that directly from HARDHAT. The HARDHAT framework comes with ethers already. We can just take ethers out of it, and so we can use this in the test. So another quick explanation is, you know, most common way, if you're a JavaScript blockchain developer, that's what I recommend for most people who are getting into the space. You know, tests are typically written in JavaScript. Okay, I mean, you can write tests for smart contracts in Solidity. Okay, but the nice thing about JavaScript is you can simulate client-side interactions. You know, you can use the same code that you would use on your front-end website or in other scripts inside of your tests, okay? So, I mean, if you're a Python developer, you might be writing tests in Python. But the whole point is I'm going to highlight here is we're not writing tests with Solidity. We're writing tests with JavaScript. And so if this is your first introduction to JavaScript, you know, you might encounter some new things here. But yeah, this is where a second programming language comes into play. And Ethers is the library that lets us talk to the blockchain. So if you're creating a blockchain-based website, Ethers is the website that essentially turns your website into a blockchain website. And it's also what lets us connect to an Ethereum node and do things like interact with accounts. Okay, you can see, I'll just pull up the Ethers.js websites. If you want to, you can do some more looking at that here. Okay, so like this will tell you more about Ethers. You'll see what you need to know about Ethers as we go on throughout this tutorial. All right, so inside of our test, we can write the tests inside a describe block, which is something that comes from Mocha. Okay, so we can say describe. So really it's just a function. Okay, so it's a function that accepts two arguments. The first is just the name of the thing you're describing. So we're going to say counter. And the second is a function. So this function is, we're going to pass it in like this. We can use an arrow function in JavaScript. So if you're new to JavaScript, then you can write an anonymous function with arrow script like this, or arrow syntax like this. Okay. And so basically this function that we're passing in is going to contain all the test examples for this counter that we are describing. So counter is the name of the smart contract. Okay. And then inside of the test, we can do this thing called, let's just do this. Let's say describe deployment. Or let's just do this. We'll just say it sets the name. That's going to be one description of what the smart contract does. Is it stores, or we'll just say it stores the count. So what you're doing is you're describing the counter and you're saying its behavior. So you say describe and say it. You can say stores the count. All right. And we can say function. And then pass in like the behavior that we expect inside of here. So we can say, basically, we can fetch the count. Inside of here, what we want to do is we basically want to fetch the count and then check the count to make sure it's what we expect. So how do we do that? Well, first, in order to fetch the count, we need to get the contract from the blockchain. Okay. So we can get the we can get the contract with ethers.js like this. We can say ethers get contract factory. Okay. And then call it counter. All right. So this is basically ethers.js. We do get contract factory. It's going to fetch the counter for us. It's going to understand how to do that from the HARDHAT framework because we've already compiled the smart contract and it's got this artifact inside of here. Okay. Well, it will whenever we run the tests. But we can store it to a variable like this. We can say const counter. Okay. And then we can say we can deploy the contract to the blockchain like this. Say counter counter.deploy. And then say my counter. Then we give it the constructor arguments. So my counter. All right, remember this, the constructor takes 2 arguments. The first one, let's just see here. The first one's going to be the name. The second one's going to be the initial count. Okay. So deploy my counter. And then also the initial count is going to be 1. We can also store this to a variable and say const count. Okay. And then we can check it. And we can say, expect, which is this matcher that we're pulling in from Chai. We can say count to equal 1. All right. That's how we fetch the count and then read it. Now, we need to change this a little bit. Okay. So, JavaScript supports asynchronous actions. Okay, that's one of the reasons we use it to communicate with blockchains in the first place. It's a good programming language to do that. And because blockchains are slow, okay, and blockchains are slow, so it's a perfect marriage of a programming language that supports asynchronous execution, and then also a thing that is slow that needs to be interacted with in terms of asynchronous execution. So we want to use something in JavaScript called the async await pattern, because right now, this is not going to work. Basically, this is just going to return a promise. Okay, I'm going to wait for that promise to resolve. I don't get too far into how promises work right now. It's not meant to be a deep JavaScript tutorial. It's more to show you how to work with smart contracts. But basically, just know you got to do this. We want to wait for this to finish. So we say await ethers get contract factory, and then await counter deploy to store this variable to a variable, because it's not actually going to return the value from the blockchain. It's going to return a promise unless you do this await. And because we're doing await, we have to use an async keyword on this function. So async, all right, because you can't call await unless you're inside of an async function call, which does things one by one rather than, you get the idea. So counter equals await, ethers get contract factory counter, and then count equals await counter, big capital C, which is the contract itself. Once it's deployed, we store that to a variable. This is the actual deployed contract. I did this wrong. Counter. And then, sorry, I don't know what I'm thinking here. And then const count equals await. Let's just see here. Counter.count. Okay, we can fetch the count like this. Expect count to equal 1. Sorry, I typed that wrong a minute ago, but this is what we want. So counter capital C is the ethers contract. Counter lowercase c is the deployed smart contract once you've actually deployed it to the blockchain. It's the JavaScript version, which we can call the functions on. That's what ethers.js allows us to do. And then lowercase count is the actual count that we're going to read from the blockchain. We say expect count to equal 1, which is the initial count that we added to the constructor function here. Okay, and so we can do, I don't want to name him install, sorry. Let's say npx hardhat test. All right. And we can see this passes. Awesome. It stores the count. So we can make this test fail. Expect the count equals 2. It's going to fail. So it fails. You can see got 1, expected 2. All right. And now we can see that this behavior works. And so that saves us from having to go inside a remix and like, check the count every single time and like recompile the smart contract. Like, oh, it's a bunch of clicks of a button and we can just write a script that checks this, okay? So let's make this test better. Let's kind of refactor it. We're going to use this. We're going to actually check for the, we can say it sets the initial count. Okay, and you can also say it sets the initial name. So we could get name here, and then we could say name is name, and then say expect name to equal, my counter. Okay, save this, and then run the test, and see it passes. So it sets the initial count, it sets the initial name, and so that works, but this kind of sucks because we're just repeating ourselves. You can see that we're doing this here, and we're doing this here, okay? So we can refactor that out into something called before each. It's a special function, which is going to do something before each test example runs. Okay. And then that lets us basically take this and then put it in here so that we don't have to do it twice. And then we can say let counter, which is going to declare a variable that we can access inside of here and also inside of here. Okay, and then we can see if that passes. Okay, so see undefined, we're reading count. So it can't do, let's do this first. Let's do before each. Let's do this also. Let's say describe deployment. And then let's put this in here. And this is going to do the deployment examples. Okay, let's also kind of nest this. Let's run our test again. All right, so we got a little issue. Let's just see here. So counter does 15, not 35. Okay, so oh, I see. It's because we said let counter and we did const counter here. So let's just say we've declared let here. We don't want to redo a const inside the before each. So let's try that again. All right, now it passes. Awesome. So sets initial count, sets the initial name. And we've added these to a deployment section. So that describes initial deployment. We can also shorten this instead of keeping them instead of storing it to a variable value. We can literally just make this a one-liner and then put it inside of here. Okay, and say await counter count to equal 1, and then get the function call for the name and then put it inside of a one-liner here, and then on npx HARDHAT test, and it still passes. Awesome. So now let's say describe counting. Describe counting. This will be actual counting behavior. And then we'll give it a function here. And then inside of here, we're going to say it. Let me just bump this up down here. Reads the count from the. Let's start with increments the count. Increments the count. And we'll say async because we're going to do that pretty much in most of our test examples because we're doing blockchain transactions. So let's show how to write new information to the blockchain and then check. So we can say await counter.count. So let me also just show this with two, tabs here. We can see let's do our Solidity code here. Okay. So we want to test this increment function. Okay, where we can actually check this. We want to call this function to see that it actually increments the count. So we're going to say counter, instead of count, say increment. All right. And then basically we're going to check to see what the new count is. So, we can get the count like this, right? So we can say let count equals await counter.count. Okay. And then we can say expect count to equal 2, okay? Or we can just say, await counter count equal to after we call increment. But what we want to do is actually wait for this transaction to finish. So we're going to say this, let transaction equals await counter increment, and then say await transaction wait. That's how you do it inside of with ethers inside of HARDHAT. You want to actually do the transaction and say await transaction wait, and then call counter count, and then look at the new count. So say impacts HARDHAT tests, and then boom, it worked. So it increments the count. So what I want to do now is reset transaction, and then I want to, because I want to do this in multiple test examples, so I'm going to refactor this and declare the variable out here. I'm going to say transaction equals await counter increment. All right, and then wait transaction wait. And then let's do it again, just to see that the counter keeps going up. All right, so let's do increment as again. And then say expect await counter count to equal 3. And then let's do it again. Awesome, increments the count. So let's do the decrement function. Okay, so we'll just make this one a lot faster. I don't need to belabor every single point in the tests. Let's go ahead and do a decrement function like this. Let's just copy and paste this. Okay, we'll say it decrements count, and then we say transaction await counter decrement, and then it should now equal 0. All right, so let's take this out. All right. Now, I also want to show you how you can test for an exception. So remember I did it before in the console, in Remix, I showed you if we try to decrement the count below 0, it's going to blow up. Because if you start out at 1 and then you call decrement, it goes down to 0. But if you call it again, it's going to throw an exception. And so I'll demonstrate like this. Basically, I'll do the count again, okay, and then just watch the test blow up. So you can see VM error, exception while processing transaction reverted for panic code, arithmetic operation underflow or overflow outside, and unchecked blocks. Basically, that means you tried to make an unsigned integer something that it's not supposed to be, which is less than 0, -1, it's got a sign, it's no longer unsigned, it's no longer valid. So you can actually check for exceptions like this. You can say, take this out. You can say expect. You can say cannot decrement count below 0. And you can say expect await counter decrement to be reverted. Okay, and that's going to expect a revert message inside Solidity. Hold on a second. I don't think it worked properly. Let's try it again. Hold on a second. All right, so I need to change this syntax. I need to take this off and then say await expect. All right, that's actually how I want to do it. And let's just try it again. All right, awesome. It passes. So it actually checks for the behavior whenever we increment and decrement. So we'll do a couple more quick tests just to wrap this section up and show you how you can, do tests. Above here we can say, reads the count from the count public variable. Oops. All right. And then we can copy this. We're going to show this. There's multiple ways to read it. Right. So it reads from the count public variable. It reads from the get count function. All right. So we can say basically, expect. It's the same thing. Expect await counter count to equal 1. Sometimes you can do this in unit testing just to show what each specific part of the smart contract does. Okay. And then you can say reach from the get count function to expect await get count to equal 1. All right. And you can see this nice readout in the test. So describe deployment, it sets the initial count, sets the name, and counting it reads the count from the public the public variable, and reads from the get count function. It increments the count, it decrements the count. All right. So now we can also talk about the name. So, it reads, we can just copy these and modify them for the name here. You say it reads the name from the name public variable, counter name to equal my counter. I believe that's what we called it up here. Yep. And then get name. All right. Okay. And then lastly, we can say it updates the name. And we can basically just say transaction equals await counter set name, say new name. And then we can say await transaction wait expect await counter dot name to equal new name. Save, run our test, and boom, it passes. Awesome. Okay, so that is it for our first smart contract and your introduction to testing smart contracts. So, we covered a lot in this section. Testing is super important for smart contracts because you always want to make sure they work properly before you put them on a blockchain. Because, of course, once you write the code, you can't change it, and you want to make. And a lot of times, smart contracts actually store real money, so you want to make sure that they are bomb-proof before you put it out there in the wild. And testing is a critical part of that. And instead of sitting here, clicking buttons inside of Remix all the time for real-world smart contracts, you want to write some unit tests, maybe some integration tests. And this is how you do it inside of HARDHAT. So now let's move on to the next section. All right, so now let's move on to our next smart contract example, where we're going to create a much more complex smart contract than a basic Hello World smart contract that kind of does something really unique that I haven't really seen in other Solidity tutorials, which is basically taking things that we already use in the blockchain now and then coding out use cases that haven't really been adopted yet that show the power of smart contracts. So I actually, put a tweet out on my Twitter when I was talking about what I want to show inside the Solidity tutorial. And one of the most requested things was, hey, show me something that people aren't actually doing with blockchain now. And that's what we're going to do in this. So we're going to code out a smart contract that facilitates a real estate transaction. And we're going to model the real estate, the property in this case, with a non-fungible token or an NFT. Okay, so let me just explain that. If you're not familiar with what NFTs are, essentially, they are non-fungible tokens, that follow the ERC 721 standard. You can see examples of Bored Ape Yacht Club. One of the most popular use cases for non-fungible tokens are crypto collectibles. Okay, like this, where each token is unique. All right, each token has an ID. And you can own each token, okay? And then you can, sell them on an open marketplace. But basically, you can use NFTs for so many things, beyond just these crypto collectibles. We can use them for intellectual property. We can use them for ownership of physical assets. We can do things like real estate. It's perfect because real estate is already a non-fungible asset. Each house is worth a different amount. And you can essentially talk about the ownership. You could model the ownership of a house with smart contracts. Okay, and you can make them programmable. So, whenever you go sell a property, you typically have this kind of convoluted process where you have to essentially, get a buyer to communicate with the seller, usually the realtor, and then you go to this closing where, in the closing, a lot of things have to happen before the sale actually takes place. You usually have to get an inspection and see whether it passes. You usually have to get an appraiser to appraise the house to make sure that it's worth what they think it is in order for the lender to give you the appropriate loan to value ratio on the property. If you're taking out a loan for the property, you have to get approved for the loan. Okay. And then, you have to put in some sort of earnest money, typically some sort of deposit to lock the contract up under contract. I mean, we're using the term contract here. It's a pretty good indication that you want to use some type of contract, and the smart contract could be an alternative to that. And then, at the end of the day, a real estate transaction is a financial transaction where you're transferring ownership, and that's what smart contracts are great for. So, we could get a lender to fund the deal inside the smart contract, and we could get, the buyer to receive the proceeds instantly upon the sale, and then also for the, real estate ownership, which can be modeled by a non-fungible token, that ownership transferred from the seller to the buyer. Okay, and you can kind of see the steps listed out here on the side. We'll revisit these, but we're going to create a smart contract that essentially does this. It puts a property in escrow, okay, and lets a buyer put money in escrow, and then go through the process of passing an inspection, going through an appraisal, going through the lender, and then transferring the ownership of the NFT from one account to another. Okay, so let's go ahead and get started doing that. All right, so inside of our project, let's go to our contracts directory. Okay, let's create a new contract inside of here. I'm going to close out the counter and say new file. I'm going to say real estate, capital R, real, capital E, estate.sol. Okay, and I'm going to close out this test. And what I'm going to do is actually just copy and paste the real estate smart contract. Now, let me explain why. Okay, this is not really a big deal. We're going to do a lot of custom coding with the escrow smart contract. So basically, we are going to use an NFT to model the real estate. Right, it's going to be a non-fungible token like this. So non-fungible tokens essentially conform to a standard called the ERC 721 standard. You can see this example here. That basically specifies a common interface that's supported by wallets, supported by marketplaces like OpenSea, et cetera, et cetera. So for that reason, we want our NFT basically to work like other NFTs. All right. So we don't want to reinvent the wheel here. And we just want to make sure that it is a basic NFT with a balance of, owner of. We can do things like transfer from one account to another, do safe transfer from, approve, all that type of stuff. Okay. And so in order to do that, we can just use a library. All right. We can use a library called OpenZeppelin. There's no need for us to code out an NFT from scratch. OpenZeppelin is a great open source project that gives us tools that we can build apps quickly. And there's no point in us coding out the NFT from scratch for the sake of this example. So we're just going to take the code from OpenZeppelin to get started. So that's also going to show you how to use libraries inside Solidity, which is a nice thing to know for sure when you're developing smart contracts, because in the real world, you're probably going to be using some libraries for some things. So go ahead and head to the repository for this. There should be a link down in the description below. Go to contracts, go to real estate. All right. And then go ahead and open this up and click raw. And then I'm just going to copy all this. And then I'm going to put it inside real estate. And then we'll see this. This is all the let me just close this out. All right. This is all the library code up here. Yeah, this is also from OpenZeppelin. Like, I didn't write this from scratch. Don't worry. You would never have to write that from scratch. You could import it, right? But this is the flattened file. Don't worry about it for now. It just makes it easy to get started. And then here at the bottom, you can see like how we create the real estate contract. Basically, we're using all this library code. We're saying contract real estate, all right, is ERC 721 URI storage. That's just the OpenZeppelin name for a contract that supports, the URI storage like this. This is all boilerplate stuff, okay? And then we're creating a constructor function inside the smart contract. Of course, we saw the constructor function was the function that gets run once and only once whenever we put the contract in the blockchain. And we're creating a token with a name and a symbol. So it's called real estate, all right, with the symbol real. And then we are minting a new NFT with this mint function that we've created here, okay? And that puts the smart contract in the blockchain and puts the metadata on the blockchain as well. Now, let me explain this metadata part, okay? So with NFTs, okay, basically, you have the NFT smart contract, which is really just a smart contract that keeps track of all the NFTs in the collection, who owns the NFTs and how much, okay? And then it facilitates transfers of ownership between NFTs from one account to another. All right. And there's one smart contract that governs all of the items in the collection. You don't have like a separate smart contract for each collectible or house in this case. Okay. So, but the pictures for the NFTs don't live on chain. So if you look at like the Bored Ape Yacht Club, like this picture is not stored on a blockchain. Okay. It's going to be stored in this thing called IPFS. So let me just pull that from my screen here. So IPFS, what is that? It's an interplanetary file system. Okay, this works kind of like a blockchain, but it's not a blockchain. Basically, it's a distributed file system where you can store files across different nodes, and then they're not on a central server. So I've already put some metadata for the NFT on IPFS, okay? And so you can see the metadata like this. You can just copy and paste this. That's why I wanted to copy and paste from the GitHub so that you can just see this quickly. I don't want to go through all those steps. I just want to focus on the Solidity coding so we can put in the IPFS. This is our IPFS link here, and you can see this is the metadata. So this is our property. So it's going to be this address, okay? So I can, let me just pull what's up here. You can see the actual property address. Here's the address in New York. You can see this actual listing. It's a penthouse for about $42 million, I believe. All right. So it's pretty healthy budget here. Monthly taxes of only low cost of $15,000 a month. Anyways, so yeah, we could say description is luxury, MIC penthouse. Like basically, you could do exactly what you would do on Zillow, right? If you look up the Zillow listing for this, let's actually just look at it. Let me just move this over. Basically, you could do all this type of stuff, where you could see all the metadata. So Zillow stores metadata like this. You can see it's got the address, it's got a description, right? It's got images. You could do all this stuff with an NFT, and you could list them all on a website, and then you could have somebody just like go on Zillow and like go through the process of purchasing the real estate, like with a MetaMask wallet. And I know it's not like probably the future that we're going to see with blockchain, just like that easy, right? But that's what's possible, right? I'm just kind of showing you a proof of concept for how this would work. So let's continue on with this. Let's look at the rest of the metadata. So there's that. We've got the image, which is in a separate IPFS link. So it's nested. So you have this metadata that has the initial metadata, like the address, the purchase price, number of bedrooms, number of bathrooms, square feet. Okay. And then you can add an image like this for the property. So then you could store it on a website and create your own like Zillow clone, with your NFT like this. All right. One more thing I'll say about this is, with this project, like this mint function, what this does is when you create the NFTs, it starts off with 0 NFTs in the collection, and then it creates it from scratch. That's what this mint function does, is it mints a new NFT. And then you can see, like, you add in the token URI, and it adds like a new NFT to the collection. So you can also see like an example of this token, like on like how it would look on OpenSea, that you can actually see that it actually works with the metadata. So you could see an example, like here's an example of how this property would look on OpenSea if you were to buy it like with a Zillow-like experience. So you can see the metadata. You can see that it's got all these attributes, details. All right. So now let's go ahead and talk about the escrow contract, because we ultimately want to sell this to somebody else. So really quickly, I realized that I accidentally created my real estate contract in the root directory. So let's just move that really fast. Let's move it into the contracts directory, contracts, real estate.sol. So you should see it right next to your counter file. Okay. So we can also add this license identifier at the top. Okay. So now we want to go over and create this escrow contract, because the whole idea is we're going to deploy the contract, and we're going to mint an NFT for the seller. So that's going to be the person who currently owns it. But then we want to have this escrow contract that essentially facilitates the entire real estate transaction, where, they approve the NFT, and then goes through this entire process of, putting down earnest money, and then, funding the deal, and then, transferring the ownership and going through inspection and appraisal and all that type of stuff. Okay. So let's go ahead and create the second contract called escrow. So in the same directory, we'll create a new contract called escrow, capital E, escrow.sol. Okay. And so same type of thing. We'll use this license identifier at the top. We'll do the same Solidity programming language version. Okay. We'll say contract, escrow, capital E. And put all the code inside these curly braces. So inside of here, we want to do, there's a lot of stuff that we want to do. All right, but the basic thing is we want to essentially, transfer ownership of property. All right, so we'll code out that basic functionality first. But we'll do all this other stuff that has to happen before it can transfer that ownership. And we'll kind of walk through these one by one. But let's start off with the heartbeat test, which is essentially making sure that this ownership can be transferred. Okay. So let's think about what we need to do here. We need to code out some sort of function that actually transfers the ownership from one account to another. Okay, so basically, we want to say, let's just code out a function called finalize sale. Say function finalize sale, and this is where we'll go through all the steps that checks out the sale. And then here is basically where we want to transfer ownership of property. Okay, that's the basic functionality. I also want to pay people, right? But for now, let's just make sure we can move an NFT, because that's the most essential part, is that we move this NFT from the seller to the buyer. Okay, so let's go start creating out a test scenario for this. All right, so basically, let's go here and then go to test and then go to counter and create a new file, and we'll say we'll call it real estate.js. Okay. And then inside of here, we'll of course say expect, and then ethers from HARDHAT. And then we're going to say describe, say real estate. We'll pass in a function. Okay. And then we'll do the same type of thing, where essentially we say, before each. All right, and we say async. And then basically we want to deploy the real estate contract. So we will say const, let me just pull this over. Const real estate equals await get, so await ethers get contract factory real estate. And then we also want to do the escrow contract. Escrow equals await ethers get contract factory escrow. Okay. And we want to first, deploy the real estate contract. So we can just say, deploy contracts. We can say, load contracts here. Okay. And then we deploy real estate like this. We could say real estate. Oops, sorry. Say, let real estate equals await real estate dot deploy. All right, then we can say let's declare it outside of here so we can read it in other places. So we can say let real estate. All right, and then we also do the same for escrow, and we want to say escrow equals await escrow dot deploy. Okay. And so let's just check the deployment first. So we'll say describe, say deployment. And let's just check that the seller actually has an NFT. Okay, so what we're going to do is, it sends an NFT to the seller. We'll say /deployer. All right, it's async function, and then passes in. So what we want to do is actually have an account that's connected. So basically, we want to set up some accounts inside of ethers.js, inside this test, that represent the different people in this transaction, because there's a lot of people. There's a seller, there's a lender, there's an inspector, there's an appraiser, there's a buyer, okay? And they all have different roles in this entire scenario. So what we want to do is create a variable that represents the seller. So we can get the accounts inside Ether.js like this. We can say set up accounts and say accounts equals await ethers get signers, and then say deployer equals accounts 0. So basically accounts is going to be an array here, and we can read out each item from the array. The 0-based index, so 0 is going to be the first account on the list, 1 is going to be the second account, etc., etc. And then we can just say a seller equals deployer. We'll just do, we'll sort of reassign this. And then we can say, for the accounts, we can say let deployer seller, so we can access these values throughout the entire test suite. Okay. And so basically we can just say expect await real estate owner of. So this is a function on an ERC721 token. We can say owner of NFT. Let's check the NFT ID. So we'll say let NFT ID is going to equal 1. That's the real estate ID that gets generated whenever we call the mint function inside of here. So whenever we mint from scratch, it's going to go ahead and create a new NFT with the ID of 1. Okay, and then it's going to owner of NFT ID, which is this, which is 1, to equal, and then we'll say seller address. Okay, so seller here is a signer with Ether. So if you want to get the actual Ethereum address, you have to call .address. You can't just do .seller. You have to do .address. Okay. So let's just see if that works. It may not pass, but let's just try it. So let's say NPX HARDHAT test. And instead of running the entire test suite, let's actually pass in the test file we want to. We want to say test realestate.js. And this might fail on us, but let's just give it a try. Okay. So we have multiple license identifiers. It's in real estate. Let's just take it out. Maybe I did it twice. I think it did it at the bottom of the file with the other contract. So let's just try again here. All right, so we got a new error, which is good. Cannot read properties undefined or equal. Okay, let me just fix that. All right, so I see what my problem is. Basically, I need to change my parentheses. So expect this function call here. Actually, I put the entire thing inside the expect function. So expect this right here, which is supposed to be inside the expect function, and then expect to equal seller address. So let's run that again, see if it passes. Obviously, I did it off camera, but there you go. Boom, it passes. Awesome. So it sends an NFT to the seller. So the seller has the NFT before we do the sale and before we start developing out any type of escrow. So again, we have an escrow contract now. It's technically deployed, but it doesn't do anything. It just has an empty function inside of it. Let's start actually coding it out to facilitate the transfer of the sale. So we need some prerequisites in order to do this. Okay, we're going to create a constructor function that stores some information like the NFT address, okay, and then allows us to actually move the NFT. So basically, we need to do a constructor like this. We'll say, constructor, okay, and then we're going to pass in some arguments here. And the first thing we want to do is track the NFT address and the NFT ID. So we'll say address, NFT address, and then uint, we'll say 256. So I do this for uint sometimes. 256 is the standard. Sometimes I'll write out long ways. So uint and uint 256 are the same thing. Let's say NFT ID. Okay. And then so let's save those in a state variable here. We're going to say address public NFT address, and then uint 256 public NFT ID. All right. And then we'll say NFT address equals NFT address, and then NFT ID equals NFT. All right. So that's going to allow us, then we need to update this constructor, this escrow to update that. So we're going to pass in the NFT address, then NFT ID. All right. So let's save that. And then let's just make sure it still works. Let's run our test. Still deploy the contract successfully. All right, so NFT address is not defined. We want to do real estate address. Sorry. That reads the address off of this smart contract right here after it's been deployed. Okay, awesome. So it's still working. We're not really checking for this necessarily inside of our, deployment here. We're just saying that it still works. Like our test still passed. This still compiles properly. It still puts the contract in the blockchain because the test suite wouldn't run if this failed here. So I'm not going to do an insanely robust test suite for this particular example. I'm just going to kind of get it working to show you the happy path or how the sale will actually take place, and then show you how you can speed up your development by doing automated tests rather than having to hand check everything inside Remix. You could do more sophisticated unit tests later on. We're just going to get it working and show you how that contract works. So anyways, how would you finalize a sale? So we have the NFT address, we have the NFT ID. These are both critical pieces of information in order to facilitate the transfer. So one thing you could do is basically import the entire, token. You can import files like this. We could say import, /real estate. Okay. And then we could basically create a new contract instance for real estate inside of here and give it the address and the ID, because if you know the smart contract code and then you know the address, you can talk to it on the blockchain. Okay. So I'm going to use a different strategy. Okay. I'm going to show you how to use smart contract interfaces. So you can code out smart contract interfaces in your code explicitly like this. We can say interface, say ERC721. And what an interface is really just a skeleton of the smart contract that shows like what the function is without actually importing the entire function itself. So basically we can say interface ERC721. So this is a ERC721 token with the interface, hence the I prefix. And then we can just import the functions that we care about. So in this case, all we care about is the transfer from function, which lets somebody else, like a marketplace or a different smart contract, move tokens out of somebody's wallet into somebody else's. So ERC721 has multiple ways to move tokens around. Okay, you can see like it's got this transfer function. Okay, where you can, it's always transfer from. Sorry, I get confused sometimes with ERC721 and ERC20. It always uses a transfer from function. Okay, it's just sort of standard. So yeah, basically that's how it works. And you can do that from your own account or somebody else's. But if you do it from somebody else's account, they have to call approve first, okay, before they actually facilitate the transfer, because you can't just call a function to move some tokens out of somebody's wallet unless they've called approve, which we'll see here in a minute. So anyways, we just care about this transfer from function, which is going to let this smart contract take the tokens out of the seller's wallet, okay, and then move it to the buyer's wallet. So how do we do that? Well, we can do a NFT transfer like this. We can say ERC721. We can pass in the NFT address. Okay, and then we can say transfer from. And this takes 3 arguments, as we can see here: the from address, the to address, and then the token ID. Okay, so the from address, we'll just say seller. We don't have the seller yet. We're just going to pass in as a placeholder. This is just a placeholder. I'm going to change this. And then the buyer is also a placeholder. I'm going to change this. And then the NFT ID is we have that already. That's this NFT ID. So NFT ID. All right. And that'll do the transfer. So that's how we get access to the NFT. We use this interface to say, hey, there's a smart contract out there that has a transfer from function. Let's create an instance of that smart contract by giving it the address, which we've stored here. And then we're going to call transfer from on that smart contract, which we defined here. We say, hey, it takes these arguments, who it's going from, who it's going to, and the token ID. And we have that here. But now let's actually access the buyer and the seller. So we can add those to the constructor function. Okay, we can say, let's just do address. And we'll make this payable. Payable. Buyer. Address. Let's just do seller first. Payable. Buyer. So we can also break these up on Solidity like this. We can read them better. All right. And so we can store those here. We can basically say address payable seller and address payable buyer. So address is just an address and Solidity of a user, okay, in this case. And payable means that they can actually receive Ether funds. So Ethereum cryptocurrency or Ether can be sent to this address because it's now payable. All right. So now we need to set these here. Say seller equals seller. And then buyer equals buyer. Okay, we do finalize sell. So let's create, we got a seller here. Now we need to create an account for the buyer. We can just say buyer equal to accounts 1. All right, seller and then buyer. And so now what we can do is basically say describe. So instead of this, let's do a new file here, or new block. Say selling real estate. And we can say it executes a successful transaction. And we're going to do several things to check inside of here. But at the end of the day, what we want to do is basically, first we want to check that the seller is the owner before the sale. So we'll do that like this. So, we've got this already. So we'll do it again here. We'll say expects seller to be NFT owner before the sale. And then we want to execute the sale. We want to say finalize the sale. So we can do that like this. Basically, we'd say transaction equals await escrow, and then we do connect. So basically, this is going to allow us to act as the buyer whenever we connect to the smart contract in JavaScript. So, with our last example, we were just calling everything on the contract, directly because it was assumed that we were the same address every time. But if we want to specify which address we are, we want to say, use the contract name and then say connect to this Ethers.js signer, which is the buyer in this case, and with the buyer to finalize the sale. Okay. And so we'll do transaction wait. We'll console log the buyer finalizes the sale. Okay. And then now we want to expect that the buyer is the owner of the NFT. Expect that the buyer, NFT owner, let me just change this, owner after the sale. Real estate owner of ID 1 to equal buyer address. Okay. So now I'm going to do this and it's going to fail. I don't know why it's going to fail, but I want to demonstrate it. Let's hope it fails for the right reason. Okay, so there's a compilation error. Let's fix that. That's not the reason I was hoping for. I think I forgot the semicolon here. Yeah, so on line 29, needs a semicolon at the end of every line. Okay, so I forgot to pass in these here. Sorry. Let's fix a couple things. So we need to actually pass in the seller address and then the buyer address. All right. Okay, awesome. Well, let's just see. There's a couple other things that need to go wrong. All right, so I need to update this. I make this mistake all the time when I'm writing tests. Basically, we need to call .address here. We're passing in the actual, actual things. All right, so now we fixed the errors in our tests, but now we get the error that I was expecting. Okay, so I expect this to error, and this is the exact error that we got. So you can read the error message. So ERC721, transfer caller is not owner nor approved. So like I was saying before, if somebody else is going to call transfer from on your behalf, then you, as the NFT owner, must call approve first. So the first step we need to do in order for this escrow contract to actually facilitate the transfer of the NFT out of the seller wallet into the buyer wallet, the seller must call approve before that transfer can happen. So like right now, the smart contract's trying to take money, essentially, or trying to take value, I should say, because an NFT is not really money, but trying to take an NFT out of the wallet when the seller hasn't approved that transaction yet. So basically, here in the last step in the before function, okay, before each, we're going to do this. Seller approves the NFT. So we're going to say transaction equals await, real estate, connect, seller. That's the connect that I was showing you a second ago. We want to connect the real estate smart contract, the NFT, as the seller, and we want to approve, call the approve function. We want to approve the escrow address to spend our NFT, which is NFT ID, which I believe should be capitalized here. Let's just do that. NFT ID. And we'll say await transaction wait. And then we can run the test, and hopefully this should pass. Let's just try it again. Boom. Awesome. So it executes a successful transaction. It moves the NFT from one account to another. So that is the core functionality of the entire thing, is moving an NFT from one account to another. Now it's very simple. We don't have all the behavior that we want. Okay, we want to actually add all this stuff where the buyer has to fund the deal, the lender has to fund the deal. We have to go through all these inspections. Okay, there's lots of different things we have to do, but that's just the initial functionality, and you can kind of see how I like to develop smart contracts with tests. Like get the basics working and then add all the complexity, and you can always save your progress. So if something breaks along the way, you can basically just go fix things one by one. Like you commit this to source code or source control, and then go back if you had any problems. So let's go ahead and make this contract a little more robust. So let's go ahead and add some other variables. Let's go ahead and build out the constructor function. So what I'm going to do is, instead of just tracking these things that we needed for the initial transfer, let's go ahead and load up the constructor with other stuff. We're going to say purchase price. Let's just add the variables here. Then we'll add them one by one. Okay. So at the top, we're gonna fill these out: NFT address, NFT ID, seller, buyer. Below NFT ID, let's say uint 256, public purchase price, and then uint 56 public escrow amount. Okay, so this is the amount the property is going to sell for. This is the amount that the buyer must put down to put this in escrow. All right, and then the seller address, the buyer address, and then we're going to say address public lender. And above that, I'll say address public inspector. Okay. So that should be all the actors that we need for this use case. So here's the scenario. Well, actually, let's go ahead and fill these out. So just below here, we'll say, uint, this uint 256, purchase price, uint 256, escrow amount. All right, and then we've got the seller, we've got the buyer, we got inspector, address, lender. Okay, and then we set these things here. And then escrow amount. And then inspector. And lender. Okay. All right, so let's now add these items here to our test. So let's just say this. Let's add the inspector and the lender. Okay. And then we'll add this here. Lender to address. Okay. And then now let's talk about the purchase price. So let's make the purchase price, let's just do everything in Ether. So Ethereum, cryptocurrency, or Ether. We'll just say the purchase price is 100 Ether. We'll just do that for simple math because our HARDHAT accounts automatically have 10,000 Ether in them. Okay. And so let's just say 100 Ether. I know there's not many houses that you're not going to buy a luxury penthouse in New York City for 100 Ether. I get that part, but let's just use it for simple math. And then we'll say the escrow amount is like let's just say it's a 20% down payment. Now I know this. So first of all, what I want to also model is like this is not going to be a perfect smart contract to facilitate a real estate transaction. It's not going to be airtight. It's not going to be exactly how a real estate transaction happens. Like we'll probably just, deposit a down payment as earnest, right? I know that's not typically what you do. You don't front the down payment until you actually do the closing. I get that part. But some things will be approximate inside of here, but this just shows you sort of what would happen in a real estate transaction, how you could model that with NFTs and also smart contracts, and you could code out a more airtight one as an exercise if you want to, or build your own project. So if we're going to do the Ether amount, we can basically say pass in the Ethers. I'm going to use, whenever we store Ether inside the smart contract, we store it in way value. So, if we wanted to be 100 Ether, we don't just pass in 100, okay? We want to do 100 followed by 18 decimal places because way is the amount of, we don't store decimal places in smart contracts, and Ether is divisible by 18 decimal places. So we store it as a whole number. When we add 18 zeros, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. And that's what 100 Ether looks like at the smart contract level. And then when you pull it out, you convert it to decimal places, and then you convert it back to 100 Ether. So there's a shortcut inside Ethers. Okay, it's called, we can do this. We can say Ethers, utils, parse units, 100, and we can say Ether, and it's going to convert that for us, okay? But I also like to essentially have this in a special function that I can do in my tests. So I'll put it up here, and I'll use a tokens function, and I'll just put that inside the function so I can call tokens over and over again. And sometimes I'll do a const Ether equals tokens. And so if I want to convert tokens to decimals or Ether decimals, I'll just quickly have this available, and then I can basically do this. I can say Ether 100. Okay, that's going to be the purchase price. And then for the escrow amount, let's just say it's 20% down. I realize that earnest money or escrow is usually a much smaller amount, but let's just pretend it's the down payment. So we'll say Ether 20. So it'll be 20% down payment for the escrow. Okay. Again, I realize it's not exactly how a real estate transaction happens, but this will be approximation just to show that how you can model this as smart contracts. So Ether 100, Ether 20. And now let's go ahead and see if we can still run the test. Let's just still see if it passes or if we messed anything up. Nope, still passes. Awesome. So we have updated the smart contract to include all these variables. We're successfully putting the smart contract on the blockchain with these new settings. And so let's continue building out this successful transaction. Okay, so let's find a way to check the escrow balance, all right, while we're doing the transaction. So basically, let's add a function here to get the balance. Okay, so below finalized sale, we'll create a function down here. Well, actually, first of all, before we do that, let's do the first. Let's do the first step in the transaction, which is basically if a buyer wants to put a property under contract, they need to deposit some earnest money. In this case, we're just going to make it the down payment. Again, it's not really going to be airtight, right? Like, this should really be a separate step. Let's just say the down payment is the earnest money. So we're going to take that 20 Ether, okay, that we did here, okay, and we're gonna create a function that lets the buyer basically put it under contract by depositing earnest. So essentially, we're going to say function deposit earnest, and we'll say public. And then what we want to do inside of here is basically take the ether, okay, and then save it in the smart contract. So essentially what the buyer's going to do when they take this down payment, they're going to send Ether or Ethereum cryptocurrency to the smart contract, and it's going to stay in escrow. Like the contract's going to own the cryptocurrency itself. And then whenever the sale takes place, it's going to take those funds and send them to the buyer in addition to the loan that's going to come from the lender later. We're going to add the down payment and add the remaining amount to the contract, and then send all the proceeds that came from two different sources, all right, to the seller, okay? So you can create a function inside of Solidity that actually lets somebody call the function and send in cryptocurrency at the same time by making the function payable. Okay, so this is a modifier that lets you send in Ethereum cryptocurrency or Ether with this function call, which we'll see in a second, which essentially when they call this function, they're going to call it, and then it's going to say, hey, how much Ether do you want to send in? And then we can basically, receive Ether into this smart contract, okay? And then we can do that like this. And we can also, when we can access that value with message value. Okay, so let's just leave it empty for now, or we can call it deposit earnest, okay? And then let's run the test like this. Well, let's check something else. Okay, so pull this over. Say buyer deposits earnest. And we can say transaction. Let's just do let transaction out here. Let's say let balance transaction. Transaction equals await escrow. Connect buyer deposit earnest. All right, and then we can basically say value, and we want to deposit the earnest amount. So instead of doing an Ether 100 here and Ether 20 here, what we're going to do is actually refactor these and then put them into our test here and say let purchase price equals Ether 100, and then say let escrow amount equals Ether 20. And then we're going to move this out, say purchase price, and then say escrow amount. And then we're going to say escrow amount here. So this calls the function and then uses the value to say how much Ether we're going to send in. So we're going to send in the escrow amount. Okay, we're connected with the buyer. We're from the buyer's account, call the deposit function, and because it's payable, we can send in value, and it's going to send the earnest money to the contract. So let's just see if that passes. All right, so it still works. So let's actually check the balance. Okay, so what we want to do is get the balance like this. Let's create a function that actually gets the balance directly from the smart contract. Let's say function get balance. It's public view returns uint, and we'll say return address this balance. So basically, this is literally referring to the smart contract, and then address takes it and converts it into an address and returns the balance in Solidity for the Ether address. Okay, so now we can basically let's just check the balance like this. We already set it here, and then let's just check the balance. Say check escrow balance, and we'll say balance equals 08 escrow get balance. All right, let's say console log. We'll say escrow balance, And then we're going to format it with ethers. ETHEREUM format ether. Okay, and then we'll actually say the balance. All right, so let's run that. Okay, awesome. So we're just logging the escrow balance, and we can prove that 20 ether was sent into the smart contract. Okay, so that it worked. We called deposit earnest money, and we sent in 20 ether, and now we've got it. So I want to add some requirements to this function. Okay, so first of all, I want to make sure that they sent in the right amount, because we don't want them to send in, you know, ether 10, right? Let's do that, because the function will still work, but the balance of the contract will only be 10. We want it to be 20 because that's the escrow amount that we specified in the smart contract constructor. We want to actually satisfy the terms of the contract. So how do we do that? Well, basically we can say require. So it requires a special function inside Solidity that must evaluate to true in order for the function to continue execution. All right, so it's a special function in Solidity, and basically you could say like 1 + 1. You say require, whatever's inside of here must return true, and if it returns false, then the function stops executing. But if it requires true, the function keeps going. So you could say, you know, 1 + 1 = 2. That's true. It'll keep working. But if you say 1 + 1 = 45, it's going to fail, and the function will stop working. So what we can do is basically say a message, a value, is greater than or equal to the escrow amount. Okay, so message is a global keyword in Solidity. It's a global variable in Solidity, and it has a value on message. And message value is the amount of cryptocurrency or ether that's sent in when this payable function is called. So what we're saying is whenever someone sends an ether with this function, take that amount and then make sure it's greater than the escrow amount, which we saved here whenever we create the smart contract. So now the functions have failed because we changed our test to only send in 10 ether. All right. Well, hold on. I didn't save it. Let's try it again. All right, so it's failing. Awesome. So let's go back to 20 and let's watch it pass. And I guess if you really wanted to, you could make sure that it's exactly equal to, but for our purposes, we're just going to say it's greater than or equal to. All right, so the other thing is we only want the buyer to, deposit the earnest money. Okay, so we could create a new requirement like this. We could say require message.sender. Okay, so message value is the amount of ether that's sent in, but message sender is the person who's calling the function. So we could just say require message sender is equal to only buyer. Okay, and then we could try to do it from, we could try to basically deposit earnest from the seller's perspective, and now it should fail. All right, it fails. And then I can also show you that we can add a reason string. We can say only buyer can call this function. And now if I run the test again, you should see that reason string in the exception. Boom, there you go. Only buyer can call this function. So the seller's doing it. So let's make it so that works. But let me show you the next thing. I don't really want to just put two requirements in here. I want to show you how to use function modifiers. So you can create something called a modifier like this in Solidity. You can say modifier and say only buyer. Okay, and then you can basically take this require function and then take it and put it here. And then you can say payable only buyer. And then now, I also do one more thing here, do underscore. All right. And now what's going to happen is whenever you call this deposit earnest, it's going to add this requirement to the beginning of the function and check it before it runs everything else. Okay, so we can still see the behavior is the same. All right, so only buyer can call this function. That's the reason. So this is really nice because that may you can add this to multiple functions if you want to without repeating yourself. And then it also cleans up your code quite a bit because you don't have extra function lines inside of here. Okay, this is a really common pattern when you're restricting who can access functions and who can't. So then this here, this underscore with a semicolon after it, it's just returning the function body. All right, so just basically execute the function after this. All right. So let's change this back to the buyer here. We're depositing Earnest. And then let's do this again. All right, awesome. So it still works. So now let's do a couple other things. Let's update our test to check the escrow balance before the buyer deposits Earnest. Okay, so we can just see what the status is before they deposit. So we can see it's 0, then they deposit, and then we can even say, like in the test, like say like, you know, buyer deposits Earnest, and we can, you know, make sure the transaction finishes. Okay, so escrow balance, buyer deposits Earnest money, escrow balance. You can watch basically the life cycle of the entire transaction just with the console logging statements. Okay, so now let's add the inspector into the equation. So what we want to do is basically go back to our thing here. We want to have an inspector who like checks out the property and says, yes, it's good to go or not. Now, I know it's more complicated than this. Like I know an inspector would submit an inspection report and there could be like a negotiation period if they find that there's something wrong with the property. Let's say that the HVAC need to be replaced, like the air conditioning unit, basically. They might come back and say, okay, well, we're going to, you know, reduce their purchase price by the amount of a new HVAC system or something like that. You could take this like to a great deal of complexity, but I'm just going to make it kind of simple for this example, just to show you how it works. And we're going to just essentially create a way for the inspector to update the inspection status. So we're going to create something in Solidity called a mapping. Okay. And so with this, well, actually, no, we're not going to do a mapping just yet. We're just going to create a variable that tracks the inspection status. So we're going to just right here. Actually, let's move this modifier above the constructor. Okay. And then below this modifier, we're going to create something called inspection passed. And by default, we'll say false. So this is going to be a state variable, which default is false. And say bool public inspection pass is false. And so a bool is just a Boolean value, which just means a value that's either true or false. And public's going to give us a function where we can fetch this out. And then inspection passed is going to be the status of the inspection. So let's create a function to update this. All right. Below deposit Earnest, we're going to say function update inspection status. Okay, and we're going to pass in bool passed, and then public. And essentially, we're saying inspection pass equals underscore inspection pass. Well, underscore passed. Okay. So that's going to take this value in, and then it's going to store it here. Okay. And then what we're going to do essentially is make only the inspector call it. So we have only buyer, and then we want to say only inspector. Okay. And then we can basically create a modifier that checks for only the inspector and say only inspector. Say only inspector. Can call this function. All right, we'll save that, and then we'll go over and try it in our test. And so here we're going to call the function. We're going to say, inspector update status. And then we'll basically just say, transaction equals await. escrow connect inspector. So update inspection status is true. And then we'll just do this transaction wait inspector update status. Let's give ourselves some space here. Let's just make sure it still works. All right. See if the test pass. All right. So I had a typo in here. Let's just see how inspection pass. Okay. So only inspector can call this function. So I think I may have done the wrong address. So connect inspector, update inspection status. I think I forgot to change this. This should be inspector. All right. So we're seeing things happen in real time here. Okay. Awesome. It works. So now let's try to change it, the buyer or something. Demonstrate failure. Okay, and then inspector. Okay, awesome. So now the inspector has the ability to, approve the transaction. So what we want to do essentially is require that the inspection has passed before we finalize the sale and actually transfer the property ownership. Okay, so we're going to say require inspection pass. All right. And then we're going to run the test again. All right, still works. But let's actually take this part out and watch it fail. And we could say must pass inspection. I forgot to save it, sorry. Okay, so must pass inspection, that's why it failed. And then let's make it pass inspection and the test should pass. Again, you could write out more robust unit tests for this that code out really complex scenarios that say, hey, whenever this hasn't happened, check for a failure. But for now, I'm just kind of demonstrating it when I write out the test. So, all right, it has to pass inspection in order to facilitate the transaction. Now let's talk about approving it from the lender's perspective and also the buyer and the seller. So what we want to do is just basically create this thing called a mapping inside Solidity, which is a key value store. Basically, it takes an ID and then which corresponds to the key, and then a value, which is just the value. In this case, we're going to be of true or false. So we'll say mapping, all right, address, and we'll say bool, public approval. So what this is going to do is take an Ethereum address and then store whether the property has been approved or not from this person. So the key is an address and the value is the value here, a Boolean. So basically, we can save this on the blockchain by passing in the address of the lender, and basically we can say, hey, the lender, when they approve it, let's save their address as the key, and then when they approve it, we'll say true is the value. But by default, it's going to be false, okay? So if we check for the approval here and they haven't approved it yet, then it will fail, okay? So basically, we can require that each relevant person has approved the transaction and the sale like this, okay? So we can basically say, require approval. We can read it out of the mapping by passing in the address of the buyer. I'm going to take these reasons out for now. Let's just take it out to make it cleaner. You could add this as an exercise. You require approval seller, and then require approval lender. Okay, so let's try to run the function, and it's going to fail because we don't have approval from all those people. All right, and you could just say, you could add reason strings here. By, and then we can just copy these. Hold on, try it again. Okay. And say must pass inspection. All right, so it must be approved by buyer. So we can do that. And let's create a function to do that. Just below inspection status, let's say function approve sale, public, let's say approval, we'll say message sender equals true. So what it's going to do, it's going to write the mapping with message sender, which is of course the address is calling the function, and then assign it true. And then we'll say buyer approves sale. So transaction equals await escrow connect buyer approves sale. So it should fail again, but it should fail with a new error message. Okay, now it must be approved by seller. So it must have been approved by buyer. We got past that. We can say seller approves sale. All right, must be approved by lender. So now we can say lender approves sale. And then do that. Here's the lender. I'll just, if you want to pause the video, you can see all those. All right, now that passes. Okay, awesome. So now we have all the appropriate parties approving the sale. Now, what we want to do is make sure that we want to pay like right now, we're taking the NFT out of the seller's wallet and putting it into the buyer's wallet, right? That's going to do the sale. But we also want to take funds out of this smart contract and then put them into the seller's wallet. So the buyer should get the NFT, but the seller should get the funds. And right now, the buyer's deposited a down payment as earnest money. I know that's not really how it works in the real world, but let's just bear with me here. We got the down payment in the smart contract. Now we want the lender to send in the remaining 80% or 80 ether, which is going to be the loan amount. And then all those proceeds are going to go to the seller. Okay. So, first of all, before we can actually facilitate the transfer, let's make sure that the contract balance is enough. So we can say require address this balance is greater than or equal to the purchase price. All right. Say must have enough ether for sale. Okay, let's do the again. It should fail this time because the lender has not deposited funds into the smart contract. Okay, so must have enough ether for sale. So now before the lender approves the sale, let's actually send in ether to the smart contract. So we can do like this. We can say lender funds the sale. Say transaction equals await lender send transaction, and then say to escrow address, and then value ether 80. That's the remaining amount. So the purchase price is 100 ether. The buyer has deposited 20% down payment. The lender's funding 80% loan to value. So they send in 80 ether to the contract, and then it transfers. So this lender send transaction, this is just something that comes with Ethers.js to send ether from one account to another. And then you provide the transaction details, which is the recipient, which is the smart contract address for the escrow, and then the value, which is how much ether you want to send. This is 80 ether. Okay, so now we should, once the lender has sent in the funds and approved the sale, we should see something working here. But now let's just see here. Let's just try this again. Hold on. Oh, I see what's wrong. They're trying to send funds to the smart contract, but I can't do it yet. Okay. So why? So in order for a smart contract to receive funds, it has to have this thing called a receive function. So right here, we're going to say receive. Okay. And let's say external payable. So this is really just an empty function that lets the smart contract receive funds, and you could execute business logic inside of here that you want to do whenever somebody sends each of the smart contract. But by default, you shouldn't be able to do this in Solidity version 0.8 because we don't want somebody to accidentally send funds to a smart contract unless they explicitly want that to happen. So if you want the contract to just receive Ether, you have to have this receive function. If you want to add extra business logic inside of there whenever the Ether is received, you can do that. But for now, we're just going to leave it blank. All right, so now it works. Okay, awesome. So it has done that. So now what we want to do is let's just see here. The last thing we really want to do to make this work is transfer the funds to the buyer. Okay, so we can do that like this. We can basically say, I'm just going to put this in here, make it fast and explain it. All right, so we're going to say payable seller call. So call just sends a message from this smart contract to the seller. And then when we say call with value, basically we're going to take the entire balance of this smart contract, however much money's in here, and then send it to the seller with an empty message string. All it's going to do is just send Ether when we do it, calling a message. And it sends it to the seller from this smart contract, and then it returns the success value of that, and we will require that that was a successful transfer before we continue on, transferring the ownership. Okay, so let's just say that, make sure that the test still passes. Okay, and then let's we finalize the sale. We've expected the buyer to be the NFT owner. Okay, now what we should also do is expect the seller to receive the funds. Okay, so let's just check the seller balance here. Okay, we're not going to actually do a test yet. We're just going to console log it. Basically, we're just going to say await Ethers provider get balance. That's how you check the balance in Ethers. You just do Ethers provider get balance, the seller address, and then we're going to parse that and see what it is. So the seller balance is this. All right, so it looks like I didn't save the file properly, so I saved it and reran it, and here's what the seller balance is. So the seller received 100 Ether, right? So it's really hard to be specific in exactly how much Ether they're going to have, because they have to pay gas fees and they have to do some transactions, and they start out with like 10,000 Ether, so it's hard to figure out exactly how much they're going to have, because if you change this code, the gas cost might change, blah, 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 blah. So what we're going to do is just see that it's greater than a certain amount. So you can do that like this. Basically, we're just going to say, expect balance, which of the seller here to be above. So that's what you can do with chai, and say Ether. So this much, okay? So it should be above this much, which basically assures that they received 100 Ether. Okay, awesome. It works. Now, that's a complete smart contract that models this real estate transaction. Now, this is not a complete, airtight solution. Of course, this is just an example of how you could use NFTs to model real estate and facilitate a, transfer process from one account to another, okay? Well, you could also do things like cancel the sale. All right. So what happens if, a buyer got in there and wanted to cancel? I can add some hints inside of there, of what to do. So for finalized sale, you can do something like cancel sale, where you could say if the inspection's passed, then, the buyer gets the money, or, this seller gets the money if the inspection's passed. You can handle edge cases. You can add a lot of tests inside of there. But that's just something to get you started. And you get this benefit of seeing how smart contracts talk to one another, how to use libraries, how to use interfaces, how to use payable functions, modifiers. You learn a lot about Solidity throughout this process. So I'll stop this section here at that, and let's move on to the next one. All right, so now let's get into coding out a real-world DeFi example with flash loans. Okay, so what are flash loans? Well, basically, this is a technique where, as a developer, you can borrow millions of dollars in cryptocurrency with zero money down as long as you pay it back in the same transaction. And, why would you want to do that? Well, people do this all the time for things like arbitrage trading on cryptocurrency exchanges. Okay. So I'll show you an example of what, a flash loan transaction might look like. You might have a flash loan provider here, it's this flash loan pool that holds some cryptocurrency tokens in it. And then basically you can create your own smart contract that takes out those flash loans and buys cryptocurrency on one exchange and sells it on a different exchange for a profit, and then returns the funds back to the flash loan pool, and then you pocket the difference. So I'll show you an example. Like, Aave is an application that provides flash loans on their platform. Okay. And so what does Aave do? So Aave is a money market account. It's a savings and lending application where it's kind of like a bank where you can deposit cryptocurrency on one side and take out loans on the other. That's their primary function, but they also essentially let you take out flash loans for a small fee. Okay. So what you can do here, how this works is you have a smart contract called a liquidity pool, and you have all these people who are providing funds to make Aave work, who are earning passive income whenever they deposit cryptocurrency into this pool. And this pool can be repurposed to take out flash loans where you have access to all this money for an instant on the blockchain, and then you can do stuff with it. As long as you pay back the final amount in the same transaction, then the transaction will succeed. And if it doesn't succeed, then it'll fail. Okay, so here's the flash loan pool. This is powered by the application where you can take out flash loans. And then here's a token contract. So we're going to do this with ERC20 tokens. So ERC20 tokens, ERC20 is just a standard that describes how, cryptocurrencies should work that are powered by smart contracts on Ethereum so that they are compatible in DeFi, in wallets, on exchanges, all that type of stuff. We looked at the ERC721 standard in the last video, but we're going to use the ERC20 standard in this video for fungible tokens. All right. Yeah, you can see examples here, like transfer is how you send tokens. You have to approve tokens before you can send them. Name, symbol, decimals, all that type of stuff. We'll revisit this whenever we are actually interacting with the tokens for the flash loans themselves. So we'll have a token smart contract. We'll have a flash loan pool smart contract. And then in order to do flash loans, we have to code out multiple steps. All right. And the only way to do a flash loan successfully is to create your own smart contracts that orchestrates the borrowing of the funds and then paying them back, and then also the other stuff that you want to do, because that's a requirement of flash loans, is that you have to pay back in the same transaction. And the only way that you can do that is to create your own custom smart contract with a function call with multiple steps, like step 1, borrow the money. Step 2, do this arbitrage. Step 3, pay the money back to the contract with the tokens. Okay. So, and the developer will have control of this entire smart contract the entire time. So, you can get on Aave and look at how they do flash loans. Like, you can literally just go through their documentation, okay, to see how to code one out for your smart contract. But for honestly, most people who are getting started, this is going to be a little bit advanced. We cover flash loans in depth inside this flash loan masterclass. So I train about masterclass inside the blockchain bootcamp. If you want to check that out, definitely do that. But I think the best way to get started, just to learn it in and out, is actually to code out a flash loan pool yourself, and then your actual smart contract that can take out flash loans like this to see how it works before you start adding on the complexity of doing it with their documentation. Because at the end of the day, what you want to have are coding skills as a developer where you can create your own custom strategies. And if you can't do this basic task first, you're probably not going to be able to do real flash loans. So let's actually get a token contract. We're going to code out our own flash loan with the flash loan pool, and then we're going to code out the borrower contract and then actually do a flash loan on our computer. And you'll see how that works, that you can start coding out these arbitrage strategies or whatever you want to do, like DeFi liquidations, et cetera, et cetera. So let's jump in and get started. Let's go into our project here, okay? And let's kind of reset, clear to neutral, and go to the contracts. And we're going to create a new file for the token. So new file, say capital T token.sol. All right, so I don't want to go through and code out a token step by step right now. I think that's the best use of our time. I want to focus on the flash loans. So we're going to go to GitHub, all right? And we are going to look at the Solidity tutorial, go to contracts, and then go to token. And then we're going to click raw. All right. copy this, and we're going to paste in token. So this is a complete ERC20 token, okay? That'll work. It's got all the functions like a transfer, approve, okay? All right. And then next what we're going to do is create a new contract for the flash loan. We'll call this flash loan. That's all. A new file relative to current view. And we'll call this next one flash loan receiver, RECEIVER, SOL. Okay. And so inside of this, we'll copy let's take this out. We'll just copy this stuff. Call this flash loan receiver. Okay. And then do flash loan. Okay. And then we'll create a test for the flash loan as well. So we'll copy the real estate. We'll say flash loan. That is SOL. Sorry. Do.js. I'm full of typos today. Guess we're going to write stuff in Haskell. There we go. Awesome. Now it's in JavaScript. So let's take the skeleton from the real estate contract. Let's just take the essentials. Let's put this over here. And for the flash loan test, let's import update my syntax highlighting. Expect. We're going to import expect and ethers, and then we're also going to basically import our helpers that we created in the last section. So definitely go check that out if you haven't already. I'm not going to re-explain everything. Try to make this tutorial series kind of cumulative. And then we're going to say describe flash loan. All right. And then basically we're going to have it before each. Okay. And then we're going to say describe deployment. Okay. We'll add some examples in here. Say it works for now. And we'll just say, that's kind of lame, but just say expect true, or say like 1 plus 2 equal 2. All right, now it's kind of stupid, but let's just get the test suite set up. So I don't want to run the entire test suite, so let's run flash loan. Okay, so not exactly sure why. Let's just see here. All right, so I had a little error from the last section. For some reason, I had a variable name that had too many S's. I think I saved the file and accidentally edited a file from the last tutorial. So anyways, going back here, we got the flash loan receiver, the flash loan, we got basic test. Let's run the actual test, npx HARDHAT test, so test / flash loan.js. Okay. And then, all right, so our tests are passing. There's not really going on, but we have a heartbeat test for the test. So let's deploy the contracts. So we're going to deploy the flash loan contract. We're going to say, const flash loan. Just collapse our file browser here. Flash loan is equal to wait ethers contract factory get flash loan. Okay. We're going to say flash loan receiver, await ethers get contract factory flash loan receiver. And then also token is equal to token equals await ethers get contract factory token. Okay. So we'll just say this is load accounts. And if you skipped ahead to the flash loan section without watching the previous sections because you wanted to learn about flash loans, definitely go check out the previous sections because I'm not going to re-explain everything that I did in the previous sections because I want to do this for the sake of time for everybody who watched this tutorial cumulatively. So let's just run the test again, make sure we're all good. It actually imports the contracts. Okay, so we got an issue here. This needs to be async. All right, it works. And then let's set up the accounts. So we'll say set up accounts. And we want to save the deployer, basically. So accounts equals await ethers get signers, and then deployer is the accounts 0. Okay, so now what we want to do is actually deploy the token to the blockchain itself. Okay, so we can see token.sol. This token has a name, symbol, and decimals, okay? And we can set the name, symbol, and total supply in the constructor function. Basically, it's when we create a new token, we can say what we want the name to be, what we want the symbol to be, and what we want the total supply to be. So what we're going to do is create a new token called the Dapp token. That's sort of the canonical fake cryptocurrency that I use for most of my tutorials. It's like the Dapp University token, basically. So basically, we'll do that like this. We'll say token equals await token.deploy. And we'll say Dapp University. And then I'll say Dapp. And I'll say 1 million. 1, 2, 3, 4, 5, 6. We're going to deploy 1 million tokens. And it will create 1 million tokens whenever we put it on the blockchain. And it will assign them to the deployer. Okay. So, yeah, that'll deploy the tokens. Let's just do it. Let's make sure it still works. Okay. And next we can deploy the flash loan pool. And what we want the flash loan pool to do, first and foremost, is store the token address. So basically, we can create a constructor inside of here. Address, token address, public. And we want to make sure, let's just save the token. Say token, public token. All right. And then we want to say token equals token dot token address. Okay. And then we want to import the token as well. So just above this, we'll say import dot / token. That's all. So it's going to take token out of the current directory and import it into flash loan, and then save the token address into the contract like this. So we can save a contract like this. Okay, so now what we want to do is deploy the flash loan pool. We'll say deploy token. And then we'll say deploy pool, deploy flash loan pool. Okay. Say flash loan equals await flash loan deploy token address. All right. So let's just do that, make sure it works. Okay. Still working here. All right, we don't really need public on this. Let's just take it off. All right, works. So now what we want to do is actually transfer some tokens to the pool. So the whole idea is we've created this token and we've created a flash loan pool that's going to let us do flash loans. And now what we want to do is create a smart contract that's going to borrow money out of here. But initially, we want to take all the tokens we just created and send them to the flash loan pool. Okay. So initially, this developer is a deployer. He's the same person in the test example. But he already owns all the tokens. He or she already owns all the tokens. And they are going to essentially transfer tokens from their wallet to the flash loan pool. So that's going to be yeah, they're going to do that. So they're going to deposit tokens into the pool. So what we're going to do is actually create a special function to deposit the tokens. Now, we're going to do this with a special function, okay? Before I get any further, I meant to mention this at the beginning, but I'm going to make it very explicit now so that everybody knows exactly where I'm getting inspiration for this contract from. I want to give full credit where credit is due. So this particular simple flash loan example, this particular simple flash loan example, I am getting, I'm referencing the original implementation from Damn Vulnerable DeFi. Okay, so I've covered this on my channel several times. It's a great resource for learning how to hack smart contracts and do security. And they have some examples on here on how you can do, like flash loan attacks and things like that. So we are going to essentially use great inspiration from their contract. We're not going to be the exact same code. We're going to change some things so that you can see it. We're going to write our own tests. We do a lot of our own custom work, but we are getting inspiration from the original contract from this project. So I will put a link to this inside of the tutorial code so you know exactly where this is, where we're kind of getting inspiration from, and full credit where credit is due, because that team's done a great job of providing some great examples for us. But we're going to code out our own version of it, okay, step by step. And we're going to use our own special token, okay? We're going to add some of our own customizations and write our own tests, but you're going to learn how flash loans work inside and out by doing it step by step. That's the value add here with some slight modifications. So, anyways, just want to call that out, be 100% clear, so in case anybody's like, hey, this looks familiar. It's very heavily inspired by the Damn Vulnerable DeFi stuff. So let's go ahead and add that to the flash loan receiver as well. I'm going to add this to the top so everybody knows exactly where we're coming from. Let's make this a little cleaner to read. Okay, awesome. So let's talk about how to deposit tokens. So what we're going to do essentially is create a function here called deposit tokens. Function deposit tokens. And say uint 256 amount, say external. Okay. And then what we want to do here is essentially take tokens out of the person's wallet and put them into the pool. So we're going to get our token here. Say token transfer from, and say message.sender, then address this, and then amount. Okay. So let me explain what this is. So again, ERC20 tokens have a function, okay, called transfer from, which is like the NFT we saw in the last section, which lets us take tokens out of any arbitrary address and send it to any arbitrary address for any arbitrary value. Now, in order for this to be successful, somebody else is spending your tokens on your behalf. You must call the approve function as the token owner first. So, if the token creator is going to deposit tokens into this pool, they must first and foremost approve the tokens before they deposit them. Okay, but this is the basic functionality that's going to let somebody put tokens into the pool. All right. So let's go ahead and do that. Essentially, we'll go here. We're going to deposit tokens into the pool. We'll say transaction equals await flash loan, connect, employer, deposit tokens. And then let's pass in, let's use our tokens helper, and let's do all the tokens. So we'll do 1,000,000. Okay. And then let's say, we'll just say let transaction. And we'll do await transaction wait. Okay. It's going to fail. Okay. So we want to approve the tokens first. So let's do that, because you can't you can't do a transfer from without proving it first. So basically, we'll add some comments here. Let's say deposit tokens in the pool. But we also want to call approve first. Say approve tokens before depositing. So we'll say transaction, make token connect deployer, approve flash loan address. That's the address of the smart contract for the flash loan pool, tokens, and then, 1 million tokens, and then we'll deposit. Now, hopefully that'll work. Okay. And now let's actually check for it. So now we want to do is check that instead of checking for 1 + 1 is equal to, let's say expect, say await token dot balance of. This is how we check the balance of the pool. So we say flash loan address, and we say to equal tokens 1 million. All right. Now let's see if the, okay, so I got a little problem here. I think I just had a little issue. Let's just fix that. Okay, there we go. So that passes. Okay, so of course we need to call async here, my fault. And then we also want to, update this, and it just works, but let's do this. Sends token to the flash loan pool contract. Let's try that again. Hopefully we fixed everything here. All right. Yeah, awesome. So it sends tokens to the flash loan pool contract. We verify that we now have funds in here to borrow, because that's the first thing we want to do is make sure that, make sure we have money to actually do a flash loan with. So the first thing is depositing tokens into the pool. Okay. So first of all, let's add some extra stuff here. Let's add a requirement. Just say we require that the amount is greater than 0, that they must deposit at least 1 token whenever they're depositing funds. Okay. So we can run our test, make sure it still passes. You could, as an exercise, code out test to check for this specific thing. Let's do amount underscore here. But for now, we're just gonna test the simple solution. Okay, and then also, whenever we are doing the constructor function, we can leave that out for now. This would be good enough for now. Okay. So the next thing we want to do inside deposit tokens is track the pool balance. So we can add a state variable here. Okay, we can say below token. We can say unsigned integer 256 public pool balance. Okay, and then we can say pool balance equals pool add, and then amount. Now, what I want to do with add is I want to use a library called SafeMath. So we talked about OpenZeppelin before. Okay, OpenZeppelin's a library that we use to, create NFTs, right, from scratch, or other Solidity libraries off the shelf. But OpenZeppelin also has a library that's really helpful called SafeMath that will help us do math safely inside of Solidity, protect from overflow and common math errors that you get with Solidity smart contracts. So we can import the OpenZeppelin SafeMath library like this, okay? And then we can, at the top of our file, basically say, using SafeMath for uint 256. So on any unsigned integer 256 bits in a uint, we can have the SafeMath functions, and that's what we're going to do here with add. So let's just do our test again, make sure it still works. Okay, so I'm going to do underscore amount here. All right, so it still works. Awesome. So now let's actually get into the behavior of coding out the flash loan. Okay, so what we're going to do here is we're going to say function flash loan, and we're going to say uint 256 borrow amount. It's external. Okay, and we're actually going to code out the flash loan inside of here. in a second. But for now, we're just going to create a placeholder for that function. Okay. So we'll do that. And then now in the, we need to go ahead and deploy the other smart contract. So we want to set, so in order to do the flash loan, we need somebody to take it out. And so in order to write that test, we need to actually go inside of here and create this borrower contract that's going to take out the flash loans. We have all these 3 contracts in the network. This one has all the behavior it needs. This one has some of the behavior, but now we need to code this contract that actually takes out the loan. So that's what we have here, flash loan receiver, but doesn't do anything yet. All right. So we need to put it on the network. So in the last line of our deployment steps, we'll say deploy flash loan receiver. Okay. And then we'll say basically, let's save some of these contracts as variables here. So, here, let's do let token flash loan receiver, let deployer. Okay. And then let's do lowercase flash loan receiver equals await flash loan receiver deploy. And what we want to do is actually save the address of the flash loan contract. So that's the first thing we'll do inside the flash loan receiver constructor function. We'll basically say constructor and say address, and we'll say pool address public. We don't need public. And we'll say pool. And we want to basically import the flash loan. Okay. And we want to say flash loan and then pool address. Okay. And then we want to store the flash loan here. And then we also want to go ahead and create the owner of the smart contract with the address of the person who deployed the contract. Say owner equals message.sender. So what we want to do is say that only the developer who created the smart contract can call these special functions, because it's going to be like their special trading contract or something like that. And we don't want somebody else to take flash loans on our behalf. So message sender, of course, is the person who called this function. So the developer who created it and put it on the network, we're going to track that with message sender. We're going to save their address as the owner inside the smart contract like this. And then we'll save the smart contract for the flash loan pool here inside pool. Okay. And so what we're going to do is, well, first let's just do that. Let's just put the contract on the network. But we need to deploy it with the flash loan address and the constructor function. Okay. That's Sol. Sorry. All right, so it's still working. So now let's describe borrowing funds. Borrowing funds. Okay, so we'll say it borrows funds from the pool. Sync. All right. And then basically right here, we'll say let amount equals tokens 100. Okay. And then, well, let's not do that just yet. Let's just do, let's create a function to actually take out the flash loan first, because we got to figure out what function we want to call. So we have, the flash loan placeholder function inside of the flash loan contract, the flash loan pool. And then we have the flash loan receiver with no, we have to create the ability to call this flash loan function, and we're going to code out the logic for it, but we need somebody else to call it because we can't really call it externally with the regular address. It has to be called from another smart contract in order to work. So we're going to say, we're going to have a function here called execute flash loan. Okay, and we're going to say uint amount. This is the amount of tokens you want to borrow. It's external. All right, and then inside of here, we basically want to say pool. So that's the pool address. You want to say flash loan, and then the amount. All right, and then now it's going to call this flash loan function, the borrow amount. And what I'm going to do is we use this HARDHAT console logging statement. So HARDHAT lets you do console log inside Solidity. So we can do console.log, say borrow amount. So we can see what's actually getting passed down to this. So this is just going to test that everything's talking to one another. So essentially we can just say let amount equals tokens 100. When we can see you know, let transaction equals await flash loan receiver connect deployer, execute flash loan, and then pass in the amount here. And then we can wait for that to finish. Okay. So let's just see if it works. It's not actual flash loan yet. We're just seeing the functions work. Okay, awesome. So they're talking to one another, all right? And you can see that our console log is working inside Solidity, so we can actually pass in the amount that's getting passed through each function. And we're seeing the amount of tokens that are actually getting passed around right here. So everything's talking to one another. It doesn't work yet, but it's wired up. So let's take out this console logging statement and then actually work on the flash loan functionality. But really quickly, one more thing I want to do is make sure that only the owner can call this function. Okay, so inside of the flash loan receiver, let's say require message sender is equal to the owner. So only owner can execute flash loan. All right. So we'll save that and then do this. All right. So if we did it with some other account, it would fail. I'll let you test it out as an exercise, but we do want to restrict who can call this function. Okay. So now let's actually start coding out the flash loan functionality. All right. So the heart and soul of the flash loan functionality, right, is going to be basically send tokens to receiver. Okay. And then get paid back, and then ensure loan paid back. Because basically that's how it works. You loan them the money, that's sending tokens to receiver, and then getting paid back is the sender basically sending you the money back, and then ensure the loan paid back. So, basically what we can do, let's work on this one piece at a time. Let's talk about sending tokens to the receiver. Okay, so let's basically say token dot transfer was a message sender. So message sender in this case is actually going to be the flash loan receiver contract. Okay, and then we'll say borrow amount. All right, and so let's just do the test to make sure it still works. Okay. So right now we can actually check the balance of, right. So right now, like, we should see, I can't exactly console log the token balance inside the flash loan receiver because we don't have access to the token yet, but we could do that, right? So let's just do it. Let's demonstrate it. So let's import the token because we're going to need to use it anyway in a minute. Just above flash loan, we'll say import token.sol. And then inside of here, well, we'll come back to this in a minute. Like, it's received the tokens. Let's talk about how to get paid back. Okay. So, there's a two-step process in flash loans. So when you can send, like, well, how this works, let me just show my screen. It's kind of hard to explain. There's two contracts here. The developer, whenever they call the execute flash loan function, this contract is going to call a function on the flash loan pool to get the flash loan. And then the flash loan contract is going to call a function on the borrower to actually execute what happens whenever the flash loan takes place. Okay. So it's like a callback. So this calls a function on this contract, and then this function turns around and calls a function on this contract. So in order to actually do something with the money, and when you do it, like you're calling pool flash loan, the pool is going to call another function on your smart contract, like function receive tokens. All right, and then it's going to, this is where you do stuff with the money, and then, return funds to pool. Okay. This is where you receive the loan and do stuff with it and then pay the money back. And so what happens is, after it sends the tokens with transfer, it's going to, like, essentially, call this function like this. So you're going to say flash loan, but you need to call this receive tokens on the receiver. Okay. So now instead of just importing the receiver in here, we can have a generic receiver and say that all receivers must implement this interface. We talked about interfaces in the last section. Definitely go check out that if you haven't already. Again, if you just skipped ahead to look about how to do flash loans, make sure you watch the last couple of videos because they're going to explain everything that I'm not covering in depth in this section. So we can use an interface and say that anybody who takes a flash loan out of this smart contract must implement this receive tokens function, and it must accept two arguments, the token address and then the amount. Okay. And that must be an external function that we can call. So basically we're going to say, I receiver. Okay. And then we're going to say message sender, which is the contract who's calling the flash loan. Okay. Say receive tokens, and we're going to say address token. This is going to coerce the token state variable, which is currently a smart contract, to an address value itself. And then we're going to say the borrow amount. Okay. And then I'll just say use loan, get paid back. Kind of all in one go here. And the flash and receiver is going to actually have this function called. So it's going to accept a couple different arguments here. It's going to say address, token address, and then uint 56 amount. Okay. And so what we're going to do is just do console log with HARDHAT, because we've imported that into our thing here. We're going to log the, let's do this. Say amount. Let's just run our test and see if we've gotten this far. See if it passes. Okay, so it's working, right? So what's happening is, we've called flash loan, execute flash loan. It's called flash loan inside this contract to the flash loan pool, which is called this. It's sent tokens to the receiver, and now it's called the receiver's receive tokens function, which is its callback function, where it lets them actually do stuff with the money, and then they'll return the money to the pool. Okay, for right now, all we're doing is using console log with HARDHAT to show the values that are passed in. Let's actually get the, let's say token. Let's log our, let's do another console log here to see if we actually have the funds. Okay. So we can say console log, token, let's just do this. Token, we'll say token address, balance of, and we'll say amount. a balance of, address this. And let's just log that with HARDHAT. See what it says. And let's just make sure that we can actually read the balance inside the loan. Okay, so yeah, we actually have the funds here. So token address, balance of address this, all right, is equal to this. Okay. So now we have the money. We have the money. And so we could even have a requirement inside of here. We could say require token address balance of this is equal to the amount. And if it fails, you can say failed to get loan. Okay. So let's do that on the test again. Okay. Let's take out this console logging statement. All right. So now I want to do one more thing while we're in here just to prove that we have received the money. I want to create an event inside Solidity. So Solidity lets you emit events whenever you're, doing transactions inside smart contract functions. That's going to let you essentially see a transaction history from every time an event was created. But it's also going to let you, subscribe to events from external consumers so that you can get alerted when things happen. You can also test that things happen inside your contracts a lot more easily with events. So we're going to create an event inside Solidity like this. We'll say event loan received. Okay. And then we're going to give it some arguments. We'll say address token and then uint 256 amount. Okay. And then we'll just say we can emit the event like this. Emit loan received, token address, and then amount. Let's do the underscores here. Move this over. Say require. All right. And then we can test for the event inside of our HARDHAT test with special matchers like this. It's pretty cool. So we can say, await, expect transaction, which is this transaction here, to emit. It's pretty cool. Flash loan receiver, and then loan received. And we can also specify the arguments with args, token to address, and then amount. Let's do that. Let's run our test. Let's see if it works. Awesome. And then if we take the event off, if we comment it out, it should fail. Yep, fails. And turn the event back on, and it works. Okay. So another thing that we want to do when we receive these tokens is we want to add some constraints on this. So basically, we want to make sure that, let's just reorder this stuff or do stuff with the money here. Let's also make sure that only the pool can call this function. So basically we'll say require message.sender equals address of the pool. Say sender must be pool. So we don't want some random person to just call this receive tokens function. Okay. We only want the pool to do it. So we'll just run the test, make sure it still passes. Again, you can write some more sophisticated tests to isolate these use cases, but for now, we're just gonna do it with the happy path. Okay, so that's some more syntactic kind of things. So some more constraints we need to add. All right, so let's go back to the Flash loan contract, and add some more requirements here. So basically, let's add a basic requirement that require borrow amount is greater than 0. We don't only want, must borrow at least 1 token. Just because we must deposit at least 1 token, must also borrow at least 1 token. Okay, so now we want to, make sure that the balance, the whole point of the flash loan is so that when we send the money to the contract, that they pay us back, or else the transaction is unsuccessful. Okay, so we can track all that stuff inside the flash loan contract like this. Let's say uint 256 balance before is equal to token balance of address this. So we're just getting token, calling the balance of function, passing in the address of this smart contract. That's what this stands for. We're converting it to address. So balance before. And we want to make sure that you're not trying to borrow too many tokens. So we can say require balance before is greater than or equal to borrow amount. Say not enough tokens in pool. Okay, save this. All right, so borrow amount is underscored here. Okay, try it again. All right, still works. And then we want to make sure that the pool's working here. So we want to ensure that this works. So we'll say pool balance equals pool balance before. Okay, so that we're in sync. All right. And then we will say token transfer, message sender, borrow amount. Okay. Let's just make sure it's still working here. All right. And then now we want to add the final check, which is to ensure the loan is paid back. Because now we've added all these checks, but if they don't pay us back the money, okay, if they do stuff with the money and don't return funds to the pool, then it's kind of useless, right? There's no point in the flash loan. We've just sent them the money. It's just a flash, transfer. It's not a flash loan. So how do we get them to pay us back? Well, basically, they're going to have to implement the logic in the receive tokens function. All we're doing is saying, hey, you have to have this special function called receive tokens. And inside that receive token, you can do whatever you want to with the money, as long as you pay it back. Okay. So we'll send you the tokens. We'll call your receive tokens function. And inside that function, you have to pay us back because this is the final step. And then we finally just check to see if the loan was paid back here. So say uint 256 balance after equals token balance of address this. Okay. So we did balance before and then balance after. Okay. And then say require balance after is greater than or equal to. So it doesn't have to be equal. It can be more. We'll take extra money back. Say flash loan hasn't been paid back. So now we should run the test and it should fail because they haven't actually paid us the money back. Okay. All right. So I forgot to do the address balance before. Sorry. Balance after is greater than or equal to balance before. All right. So yeah. The flash loan hasn't been paid back. We get the exact error that we expect. So now inside of the flash loan receiver, we need to actually return the funds to the pool because it's not going to work. That's the whole point of a flash loan. The flash loan failed because we didn't pay the money back. That's the whole beauty of them is you can't lose the money if you try to borrow it. And then basically require token address, transfer, message sender, amount. So we're going to send them back. We're going to add it to require here. And then if it doesn't work, we're just going to say transfer of tokens failed. So I'll scoot this over so you can see that fully. Okay. Okay, awesome. So now it's passing. We've actually successfully taken out a flash loan. We have done that and then paid the money back. Awesome. So there's one last thing that I want to add to the flash loan contract before we finish. This contract is vulnerable to reentrancy. And remember, I was talking earlier that we're taking heavy inspiration from the damn vulnerable DeFi contract. I put the links in here for full credit. You know what I mean? So in that, the whole point is to show you how to, basically create something that, helps with that. So we're going to add, or basically show you how reentrancy works. Okay. So we're going to add a non-reentrant, a reentrancy guard from OpenZeppelin. So we can basically import that like this. And if you don't understand reentrancy, we're going to do it. We're going to cover reentrancy in the next section on on hacking smart contracts. Okay, so that's going to be the next section. So we'll revisit this and talk about reentrancy, why it's important, and how to protect yourself. But for now, basically, we're just going to say flash loan is reentrancy guard, and then we say external non-reentrant, external non-reentrant. All right, let's just do it again. Okay, awesome. Boom, there we go. All right, so that's an overview of how to code out a flash loan smart contract and then how to code a contract that receives the money. So now what you can do is essentially take this and implement your own code here to go do stuff with the money, like buy cryptocurrency on one exchange and sell it on a different exchange. But in order to get to this point, you have to really understand how flash loans work from the inside out so that you can actually transfer tokens around, ensure that you've got money, how to pay money back. And this is a simple flash loan example, which is a great prerequisite to understanding how to do like real world flash loans if you're going to interface with a protocol like Aave and then go through their documentation on how to set up flash loans with their developer documentation. So once you have gone through what I've just shown you, it's going to be a lot easier for you to actually understand how to implement your own contracts. Because if you don't know how to make smart contracts talk to one another, if you don't know how to like pay tokens around how tokens work, you're going to get completely in over your head. But after you have, gone through this primer on flash loans in this particular installment of this tutorial series, you're going to be way better equipped to actually use their flash loans or somebody else's. All right. And then code your own custom logic to do stuff with the money. So this is where you can do things like buy cryptocurrency on one exchange and sell it on another. But once you've done this, you got your own tests in place. That's going to make it, a lot easier for you to go down that path. So hope you like this section. That's an overview of flash loans. In the next section, we're going to talk about smart contract hacking, particularly with reentrancy, just like I hinted at with this example right here. All right, so now let's get into our section on hacking smart contracts. Okay, so this is a really popular topic because, there's so many smart contracts out there that hold lots and lots of money inside of them. And, smart contract hacking is a really important topic because at the end of the day, you ultimately want to learn about security vulnerabilities. Okay, not so that you can go out there and steal other people's money, but so that you can see like what bad guys can potentially do to your own smart contracts, so that you can protect your own contracts, and then also, find these in other people's smart contracts and help them. Like either you can check their smart contracts before they ever get deployed to the blockchain, or you can essentially find security vulnerabilities in real smart contracts out in the wild, okay? And you can disclose those vulnerabilities for bounties, okay? You can see a website like immunefi.com that has paid, is basically protecting $100 billion in user funds. They've paid out lots of bounties. You can see they've paid out $40 million, and they have $133 million of bounties available, okay? And then you can see like all the bounties that are listed here. So, security auditing is one of the most lucrative skills in blockchain. It's one of the highest paying developer jobs, and there's also a ton of upside in getting bounties. But if you're ever even going to do that, whether you're trying to go be a bounty hunter, a bug bounty hunter, or you're going to be a security auditor, or just a competent smart contract developer that understands security vulnerabilities so that you don't make somebody else's life harder. Okay, it's important to just get the basics. So there's lots of different ways in which your smart contract could get hacked. But one particular way that we're going to focus on in this tutorial and actually code it out step by step so that you really understand it is called a reentrancy attack. So this is one of the most common security vulnerabilities in smart contracts. If you've ever heard of the DAO hack, okay, that was one of the most famous, bugs early on in a contract that was hacked on the Ethereum network. So that was a reentrancy attack. This is, this exists in lots of different production smart contracts that have been disclosed over the years. It's really, really common. It's one thing that you want to learn to avoid. So I'm going to show you how to code it out step by step. So before we do that, let's look at the basics of what a reentrancy attack is. Well, let's break it down. Reentrancy. So re-enter, all right? That's the word enter is inside of there. Enter, entrant, and then re. So basically it means that you're calling a function again, okay, before it's like everything's finished updating. So here's an example. So you have contract A, all right, which basically is responsible for checking a balance and then sending funds and then updating the balance. And then if you create a second smart contract, it can receive money, and then contract B can keep calling contract A before it's done updating balances. And then you can just like do this on loop, and you can essentially drain the entire smart contract of all the money inside of it. So that might sound a little bit abstract, but I think we just code the example out. You're going to see exactly how it works, how a reentrancy attack is performed, and then how you can protect your own smart contracts against that reentrancy attack. So let's start off by coding. Okay, we're going to code the smart contract that actually deposits funds. So create a new file. And we'll call this bank. So bank.sol. All right. And then what are we going to do with bank? Well, we're basically just going to create a smart contract that lets people deposit Ether inside of it and then withdraw the Ether. And we'll create a reentrancy vulnerability. We talked about reentrancy in the last section briefly with our flash loan example. But we're gonna talk about reentrancy from scratch in this example. So let's just do our boilerplate code at the top of the file here. Let's add the license identifier. Okay. Let's add the Solidity programming language version. Okay. We're going to import a library from OpenZeppelin for the addresses. All right. We're going to say import OpenZeppelin contracts utils address.sol. Okay. We talked about OpenZeppelin in the previous sections. If you're just skipping ahead to this for the auditing purposes, you don't understand some of this stuff. I've made this video cumulative, so I'm not going to cover every single thing in depth that I covered in previous sections. I try to make that cumulative for everybody who's watched up to this point and not just repeat myself over and over again. So anyways, we're going to say contract bank. Okay. And then we're going to put all the code inside of here. And then we're going to have this thing that says using address for address payable. And that address comes from the address library here. Okay. And so basically, this bank's going to have a really simple functionality. It's just going to let people deposit Ether funds and then withdraw their funds. And you can make this really complex smart contract where you did yield farming with it or something, or let people take out flash loans with these funds. Doesn't really matter, okay? As long as, but right now we're just going to have really simple deposit and withdrawal functionality so that you can highlight how the reentrancy works, and you can apply this pattern to many other things. Because at the end of the day, if you're going to become a good security auditor or just a better smart contract developer, you don't have to be a genius, right? But the more patterns that you learn to recognize, you'll see these out in the wild and learn how to protect yourself against them. And I'm going to show you how to recognize the reentrancy pattern and how to protect yourself against it. So let's create a basic test, all right? So down here inside of the test file, well, looks like I created the Solidity contract in the wrong directory, so let's just move that. Let's put it in contracts, bank, okay? And then inside of here, we're going to create a test. So I'll say new file. And if you are just skipping ahead, I'm in a HARDHAT project. I talked about HARDHAT in the second section inside of testing smart contracts. If you want to revisit that and see how to create this inside your project. So we'll see, let's call this reentrancy.js. Okay. So now we should have that here. And then I think that created in the right place. I think I moved that. Let's move it. Sorry, everybody. Let's go to tests. All right, there you go. Boom, reentrancy.js. And inside of here, we're going to do our boilerplate. We're going to say expect from chai, and then ethers from HARDHAT. Okay. And then we'll say describe, say reentrancy. And we'll say do this function. Okay. And we'll do our deployment. Say async, go at the function. And then we'll say let deployer, okay, say let bank. Okay, we'll deploy the bank contract. So we'll do, we'll say const bank equals await ethers get contract factory. And we'll say bank. And let's go ahead and connect the deployer to it. All right. So we're going to, well, actually, we're going to, yeah, we're just going to do that. Okay. We're only going to have, we're only going to let the deployer do that for now. And we'll say bank, await, bank.deploy. Okay. And then let's just see if that, let's do a smoke test and see if it works. So this is from the previous section. Let's say npx HARDHAT test. Let's say reentrancy. Okay, so before each, I think I did a typo here. Okay, so it's that worked, but let's actually create a test example. Let's just say test. It facilitates deposits and withdrawals. And then we'll just say function. And actually, let's make this a describe function, not it. Describe. Okay. And we'll say it accepts deposits. All right. Let's say async. We're going to check that deposits actually took place. So check deposit balance. Okay. So let's create a function to let people actually deposit Ether into the bank. All right. So we'll create a function here called deposit. Deposit. And we'll say external payable. And then we'll do this like this. We'll say balance of. So what we're going to do is create a function people can call to deposit. And they'll call this function. Remember, payable from our last section lets us actually send in Ether or Ethereum cryptocurrency to the smart contract whenever they call this function. So they can send that in as part of the transaction. They call the function, they send in some value here. So that will allow us to deposit funds to the bank, but we need a place to store that. All right. So we're going to use a mapping. Again, we covered mappings in the last couple sections, so go revisit that again. If you're just jumping into this section, I'm not going to cover everything again from scratch. We covered this cumulatively in the previous sections. So mapping, and we'll pass in an address, will be the key, and the value will be the UINT 256. That'll be the actual balance. Say public balance of, just like an ERC20 token would. Okay. And inside deposit, we'll just got a really simple code here. Again, this is just to highlight reentrancy. It's not going to be a bomb-proof bank contract. In fact, it's not supposed to be. It's supposed to be vulnerable to reentrancy, and I'll show you how to fix that. But for the basic functionality, we're just going to say balance of. Okay, and then update the mapping with message sender. So this will be the person who's sending the money. And then we'll basically add the message value, which is the amount of Ether sent in. And this plus equals basically just updates the amount with this value. So in the previous sections, we saw the increment operator with like plus plus and then minus minus. But plus equal increments by a specific value. Those previous ones, this would just update it by, 1 without this, right? Or this would update it, this would change it, this would decrease it by 1, and this actually updates it by a specific value, which is message value. Okay, so what this does is just reads the balance and then updates it it adds the value that's sent in here. So that's deposit. So let's just check that it accepts deposits. That's the basic functionality we want to do here. So we'll actually call, we'll say await bank.deposit. And we'll say, we can pass in the value like this. So value, we'll say ethers. Let me pull this over. Let me kill the file browser. We don't need that right now. Ethers, utils, parse, ether. We'll say 100. Okay. And we're going to do that from the deployer because we're automatically with the deployer whenever we do this. And then we'll just check the deployer balance here. Say const deployer balance equals await bank balance of the deployer address. We'll say expect deployer balance to equal, we'll say equal EQ for short, ethers to utils, parse ether 100. All right, so let's see if that works. Run the test. Okay, all right. So let's just fix this. All right, so I realized with the problem here, we haven't specified the deployer yet. Okay, so the deployer is going to be one of the accounts from ethers. So we can, get the signers from ethers like we did in the previous examples. Again, go check that out if you haven't already. We say await ethers get signers. That's going to give us all the wallets connected. And we can, instead of we're going to show you a new pattern. Basically, we can do a destructuring here with a deployer. So it's going to return an array, and we can just get we do parallel assignment here. So I said destructure, I meant parallel assignment. We can parallel assign the deployer by just giving it an array like this, and it's going to assign the deployer variable from the first item in the array that's returned by get signers. Let's do that, and let's try it again, see if it works. All right, it passes. So it accepts deposits. We can see that it actually deposited funds in there. Okay. So now let's add another user into the equation. Let's add a user. Let's let them deposit some funds too. Okay. Let's and then we'll say await. Let's let the user deposit 50 ether. So we'll do it like this. Say await bank connect user. So not doing it on behalf of the deployer here. We're connecting with a different account, bank user. Deposit value ethers utils parse ether 50. So they're going to send 50 ether. The deployer is going to send 100. That'd be 50. Okay. And then now we can check the user balance inside of here. Could say user balance equals await balance of user address to equal 50. Try that. Okay. Awesome. So now we can say it should accept withdrawals. That's going to be the other part of the equation. So it accepts withdrawals. Pass in a function. This should be async as well. And inside of here, we want to withdraw some funds from the deployer account. So we can do it automatically because we're connected with it like this. But we need to implement a withdrawal function in the smart contract. So we'll do a withdrawal function like this. Function withdraw. External. And we'll say, well, we're going to create a vulnerability here. We'll just say uint deposited amount equals balance of message.sender. And then we will say payable message.sender. Send value, say deposited amount. Okay. So basically it's going to withdraw all of my funds inside, all of the funds inside the contract. Okay. And then it's going to update to balance of message.sender equals 0. Okay. All right. So let's test out that functionality. We'll just say await bank withdraw. Okay. And then let's just check the deployer balance. We'll say const deployer balance equals await bank balance of deployer address. And then let's check the user balance. Okay. And then the deployer balance should be 0. It should take out all of their tokens or ether. And then the user balance should still have some ether inside there. So it should still be 50 because the user didn't actually call withdraw. Do that. We'll run the test. Okay, awesome. So it accepts deposits and accepts withdrawals. So that is the basic functionality to the bank smart contract. Again, this could be a lot more sophisticated. You could make this like a full-on liquidity pool with like flash loans or yield farming or something. But for now, we just want to make it a simple bank and highlight the reentrancy vulnerability. So in order to do that, we have to create a separate smart contract because, a user in and of themselves could not just get on there with an Ethereum address and then, perform a reentrancy attack to drain the funds from this bank. All right. But someone with a smart contract could execute a reentrancy attack. And so for that reason, we need to create a separate smart contract for the attacker. So let's create a new contract here and we'll call this attacker.sol. Okay. Let's just make sure that it's actually in the right place. Yeah, it's in our contracts directory. And inside of here, we're going to code out the attacker contract. So we'll do our boilerplate. We'll add the license identifier and then also the programming language version. And then we'll say, let's just see here, contract attacker. Okay. And then we'll put our stuff inside of here. And we will deploy the contract to the network. All right. We'll just say, well, first of all, let's add some more stuff. First of all, we want to set this up so that it understands how to interact with the bank. Okay. So I'm going to do this a little bit faster because we already covered our interfaces, in the previous sections. Definitely go check that out if you haven't already. But we're going to say interface bank. Okay. And we know that the bank has a deposit and withdrawal function, like we saw here. Okay, so we're going to add that. We'll just say, we'll do this. Say it has a deposit function and it has a withdrawal function. This is external payable and this is external. So our attacker contract is going to know how to interact with the bank based on this. And then we'll add a constructor function. And we'll say address bank. And then we'll do this. We'll say, we'll save the bank here. Say bank, public, mutable, bank. And then we'll say bank equals bank. Okay. And then now we should be able to deploy our attacker here. So we'll say const attacker equals await ethers get contract factory. And we'll paste in the attacker. And we'll go ahead and we'll add a new attacker. We'll add a new user here for the attacker. This is the actual account that's going to do the exploit, not the attacker contract. This is the attacker contract. This is the attacker user. We'll go ahead and connect the attacker. Okay. And then we'll say attacker contract equals await attacker deploy. And we'll say bank bank.address. Okay, so let's save this here as well. We have to do attacker contract long ways because there's a naming conflict between the attacker user and the attacker contract. So we'll just do that like this. Let's just deploy it, make sure it still works. All right, still works. Awesome. So now let's focus on executing the attack, the Reentrancy attack. So let's say it allows attacker to drain funds from withdrawal. We'll say async. We'll do a function here. Okay. So let's see how we can actually do reentrancy. All right. So let's set this up with some console logging so that you can see how it works. So the first thing we want to do is just get the entire Ether balance of the whole bank. Okay. So earlier before, we were checking the balance, right? Like we were using the balance of function to see what the actual balance was of each user. But in this case, we want to see like the entire balance of the bank. So we could do that like this. We could say await ethers provider get balance. That's how we do it in ethers.js, just checking the ether balance of any address. It can be a user address, an externally owned account, or it can be a smart contract address. So say bank.address. Okay, so we can say console.log. All right. And then you can see it here. Okay, so we can see the value. But let's actually format it. So we'll say, ethers.utils format ether. And then we'll do that. Okay, so 150. Okay. And so now we can add some more to the console logging statement. We can actually do string interpolation. So you can interpolate the values inside the string. If you use backticks, right? You can use this $sign and then use these curly braces and then put these inside of here. Okay. And then you can say basically like bank balance and then do this. Oops. Template string. Let's see here. What did I do? So it's missing. All right. So that's working. All right. And so we'll also do this. We'll just do a console log before. Save that. And then let's also check the attacker's balance. Okay. I'm just going to do it like this. Copy that and say attacker's balance. For my Ether, let's do the attacker address. Okay. Okay, so we can see the attacker's address is this. There's the bank address. So what we want to do is actually do the reentrancy exploit and drain the bank completely. Okay. So let's do it like this. Let's create an attack. Well, first of all, before we do that, let's go ahead and log it after. So we're gonna perform the attack here, and then let's log after. Okay. So it'll be the same. We haven't actually performed the attack yet, but we're just setting up the test so we can see before and after. And then let's check bank balance has been drained. We'll do that in a minute. Okay. So we set this up. Now let's actually create the functionality into the attacker contract to do it. So we're going to create an attack function. All right, inside attacker. Say function attack external payable. Okay, and what we're going to do inside here is perform the attack, but we also want to make sure that only the attacker can call this. So let's set an owner. All right, So what we're going to do is add the ownable library. So in our previous ones, we set the owner as message sender, but we can use a library, all right, from OpenZeppelin, which we talked about several times in this series already. We can import the OpenZeppelin ownable, all right, and just say is ownable. And then whenever we do that, it's going to automatically assign the owner to the person who deployed the contract. And so we'll just say is ownable. So if you look at our previous examples, like when we did like flash loan receiver, like we set the owner like this. But when we use the ownable library, we can get that functionality for free by simply inheriting from the ownable library and then doing that. So let's just run the test to make sure we still compile, that we set up our library properly. Okay, so now we need to actually fix that. Okay. So I accidentally added is ownable to the bank. We don't really want that. It's my fault. Sorry, sometimes it's hard to code and talk at the same time and then think about what I'm doing. So let's try that again. All right, so it passes. And then now we want to call the attack function. So it doesn't do anything yet. We're gonna write the test first, then make it pass. So await attacker contract attack. And then we're going to pass in, it's going to be a payable function. So what we're going to do essentially is just do it with 10 ether. So we're going to do 10 ether in a loop to drain it. Value. Ethers, utils. Parse, ether. 10. We're going to send in 10 ethers. I'll move this over so you can see the full code. All right. So let's make sure we can actually call the function. Okay. So it's not doing anything yet, but we're calling the function. And then lastly, what we want to do, let's write the test that we want to happen and then make it pass. So the expectation is expect. I'm going to move this up so you can see it in case it's cut off screen. Let's say expect await ethers provider get balance bank.address to equal 0. Now it's going to fail because we're not actually draining the contract yet, but we'll write the test first and make it pass. Okay. So it's expecting it to be 0, but it's actually this. All right. So let's write the code to perform the reentrancy attack. So how this is going to work is that we are essentially going to call deposit and withdraw, okay, back to back inside the same function. All right. And then we're going to implement a function to receive ether. And then whenever we essentially receive the ether, we're going to call withdraw. We're basically going to, we're going to keep doing it in a loop. So I'll show you how that works. So go back to our example here. We can see what happens is it checks the balance, it sends the funds, updates the balance, and then this has a function that lets us receive ether. And inside that function where we receive ether, we just do it again. Okay. So we need an attack function and we also need a receive function. So again, we covered receive in the previous section. Receive is the function that lets this smart contract receive ether. Okay. Because the external payable. And in the previous section, all we did was we made this contract receive ether. That's it. And it just stored ether. But like I was saying before, is you can execute business logic inside of here. And so basically what we want to do is call, bank withdraw again inside of here. Okay. So here we're going to say bank deposit. And then let's just do this. Say value, message.value. Okay. I'll make this only owner. Okay. And then we're going to turn around and call withdraw. Okay. And then inside of receive, we're going to do withdraw again. But we want to do it based on some conditions. We want it to drain the entire thing. So this is how it's going to perform the loop. So say if, let me just move this down in case you can't see it. We'll say if, we can do conditionals, that's a little like this. Say address, bank contract, or say bank, sorry. It's greater than, or address balance. We can read the balance in solidity like this. If it's greater than 0, if there's still funds in there, we want to keep calling withdraw. All right. And if it's fully drained, I'm not sure why it's doing that. We want to send the funds to the attacker. And then transfer address, this balance. So this will actually send the funds to the attacker account. All right, so let's kind of go over that to see how it works. And well, actually, let's just run the test and see if it passes. And then we'll explain, we'll make sure, we'll fix any potential errors in the code. All right, so yeah, let's just fix that. Let's add a semicolon here, add a semicolon here. All right, so it worked. You can see that here's the balances. We'll explain it here in a second. But okay, so let's look at it. So the contract, what it does is it calls attack, which does deposit. All right, it goes to the bank's deposit function, which, you know, basically updates balance. And then it instantly calls withdraw. Okay, and whenever it receives the ether in this withdraw function, you know, it takes the deposit amount, then sends it down to 0, okay? It's going to hit this function receive, which is going to say, okay, we haven't finished updating. It hasn't finished totally updating the state yet. So we can, once we get it, if the balance is still greater than 0, we can call withdraw again. And that's where the real big vulnerability comes into place. You can just keep calling withdraw once you've received the money because of how brittle this implementation is for balance of, okay? So you can see here, like payable, send value. Once it hits this, it hasn't hit this yet. Okay, so you can just call withdraw again before it actually sends your balance to 0. That's where the big vulnerability is because it's a brittle implementation, all right? And so you can just keep calling withdraw and it will drain the funds down to 0. And once they are 0 and it hits this again, you're just calling it on loop. You can basically say, all right, now all the money's in this smart contract, just send the money to my wallet and it's gone, okay? So that's how you perform a reentrancy attack, and that's how you spot the vulnerability, is because whenever it receives the money on this line, it hasn't hit this line yet, and you can just keep calling withdraw, drain the contract balance to 0, okay? And what you can see here in the test, okay, we'll just run it, make sure it still works. You can see the attacker bank's balance before is 150. The attacker's balance before is this. And then, you know, the bank's balance is 0 after the attack, and the attacker's balance is now this. All right. All right, so that's how you perform the reentrancy attack and how you can spot the vulnerability in your own contracts. Now, how do you fix it? Like, how do you get better at it? Well, there's different strategies. But the easiest way is just to add the reentrancy guard from OpenZeppelin. So we did that in the flash loan example previously. Okay, so inside flash loan, we see this reentrancy guard, non-reentrant. So let's just import that into our code from OpenZeppelin. So basically, let's just go to flash loan and let's import the reentrancy guard. Let's just copy this, and then we'll add that here. So below that import, we'll do this import. I'll move it over just so you can see the final code solution. And then we will say bank is reentrancy guard. All right. And then let's just make sure it still compiles. It should still work. We're not actually doing the reentrancy guard just yet. I just want to make sure that it compiles properly. We imported the library with no issues. Okay. It's still vulnerable. Okay. But we'll make sure the contracts compile. So now we can essentially add the non-reentrant function here, protect against the reentrancy attack. Say non-reentrant. Look at that modifier. So I think that's how you spell it. Let's just see. All right. Unable to send value. Perfect. Awesome. So now we are successfully protecting against the reentrancy guard. So I'm going to leave that off the final code solution because, if you want to write a test yourself as an exercise to prove that it's non-reentrant, you could create a new maybe copy of the bank to show that the non-reentrant version and then test and make sure that the transactions are reverted. We showed you how to, safeguard against, basically how to check for revert messages in other contracts in previous sections so you could write your own test if you want to. But that is an overview of reentrancy, how to spot it inside your smart contracts, step by step, and how to fix the problem.
Let's take a look at the app we're going to build today in this tutorial. This app will have the same core features common across all of the most popular marketplace apps in the NFT space right now. It lets you buy and sell NFTs with Ether, as well as view the ones you've purchased or listed on the marketplace. I'm going to walk you through, step by step, how to build each layer of this application. We're going to spin up a development blockchain, create Ethereum smart contracts, write tests against them, and build a client-side website so that anyone can use the app. You don't need any prior coding experience to follow along with this tutorial. I'll explain everything assuming you know nothing. Even if you have no idea what an NFT or blockchain is, that's okay. I'll go over what those things are before we start coding. And one last thing before we get started, if you want to see more full-length coding tutorials like this one, please leave a like and subscribe to this channel. And if you enjoyed the video, want to take the next step, become a blockchain developer as soon as possible, head on over to dappuniversity.com/bootcamp to get started today. First things first, let's go over what a blockchain is, and then we'll cover NFTs. If you're already familiar with these technologies, feel free to skip ahead using the timestamps linked in the description down below. So what is a blockchain and why do we need it? In essence, a blockchain is a distributed ledger that powers decentralized applications, or dApps for short. A dApp is different from most traditional web applications in that the client-side website, the part of the app that users interact with, doesn't talk to a centralized server that connects to a database. Instead, a dApp relies on the blockchain to store data, but not just any type of data that represents value. So you might be asking, why should we use a blockchain as opposed to a regular web app to store value? Well, the problem is that if, for instance, someone wanted to make a digital currency using a centralized database with a server, everyone who held the currency would have to trust that the person in control of managing the database would not arbitrarily change people's balances without their permission, and the developers of the server don't change the app's source code. Blockchains provide a solution to this. Because they are decentralized and immutable, you can create a digital currency or a digital representation of any asset for that matter using the blockchain. They circumvent the need for trust. So how do blockchains accomplish this? Well, a blockchain is made of a network of computers called nodes, which each contain an arbitrary copy of all the data contained within the network. You can gain access to the entire network by connecting to any one of these nodes. The data is stored in bundles of records called blocks that are chained together by the preceding block all the way down to the genesis block. When a new transaction occurs on the blockchain, all of the nodes execute the transaction in order to verify it and achieve consensus. Once that happens, there's no way to revert or modify the transaction. It stays on the blockchain forever. On the Ethereum network, you can also deploy smart contracts, which are Turing-complete programs that run on the blockchain. Smart contracts allow you to build any arbitrary application that handles business logic or agreements between different parties in a trustless manner. Using smart contracts, you can create Ethereum-based tokens, exchanges, crowdfunds, or auctions to name just a few. But for this video, we're going to build just two smart contracts that will power our NFT marketplace. One that represents a collection of NFTs, and another that allows users to buy and sell them. An example of a real-world NFT marketplace app out there is OPENSEA. And at the time of recording this video, not only is it the largest NFT marketplace, but it's also the most popular dApp in the world. It goes to show just how popular NFTs are right now. But what exactly are NFTs? An NFT is a non-fungible token, which means that it can't be interchanged for another NFT within the same collection. So why is each NFT worth differently? Well, unlike regular fungible tokens like Ether, Bitcoin, or even the US dollar, it matters which NFT you own. For instance, the first Bitcoin ever mined is worth the same as the last Bitcoin mined. But for NFTs, each one has unique qualities about it that make them appear more or less valuable compared to any other NFT. NFT smart contracts associate each NFT with an ID and a link to where the content of the NFT can be found on the web. This content can be an image, piece of music, or even a video, but most of the time it's just an image. Storing large files like this directly on the blockchain is very expensive and sometimes impossible. So as a workaround, these files are normally stored on a decentralized file storing system like IPFS, and the hash that points to where these files are located are stored on the blockchain. An NFT smart contract also keeps track of the owners of each NFT. There are special functions on the contract that allow us to transfer NFTs to new addresses. We're going to write a marketplace contract that interacts with these functions on the NFT contract to allow users to buy and sell NFTs. When a user wants to list their NFT for sale, they will call a function that will transfer their NFT to the marketplace, and the marketplace will keep track of the seller of the NFT and the price they want to sell it at. Users can buy any listed NFT by calling a function that transfers the amount of Ether the NFT was priced at from the buyer to the seller, then transfers the NFT from the marketplace to the buyer. Also, our NFT contract will have a mint function that will allow sellers to create new NFTs and then list them on the marketplace. Now let's start installing the dependencies we need for blockchain development. The first thing we're going to need to install is Node.js. You can install it directly from the website right here. And if you're not sure whether you have it installed yet, you can open up a terminal and type the following command, node-v, and it should output the version of Node you have installed if you have it installed. And I have version 17.0.1. And for this tutorial, I recommend installing a version of Node that's greater than or equal to 16.14 or less than or equal to 17.0.1 to avoid dependency issues. The next dependency we need is HARDHAT, which is a smart contract development framework. We can use it to write smart contracts in the Solidity programming language, write tests against them, and even boot up a local development blockchain with a few commands and then deploy those smart contracts to it. For this tutorial, I'm going to install a very specific version of HARDHAT, and I suggest you do the same. So in your terminal, type npm install --save-dev HARDHAT at 2.8.4, and then press enter. Lastly, we're going to need to install MetaMask, which will turn our browser into a crypto-compatible browser. To do that, go to the metamask.io website, then click download, click this install MetaMask for Chrome button, go through the setup steps, and once you've done that, go to your Chrome extension settings, and then make sure MetaMask has been enabled. And you know it's been enabled once you see this Fox icon at the top right-hand corner of your screen. All right, now let's start setting up the project. Now, instead of setting everything up manually, we're going to use a starter kit that I created. You can find the link to it in the description. So go ahead and copy it. Then open up a new terminal. Type git clone, paste in the URL, add a space, and then we're going to set the name of the project to NFT Marketplace, then hit enter. Okay, once that's done, go ahead and enter into the directory by typing cd NFT Marketplace. Now I'm going to install all of the project-specific dependencies by typing npm install, hit enter. All right, once that's done, you know it was successful if it said added packages right here. It's okay if you see any warnings. It's not ideal, but as long as you don't see any error messages, then the installation was successful. Now, before we move on, we're going to need to install a few more dependencies not included in the starter kit. So if I go back to the application preview, you see that whenever I click any of these navigation links, the app routes me to a new page. We need to install the React Router DOM dependencies to support this feature, since it doesn't come bundled with vanilla React. So to do that, go back to your terminal, type npm install react-router-dom at 6, then hit enter. All right, once that's done, let's go ahead and install the next dependency that we're going to need, which is the IPFS HTTP client. We're going to use this to upload the content of the NFT to IPFS before we mint it using this create and list NFT form. So we go back to our diagram, we see that our NFT contract stores the hash of where the image is located in IPFS. So go to the terminal, type npm install IPFS -http -client at version 56.0.1, then hit enter. Whoops, should be a dot, not a comma. The last dependency we're going to add to our project is the OpenZeppelin contracts library. This is essentially a library of a bunch of secure pre-made contracts that developers can import into their projects when writing a new contract, so they don't have to constantly reinvent the wheel for a lot of common smart contract patterns and implementations. So we're going to use this to import the ERC 721 NFT standard. We're going to go look at that standard more in depth once we get to it. So go ahead and enter npm I at OpenZeppelin/contracts and then at 4.5.0, then hit enter. All right, with all the dependencies installed, let's go ahead and get a tour of the project. So I'm going to open up the project with the VS Code text editor. You can use whichever text editor you'd like. I'm going to do it from the terminal using a symlink by typing code space dot, then hitting enter. So this is a HARDHAT and React project combined into one. HARDHAT gives us all the features we need to create smart contracts, write tests against them, and deploy them to a local blockchain. And React allows us to create a client-side website that talks to these smart contracts. So I'm going to show you what's inside of here. The first place to take note is this hardhat.config file. This is where we specify the version of Solidity that we will be using to compile our smart contracts, as well as where the smart contracts live in the project. Now, if you've used HARDHAT before, this may look a little new to you. That's because I've configured HARDHAT to put the smart contracts in a place that they're not normally at by default. This is because I want to be able to access the contracts from the client-side portion of the application. And in just a moment, we're going to look more in depth at how that works. Moving on, let's go ahead and check out this source directory. So our app is organized into two different parts. We have this backend component found in this backend directory, and this is where all of the smart contract source code will live, as well as the test for those smart contracts and a deployment script, which we can run to deploy these smart contracts to our local development blockchain. I'll explain what this code does once we get to it. Moving on, we have this front-end directory, and this is where the code for our client-side application will live. And the code is made up of components, React components, which are reusable pieces of code that come standard with the React framework. And we also have this package.json file, which contains all of our project-specific dependencies. And as you can see, we included the OpenZeppelin contracts, the IPFS, HTTP client, and React Router DOM manually. Next, let's go ahead and boot up the web server of the client-side application to make sure that everything was set up properly. I'm going to do that from VS Code's built-in terminal. Type the following command, npm run start, hit enter. And that command should have opened up the client-side app in a new browser tab like this. So here's the Dapp University Starter Kit. We're using Bootstrap to style it. We've used it to create this really nice looking navbar, font, and image logo. And we're going to use Bootstrap quite heavily to make our application look really nice without having to code out a bunch of raw CSS. So eventually we're going to turn the application from this into this. So to go from the starter kit to the completed app that I just previewed to y'all, we're going to need to modify the starter kit code located inside the app.js directory. So go ahead and return to your terminal, open up a new tab. We're going to use this new tab to develop our smart contracts. We can leave the web server running in the background. We're eventually going to return back to it once we're done with the backend portion of the app. Okay, let's start by creating a new directory for the contracts by typing mkdir source backend contracts and enter. Okay, and then let's go ahead and create our first contract inside of that directory. I'm typing touch source backend contracts nft.sol. Hit enter. Okay, let's check it out. Boom, and here it is. So we're going to start by pasting in the license identifier, like so. We're going to be using an MIT license. Next, we're going to indicate to the compiler which version of Solidity we're going to use with this pragma statement. So pragma, Solidity, and then we declare the version number of Solidity we're using. So we're using 0.8.4, which is the same version that HARDHAT expects us to use. And we end every single line of code with a semicolon. Next, we're going to import the ERC721 URI storage contract from the OpenZeppelin library, like so. So the ERC721 standard is an agreed upon standard that defines the set of all functions that a NFT contract should have at the bare minimum. This standard was designed so that any NFT contract is compatible with any Dapp, wallet, or marketplace that interact with it. Plus, it saves developers a lot of time. It prevents them from having to reinvent the wheel each time they create a new NFT smart contract. They can just import this ERC721 contract into their NFT contract and append it where needed. And that's exactly what we're going to do. But before we do that, let's take a closer look at the functions that make up this standard. So you don't have to know what each of these functions do, but you should focus on this transfer from and approve to function. These are the main functions that we will be calling from inside of our project. This transfer from function transfers a specific NFT, passing in the token ID, from one account, passing in a from address to another, passing in a to address. And then this approve function allows a particular address. Normally it's a contract, but it can be a user's address, an externally owned account rather, to spend a particular NFT that we own. Yeah, whenever we transfer NFTs to the marketplace, the user will have to call this approve function first. We're going to examine these functions more in detail once we start coding out the marketplace contract. Next, we're going to create the contract like so. Contract, followed by the name, NFT, then curly braces. Inside these curly braces is where the code of the NFT contract will reside. Now, we also want to inherit all the functions from the ERC721 standard, which we've imported here. And we can do that using the is keyword. So we could say NFT is name of this, paste it here. Sweet. Now our NFT contract abides by the ERC 721 standard. Next, we're going to declare a state variable that keeps track of the number of tokens. Now, state variables are variables that are declared within a contract, but outside of any functions within that contract. And only the functions from within the contract can modify these state variables. And these state variables are stored to the blockchain. And whenever a function modifies a state variable, you are modifying the state of the blockchain, and therefore it costs gas to call said function. So I'm going to give a more concrete example of that once we code out the mint function for this NFT contract. So to declare a variable, we first have to declare the data type of the variable. So for the token count, we're going to declare it as an unsigned integer. So you can abbreviate that by typing uint. And then we follow that up with the name of the variable, so token count. And the reason why we have to specify the data type of the variable is that Solidity is a statically typed language, which means that the data type of a variable cannot change. It's determined at compile time. So we have to be explicit with the data type for each variable we declare. And we also want to allow this token count to be read outside of the contract. So we'll mark it as public as well. Next, let's create a constructor function, which is a special function that's called only once after the contract has been deployed to the blockchain. To do that, we're going to type constructor parentheses followed by curly braces. Inside these parentheses is where we pass in the arguments for the constructor function. And inside these curly braces contains the code of the constructor function that will be executed when called. So for this constructor function, we're not going to put anything inside the curly braces or pass any values to it. But what we are going to do is call the constructor on this inherited contract. So the ERC 721 contract. We can do that by typing ERC 721 and then pass in the arguments for this constructor. So the first one will be the name of the NFT. So we're going to call it Dapp NFT, followed by the symbol of the NFT, which I'll set to, Dapp in all caps. Next, we're going to write a function that will allow us to mint new NFTs. So to do that, we'll use the function keyword, followed by the name of the function, parentheses, and this function will accept one input, and that's going to be type string. And this will be the token URI, which is the metadata of the NFT, essentially the link to where the content of the NFT can be found on IPFS. So I'm going to pass that in. And whenever you're passing strings to a function, you need to specify the memory location of the argument. So I'm going to specify that it's in memory. And then we need to set the visibility of this function. So we want this function to be called from the outside, but not from any functions within this contract. So we'll use the external keyword for that. And we also want this function to return the current token count, which will correspond to the ID of the newly minted token. So to do that, we'll use the returns keyword, then specify the return data type, which will be an unsigned integer. Inside the function body, we're going to increase the token count by 1 using this ++ increment operator. Then we're going to mint a new NFT by calling the internal safe mint function, which came from the inherited ERC 721 contract. And for the first argument, we pass in the address that we're minting for, which is the caller of this contract, which we can reference from the global msg.sender variable, and the ID of the token, which we can get from the token count. Then we're going to call another internal function, this time a function that sets the metadata for the newly minted NFT. And we pass in the ID of the NFT for the first argument, and for the second, we pass in the token URI that we passed into our call to the mint function. Then after that, we return the ID of the token we minted by returning the token count. And that's it. We've completed the entire NFT contract. That's all we needed. We just needed one function to mint NFTs. So one thing I should note before I continue is that in Solidity, if you declare a variable but don't initialize it, that Solidity will automatically initialize that variable with the default value of that variable's data type. So the default value of an unsigned integer is 0. So therefore, the token count is initialized with 0, even though we don't explicitly write that. Solidity does it automatically. All right, now let's try to deploy this contract to the blockchain and then interact with it from the HARDHAT console to make sure that we've set up the project correctly. First, we need to spin up a local blockchain. The HARDHAT framework comes bundled with a blockchain that we can run from our terminal. So to do that, go ahead and create a new terminal tab and then type the following command: npx hardhat node, then hit enter. And as you can see, the local blockchain comes with 20 unlocked accounts, each funded with 10,000 fake ether. And here are the addresses of the accounts and then the associated private keys. Please do not use any of these accounts to store any real money, because everyone who's seen this video can gain access to these accounts and compromise your funds. All right, now that we've booted up a local development blockchain, let's check out this scripts directory, open up this deploy.js file. Whenever we run this deploy script, we essentially put our smart contracts on this blockchain. And we also save a copy of the smart contracts ABI and the smart contracts address to this front end directory. We do that so our client-side application can create a JavaScript instance for our smart contracts. And to do that, it needs the contract's address and ABI. Our front-end website has to create these instances in order to read and write data from our smart contracts. Don't worry if that seems a little confusing. It'll make a lot more sense once we start building out the front end. I just want to explain the purpose of this save front end function within the deploy script. We can do that by calling the getContractFactory method on the ethers object. Right now, this deploy script is incomplete because we haven't implemented the code that performs the action of deploying the NFT contract to the blockchain. So we can do that in 2 lines of code, like so. So this first line of code fetches a contract factory, so specifically an NFT contract factory. And all this, if you want to know more about what a factory is, you can read it from the Ethers documentation. So it says that the contract factory sends a special type of transaction and a init code transaction, where the init code will be evaluated and the result becomes a new code to be deployed as a new contract. So in other words, we require this contract factory to deploy the NFT. So we get an NFT contract factory, and we can fetch that by calling the getContractFactory method on the ethers object that's injected into our HARDHAT development environment. And all ethers is just a library for interacting with Ethereum nodes. And then we pass in the name of the contract that we want to get a factory for. And then we call the deployed method on the factory to fetch a deployed copy of the NFT. So for each of these function calls, we need to use the await keyword, because each of these calls are asynchronous. They return a promise, and we have to wait for that promise to resolve before we get a return value. And the reason behind this is that these are both calls to the blockchain, and the blockchain is slow. It returns values asynchronously. So that's why we have to use this await keyword. If you want to know more about how promises work, you can read the developer Mozilla documentation about it right here. I'm not going to go into too much detail about it. All you need to know is that it's used to handle asynchronous function calls. All right, now let's pass in the NFT contract and name of the contract to this save front-end files function. Alrighty, now let's go ahead and run this deploy script. So in your terminal, enter the following command: npx hardhat run source backend scripts deploy.js. Then we got to specify the network. So -- network localhost. Then hit enter. Sweet. We have successfully deployed the NFT smart contract to our local blockchain. Now let's go ahead and enter into the HARDHAT console by typing npx hardhat console, then hit enter. So this HARDHAT console is an interactive JavaScript environment for interacting with our blockchain and any smart contracts deployed to it. So let's go ahead and fetch a deployed copy of the NFT smart contract. We can do that by typing const contract await, then ethers. I'm going to use this get contract at method on the ethers global object. So get contract at. For this method, we first pass in the name of the contract we want to get, followed by its address, each within quotes. So you can get the contract from here, contract address rather, copy it, paste it within these quotes, and then hit enter. Sweet, it says it's undefined, but we enter in the variable name, the console contract will get the output. And sweet, it outputted a contract object which contains all of the external functions of the contract, essentially the interface. So we're going to call this token count function to output the token count on the NFT contract. So let's go ahead and type const token count await contract dot token count parentheses. Hopefully it works. Darn it. Okay, I see what's wrong. My bad, guys. I forgot that when I was entering into the console, I need to specify the network. So let's go ahead and exit out of the console by typing .exit, and then go back to the console command, and then type -- network localhost, then hit enter. Okay, now let's retype those commands. Reach, and then we'll do token count like this. Awesome. Type token count. Sweet, big number, value 0. Awesome. Exactly what we wanted. Now let's fetch the name of the NFT, which should be Dapp NFT. So do that like this. Name, await, contract. Replace token count with name, and then hit enter. Log name. Sweet, Dapp NFT. Now let's do the same thing for the symbol. Symbol equal to await, contract, dot, symbol, enter, symbol, sweet, DAPP. Exactly what we expected. Now that we've finished building out the NFT contract, deployed it to the blockchain, and interacted with it from the HARDHAT console, let's go ahead and build out our second smart contract for the marketplace. So if we go back to the diagram I showed y'all earlier, the marketplace contract is the contract where users can list their NFTs as items to be sold by potential buyers. So let's go ahead and create that. So let's create a new file inside of this contracts directory. Right click, new file. I'm going to call it marketplace.sol. Now let's go ahead and copy and paste the same license and pragma statement that we implemented in our NFT file onto the marketplace. Next, we're going to import the interface for the ERC 721 NFT standard from OpenZeppelin, like so. So before I continue, let me briefly explain what an interface is. In Solidity, you can interact with other contracts without having to know its code using an interface. So for instance, our marketplace will need to call this transfer from function on the NFT, but from the perspective of the marketplace, it doesn't need to know the code behind this transfer from function. It just needs to know how to call it. So essentially, an interface just defines how to call all the externally accessible functions of a smart contract. Next, we're going to implement a reentrancy guard contract that will protect the marketplace from reentrancy attacks. I'll explain more about how a reentrancy attack works once we implement the non-reentrant modifier on the marketplace functions. Next, let's declare some state variables. Our marketplace will charge fees for each NFT purchased. So we need to keep track of the account that receives those fees, as well as the fee percentage on the sales. So each of these variables will be public, and the fee percent will be type unsigned integer. The fee account will be type address, and it will also be payable so that the fee account can receive the Ether fees. And both of these variables will be marked as immutable, which means that they can only be assigned a value once. And we will initialize both of these inside the constructor of the marketplace. Next, let's write the constructor function that will initialize the fee percent and fee account. So it'll look like this. We pass into it the fee percent and assign that to the fee percent state variable. And then for the fee account, we don't pass any addresses into it. We can reference the msg.sender and assign that to the fee account because we want to set the fee account to the deployer of this contract, and only the deployer can call this constructor function, and we cast the deployer as payable. So before I start writing the functions that allow users to list their NFTs on the marketplace and to buy those NFTs, let's go ahead and finalize our setup by deploying the marketplace on the blockchain. So we can do that by modifying this deploy script. All right, now we're going to deploy the marketplace in the same way that we deployed the NFT, except we're going to pass in the fee percent inside the deploy method because the marketplace constructor accepts fee percent as an argument. So we have to pass that to the deploy method. Then we want to console.log the marketplace address and then save the marketplace files to the front end. All right, now let's go ahead and run the deploy script. So open up terminal, and if you are inside the HARDHAT console, you can exit out of it by typing .exit, hit enter. Now let's run the deploy script. Sweet, we have successfully deployed both the NFT and marketplace contracts. So now let's enter back into the HARDHAT console and interact with the marketplace contract. So let's fetch it like this: const marketplace is wait ethers.get contract at. Okay, and we'll pass in the name of the contract, capital M marketplace, followed by the contract's address right here. Copy it, paste it between the quotes. Okay. All right, hit enter. Awesome. Marketplace. Now let's fetch the fee percent on the marketplace. Fee percent await marketplace dot fee percent. Okay. Awesome. The value is 1, just like we set right here. Now let's fetch the fee account. Fee account. Okay. Sweet. And this fee account address should be identical to the first account listed here on the local development blockchain, because by default, HARDHAT assumes that the deployer is this account. So let's copy it, see if it's identical. Sweet, and it is. So one quick thing I should mention before we move on is that you may have noticed when we ran the deploy script for the second time that the deployer's account balance that we logged right here has decreased from its original 10,000 Ether. This is because whenever you deploy a contract to the Ethereum blockchain, you are updating the state of the blockchain. You're creating a transaction. And whenever you do that, you have to pay a fee for that. And that fee is paid with Ether. All right, now that we have finished setting up the deploy script, let's go ahead and start programming the marketplace. We're going to start with the function that will allow us to list NFTs for sale, and then the one that lets us buy them. Now, each time we implement some functionality into the contract, we need to test it out to ensure that it's doing what we expect it to do. We could run these tests from the HARDHAT console like we have been doing, but that's slow and inefficient. The better way is to write test scripts that automate this process. Testing smart contracts is very important because once a contract has been deployed, you can't change its code. It's not like web development where you can easily push bug fixes after you've deployed your app. The cost of bugs for smart contract developers is much higher. So writing robust tests for your smart contracts is an integral part of the development process. So the HARDHAT framework lets us write tests for our smart contracts, and we can create a directory for them inside of this backend folder. We're typing mkdir source backend test suite, and that created a new test folder. Inside of it, we can create a new test file named NFT marketplace.test.js. So this file will contain all of the tests for both the NFT and marketplace contracts, and they're going to be written in JavaScript using the Waffle testing framework provided to us by HARDHAT. Now, in addition to the Waffle testing framework, we're going to use the chai assertion library within our tests to conveniently compare values. We can use it to compare return values to expected values, among many other things. So, it comes with a should, expect, and assert declarations. So let's go ahead and import chai and then create our tests. So we'll write describe, and then we'll pass in the name of the test. So NFT marketplace. Then for the second argument, we'll pass a callback function. So an anonymous callback function, a function without a name. And inside of here is where we'll write all of the tests. So in order to write tests against them, we need to get the contract factories for each, just like we did inside of our deploy script using the ethers object injected into our HARDHAT development environment. Next, we need to fetch the signers for each of these test accounts on our HARDHAT development blockchain. You could think of signers as abstractions of Ethereum accounts that can be used to sign and then send transactions to the Ethereum network. So to get them, we can write await ethers dot get signers, and this will return an array of signers. Now we want the first signer returned in this array to be the deployer, and the second to be address 1, the third address 2. Now for this to work, we need to declare a variable for each of these signers up here using the let keyword like this. Next, we're going to deploy the contracts just like we did inside of the deploy script. And then we need to declare a variable for the NFT and marketplace contracts up here. NFT marketplace. All right, now we have everything set up to start writing our first test. But before we do that, let's wrap all of this code inside of a before each hook like this. So because we're going to be writing multiple tests, this before each hook will prevent us from having to copy and paste all of this code at the beginning of each of the tests. The before each hook does that for us automatically. So we only need to write this code once inside of it. Now let's write our first test to make sure that each contract was deployed to the network correctly. We can do that by writing describe, and then deployment, pass in a callback, and inside of here, we'll create the first test like this. It should track name and symbol of the NFT collection. We'll pass in an asynchronous callback. We're going to use expect from the chai library to make sure that the name of the NFT is correct. So we can do that by typing expect, and then we're going to fetch the name of the NFT like this, await NFT.name. All right. And say to equal, and this is where we put in the expected value. So we expect it to equal Dapp NFT. Okay, now let's duplicate this code. Do the same thing for the symbol. So symbol equal to all caps Dapp. Okay, let's do a quick overview of the code, make sure everything looks good before I run the test. Oh, this fee percent is undefined. Let's go ahead and define that up here. Let fee percent, assign it to 1. Okay. Now let's run the tests. Open up a terminal, type npx hardhat test. Nice. You see how fast that was? Remember how long it took for us to test for the name and symbol using the HARDHAT console? Automatic testing like this saves us so much time, especially for the more complicated tests, like the ones we're about to write. Next, we're going to test the deployment of the marketplace contract, just like we did from the HARDHAT console, like this. So we're going to track the fee count and fee percent using expect, like we did for the NFT collection. Next, let's check that the minting functionality on the NFT contract works. So we do that by like this, saying describe minting NFTs, and then we'll say it should track each minted NFT, a sync function, and inside of here, address 1 will mint an NFT by connecting their account to the NFT contract, calling the mint function on it and passing in the URI for it, and passing in URI metadata for the token. So you can set that variable up here. Let URI equal to sample URI. And moving on, we first checked that the token count for the NFT contract is equal to 1, and the balance, NFT balance for address 1 is equal to 1, and that the token URI for the first token is equal to the URI we set up here. Next, let's test what happens when address 2 mints an NFT. We should expect that the token count increases to 2, the NFT balance of address 2 should equal 1, and the token URI for token 2 should equal the URI we set up here. All right, and that's a really good basic test to start off with. We've covered the deployment of each of the contracts as well as the minting functionality of the NFT contract, which is all that we've covered so far. All right, now let's go ahead and finish building out our marketplace. So we know that the marketplace contract needs to keep track of each of the NFTs listed for sale. You could think of these things as items, okay? Marketplace items specifically. So each marketplace item has some data associated with it. It would include the ID of the NFT, the address of that NFT's contract, the address of the seller, the price that the seller set the NFT to. So we can group all of this data together into this thing called a struct. Okay, and we'll call it an item. You could think of a struct as the Solidity equivalent of JavaScript objects, if you're familiar with that. It allows you to create complex data types with multiple different fields. For the struct, we specify an item ID and an instance of the NFT contract associated with the NFT, the ID of the NFT being put for sale, the price it was set at, and the seller, as well as whether the NFT has been sold or not. The sold field is of type Boolean, which means that it can only hold either a true or false value. Now that we have defined our item struct, we need something that can store all of the different items. We can do that using a mapping, which is a special data structure in Solidity. It is a key value store, and you can look things up based on a key and get a value back. The item ID will be the key, and the item struct will be the return value. We can define our mapping like this. Mapping, and then inside parentheses, we specify the data type of the key, be an unsigned integer, then the data type of the return value should be an item, then we name, then we can set the name of the mapping. I'm going to set it to items, and we want this mapping to be publicly accessible, so we'll say that it's public. Now let's create the function that makes items. Function make item, and we're going to pass the NFT contract of the NFT to be listed. So to underscore NFT, and we're going to make this an instance of an ERC 721 contract by making it the data type ERC 721, which we imported from here. So from the front end, the user will pass in the address of the NFT contract, and then Solidity will automatically turn it into an NFT contract instance. Next, we will input a token ID as well as the price of the token. And the function will be external, and we're going to add the non-reentrant modifier to it, which came with the inherited Reentrancy guard contract. What this non-reentrant modifier does is it prevents bad guys from calling this make item function and then calling back into it before the call to the make item function, the first call that is, has finished. If you want to know more about how reentrancy guards work, you can check out OpenZeppelin's documentation about it right here. Inside the function body, let's check to make sure that the input price is not 0. We can do that using a require statement like so. The require operator first accepts a condition, and if the condition, in this case, price greater than 0, is true, then the rest of the function is executed. And if the condition is false, the function stops executing, and any changes made to the state are reverted. Then for the second input, it accepts EVM revert error message. Next, we're going to transfer the NFT that the user wants to list by calling the transfer from function on the NFT argument, setting the from argument as the account that called this function, the to argument as this contract, and then the token ID argument passed into the function. Next, we're going to add a new item to the items mapping. So we initialize a new item and assign it to the items mapping, setting the key as the item count. We can initialize a struct by calling it like a function, passing in the struct's data fields. For the item ID, we pass the item count, NFT for NFT, token ID for token ID, price for price. Then for the seller, we pass in the account that called the make items function and cast it as payable. For the sold field, we set it to false. Lastly, I want this function to emit an event. Now, an event allows us to log data to the Ethereum blockchain. You can use events as a cheap form of storage or a way to update user interfaces when listened for. So let's go ahead and define an offered event at the top of the contract below this struct. Then we're going to emit it at the bottom of this make item function. So to define an event, first use the event keyword, followed by the name of the event. So offered, then parentheses. And inside of these parentheses is where you define each field of the event. So for the offered event, we're going to log the item ID, the NFT contract, the address of the NFT contract, the token ID, the price of the item, and the address of the seller. And the NFT and seller fields, we're going to set as indexed. This will allow us to search for offered events using the NFT and seller addresses as filters. Then we're going to emit an offered event like this, passing in basically the same data fields as the item struct minus the sold field. And for the NFT instance, we fetch its address by casting it in the address operator. So we're going to describe making marketplace items. And inside of here, let's first create a before each hook that mints an NFT for address 1. And then address 1 approves a marketplace to spend that NFT by calling the set approval for all function on the NFT contract. So why do we need to call the approve function on the marketplace? Well, in order for this transfer from function to work, the caller of the make item function needs to have approved this marketplace contract to transfer their NFT on their behalf. For the first test, let's check for the success case. So it should track newly created item, transfer NFT from seller to marketplace, and emit offered event. First things first, address 1 will offer their freshly minted NFT for sale on the marketplace at a price of 1 Ether by calling the make item function, passing in the NFT address, the token ID, and the price set in way of the NFT they want to sell. So let me briefly explain what way is. You can think of it as the smallest subdivision of Ether, essentially the penny of Ethereum. So if we think of the US dollar, it goes up to 2 decimal places. There's no further subdivision after the penny. But for the Ethereum cryptocurrency, there is 18 decimal places. So that means that 1 Ether is equal to 10 raised to the 18th power way. So that's 1 followed by 18 zeros. And this two-way function that I wrote right here automatically converts Ether into way using the ethers.utils parse ether method. Now, the reason why we have to pass a way value instead of an ether value for the price argument is that you can't represent decimal values in Solidity. You can only represent integers. So we have to represent ether in our smart contracts as its smallest subdivision, way. Moving on, we then check inside the transaction log of this function call to make sure that an offered event was emitted with these arguments. Next, we check that the marketplace is the new owner of the NFT using the owner of function on the NFT contract, passing in the marketplace address. Then we check that the item count on the marketplace is equal to 1. And lastly, we fetch the newly created item from the items mapping on the marketplace contract, passing in a key of 1 to represent item ID 1. Then we check that item ID is equal to 1, NFT is equal to the NFT address, token ID equal to 1, price is equal to the wave value of 1 ether, and sold is equal to false. All right, that just about does it for the success case test. Now let's write a test that handles the failure case. For this test, it should fail if the price is set to 0. That's because if the price is 0, it will not pass this condition set in the require statement of the makeItem function. So we call the makeItems function, passing in a price of 0. Then we expect it to be reverted with this error message: price must be greater than 0, which is the same message emitted by this require statement when this condition fails. All right, and that completes the making marketplace items test. Now let's run the entire test script to make sure that everything is working as it should. So npx HARDHAT test, hit enter. Sweet. Everything passed. All right, now let's implement the final function on the marketplace contract that will allow users to purchase NFTs. So we're going to name the function purchase item. We'll accept as input the item ID that the user wants to purchase. The visibility will be external, and we're going to mark it as payable so that the user that's calling this function can send ether with it. And eventually this ether will be sent to the seller of the item ID and a small portion to the fee account. And we're also going to apply the non-reentrant modifier like we applied to the makeItem function. So before I start coding out the body of this purchase item function, I'm going to write this get total price public function. This function will get the price of an item, the total price of an item. So that's the price of the item set by the seller plus the market fees. And this function will be view because it won't be modifying any state variables. It will only be reading them. And we're going to set the visibility as public because we want to be able to call this function from inside of this purchase item function and from what outside of the contract, because whenever a user wants to buy an item, we need to know how much ether they need to send with the call to the purchase item to cover the price of the item set by the seller plus the market fees. And this function returns that price. So to fetch the total price, we're going to fetch the price of the item from the items mapping, like so. Then we're going to multiply that price by the sum of 100 and the fee percent. And then we're going to wrap this whole thing in a return statement. Sweet. And that completes this get total price function. All right. Now inside of this purchase item function, let's get the total price of the item and assign it to a local variable like so. Next, let's get the item from the items mapping and store it in a variable like this. Since we're creating a variable that's of a complex type, so a type struct, we have to declare the storage location of the variable. So we're going to say that it's from storage, which means that this variable is reading directly from this storage mapping. It's not creating an in-memory copy of the item. Next, we're going to check that the item ID is valid by ensuring that it's greater than 0 and it is less than or equal to the item count. We're also going to make sure that the ether sent with this function call, which we can reference using the global msg.value variable, is greater than or equal to the total price. And for the final require statement, we're going to check that the item that the user wants to purchase has not already been sold. This bang operator evaluates this item.sold to the opposite Boolean value. So if it's not sold and the item.sold outputs false, this whole condition will output to true. But if item.sold is true, then the condition will be false and the function will revert. Next, we're going to pay the seller by calling the transfer method on the seller's address, passing in the price of the item, and then we're going to transfer the fee to the fee account address, passing in the total price minus the item price, which will evaluate to the fee amount. After that, we're going to update the item as sold. Then we're going to transfer the NFT from this address to buyer or the sender of this function call. And we're going to do this by calling the transfer from function on the NFT contract, which we can get from the item struct. And then for the token ID, we pass in the token ID on the item struct. Lastly, we're going to emit a bot event at the bottom of this purchase item function, like we did for the make item function. So we first have to define it like this. The event will have pretty much all the same fields as the offered event, except we're going to add an additional field, which is the buyer. So this is the address that called the purchase item function. We're going to set this buyer field as indexed because when we're building out the user interface, we want to show all of the items that the user has purchased from the marketplace. And we can fetch that data by searching for bot events where the buyer address is equal to the account that's connected to the user interface. We're going to set the item ID as the item ID argument, the NFT as the address of the item's NFT contract, for the token ID, the item's token ID, for the price, the item's price, for the seller, the item seller, and for the buyer, the account that called the purchase item function. Woohoo! And that completes the marketplace contract. Now all we have left to do before we start building out the front end is to test out these two functions inside of this test script. So let's get started on that. So we're going to describe purchasing marketplace items. And like with the previous test for the making marketplace items, we're going to set a before each hook inside of here. Inside the hook, address 1 first mints an NFT, then approves a marketplace to spend that NFT, and then calls the make item function to list it on the marketplace at a price of 2 ether. All right, now let's write the test that handles the success case. It should update item is sold, a seller, transfer NFT to buyer, charge fees, and emit a bot event. First, we need to fetch the initial ETH balances of the seller and the fee account to ensure that each of their balances increases by the appropriate amount after the item has been purchased, we can fetch the signer or the account's ether balance by calling the getBalance method on the signer object. Next, let's fetch the total price of the item by calling the getTotalPrice function on the marketplace contract, passing in 1 for the item ID. After that, address 2 will purchase the item. We can specify the amount of ether we want to send with the call to the purchase item function by passing in a metadata object as the last argument, setting the value property of that object as the total price in way that we fetched earlier. Next, we check inside the transaction log of this call to ensure that a bot event was emitted with the following arguments. We ensure that the item ID is 1, the NFT is the NFT contract address, the token ID is 1, the price of the item is the price we set in way, and the seller is address 1 and the buyer is address 2. Now that we've purchased the item, let's fetch the final ETH balances of the seller and the fee account. Next, let's ensure that the seller's final ETH balance is equal to the seller's initial ETH balance plus the price that they set the item at. We're going to convert the balances from way to ETH because JavaScript does a poor job at adding big numbers together. Whoops, I just noticed that I did not declare this total price in way variable. So let's do that right now. Next, let's calculate the fee by taking the fee percent, dividing it by 100, and multiplying all of that by the price. Then let's check that the final ETH balance of the fee account is equal to the fee account's initial ETH balance plus that fee. Next, let's check that the buyer, which is address 2, is now the new owner of the NFT by calling the owner of function on the NFT contract, passing in the NFT's ID. Lastly, let's check that the sold field for the first item is now equal to true. All right, let's go ahead and run the test really quick to see if we made any errors. Okay, MPX HARDHAT test. Awesome, everything's passing. Alrighty, now let's write the final test for the project, which will test the fail case for the purchasing item function. Essentially, we're going to trigger all 3 of these require statements to ensure that they are working as expected. So we should expect the function to fail for invalid item IDs, purchasing sold items, and when not enough ether is paid. Let's first check that it fails for invalid item IDs. So we're going to call the purchase item function, and we're going to pass a value of 2 for the item ID, which is greater than the item count, which is set to 1. So it should be reverted. And we're going to call the purchase item function again, but this time pass 0 for the item ID, which is less than 1. So it should also be reverted. Next, let's move the total price in way variable declaration outside of the success case test so that it's accessible from within the fail case test right here. Next, let's ensure that it fails when the ether sent with the call is less than the price plus the fee. So in this case, we're only sending in the price of the item that the seller set. So we should expect it to be reverted. Lastly, let's check that it fails when trying to purchase items that have already been sold. So address 2 first purchases item 1, and then the deployer account tries purchasing item 1 after it's been sold. So in that instance, it should be reverted with item already sold. Alrighty, and now we have finished writing the final test for the marketplace contract. So let's go ahead and test it. npx HARDHAT test. Hopefully it works. Sweet, all 7 tests passed. Now we can move on to developing the front end. But first things first, let's go ahead and deploy the completed smart contracts. So in case you forgot, we're going to run npx HARDHAT run source backend scripts deploy.js -- network localhost. Then hit enter. Sweet. So this is a starter kit that we began the project with. It's very bare bones. We haven't done much modification of it. But for the rest of the video, we're going to modify it to create the final product, which is this, the Dapp NFT marketplace. So we're going to turn this into a multi-page app using React routers and connect it to the blockchain and display the account we're connected to the app with at the top of the navbar right here. We have a lot of work cut out for us, so let's get started on all of that right now. So in order for us to connect our app to the blockchain, we first need to connect our browser to the blockchain. We can do that by importing the accounts on our development blockchain into MetaMask. But before you do that, make sure you've added HARDHAT node to the list of available networks on your MetaMask. If you haven't done that yet, go ahead and click this button at the top of your MetaMask. Go down to add network. And then you're going to fill out all these fields with this information. Once you've done that, go back to the terminal tab that's running the local blockchain and copy the private keys for the first 2 accounts. So I'm going to import the private key for this first account into MetaMask, like so. Copy it, click MetaMask, click the circle, click import account, then paste in the private key, then hit import. Boom, and go ahead and do that for the second development account. All right, now that we've connected our browser to the blockchain, let's go ahead and connect our app to it. To do that, open up the app.js file located inside the components directory. First, let's import the ethers.js library like this. This is a library that will allow us to talk to Ethereum nodes, and we've already used it within our tests and deploy scripts to connect to our local dev blockchain, and we're going to use it to do the same thing for our app, except Ethers is going to connect to MetaMask, and MetaMask is already connected to the blockchain, so Ethers will use MetaMask as its Ethereum provider. There are many different types of providers, but the provider offered by MetaMask is called a Web3 provider. So that's the one we're going to connect to. Let's go ahead and create a function inside of the function body of app that handles this connection to MetaMask. We're going to call it Web3 handler. All right, now let's instantiate a new provider from MetaMask by writing new ethers.providers, specifying the type of the provider, Web3 provider, by passing in the window.ethereum object injected into the browser by MetaMask. Let's also fetch the accounts listed in our MetaMask wallet. This line of code will return an array of accounts, and the first account listed represents the account that's connected to the app. We're going to display the address of that account on our navbar, so we need a way to store it. React allows us to store data on the front end, kind of like a mini database, using this useState hook. We're going to use this hook to store the account connected to the app. So this is the way useState works. First, it returns a variable that we can use to reference the stored value, followed by a function that we can use to update this stored value by passing the new value as an argument to it. We also pass to the useState hook itself the default value of the stored variable, so the value of the variable before it's set by the setter function. So we're going to set account to null by default. So let's use the setter function to store the connected account. Next, let's get the signer of the connected account from the provider like this. Awesome. We have set up our connection to the blockchain. The next step is for us to load the contracts from the blockchain. We're going to create a load contracts function that does just that. It's going to take as an argument the signer that we fetched from here, and we're going to call this function at the end of our Web3 handler function. So we're going to fetch deployed copies of the contracts using the ethers.contract method. To get a deployed copy, we have to pass in the contract's address, its API, and a signer. When we ran the deploy script, we saved a copy of each contract's address and API inside of this contract's data folder inside of our front end. So we can import that up here like so. We also need to store each contract into the state of our application using the useState hooks. We also need to keep track of when our app is loading data from the blockchain to know when to display the contents of the app. We're going to set loading from true to false once all the contracts have finished loading. Sweet. We have written the functions that connect us to the blockchain and load the contracts. Next, let's create the Navbar component for our application that will contain a link to all the different routes that we're going to set up, as well as a button to connect our wallet to our application that, when clicked, will trigger this Web3 handler function. So let's get started with that by first deleting the current Navbar and then creating a new file inside of this components directory. We're going to call it navbar.js. Okay. So to speed things along, I'm going to paste in some boilerplate code for this Navbar file. I'm doing this because for the front end portion of this tutorial, I'm mainly focusing on how to connect your client-side website to the blockchain, not how to code out and design the user interface with HTML and CSS. So as I mentioned before, we want our app to route to a new page in our app each time they click one of these navigation links. So I'll demonstrate that by going back to the preview of the finished app. You see that if we click the create link, we get routed to create, and my listed items we get routed to localhost -3001, my listed items, my purchases, same thing. So to configure that, we need to import link from React Router DOM. Then for each nav link element, we set the as attribute to the imported link and the to attribute to a string that corresponds to the route in the URL. We're also going to pass the Web3 handler function an account as props to this navigation component. And if the account is loaded, we're going to display the account's address. And if not, we're going to display a connect wallet button that when clicked will trigger the Web3 handler function. Now let's go back to our app and import the navigation component like so. Then we're going to put the navigation component where the previous navbar used to be, passing in the Web3 handler function and the account as props to it. Next, let's go ahead and set up the different routes for our app inside of this return statement. To do that, we need to import browser router routes route from React Router DOM. First, we need to nest all of this HTML code in the browser router element. Okay. Next, we're going to create a routes element that contains each route below the navigation bar. Next, we're going to create a route element for each of the URL links that we set up in the navbar. Now let's create a new file that will contain the component that will pass into the element attribute for each of these routes inside of this components folder. We're going to create a home component for this path, a create component for this path, a my listed items component for this path, and a my purchases component for this path. Now let's go ahead and import all of these into our app.js file, like so. So one last thing before we start building out the components for each route. To do that, we're going to embed some JavaScript code within this HTML using these red curly braces. Then we're going to check if it's loading, and we use a ternary operator. So if loading is set to true, then we render this, which is a spinner. And if loading is false, then we render the routes. We also need to import spinner from React Bootstrap, like so. All right, now we can start building out the components for the different routes, starting with the home route. So we're going to assign the home component to the element attribute. And for now, we can get rid of these element attributes. We'll fill them in once we get to them. All right, now let's get a quick preview of what our app looks like so far. As you can see, the navbar is rendering. Let's see if the links in the navbar work. Create. Sweet. It routes us to the create URL. My listed items works. My purchases work. Awesome. So let's go ahead and start writing the code for this home component inside of this home.js file. Like with the navbar, I'm going to paste in some boilerplate code to get us started. This home component is going to display all of the listed marketplace items. So we need to fetch the marketplace. So we need to pass in the marketplace contract to fetch all of the listed items, and the NFT contract to fetch the metadata for the associated NFTs. So let's go back to our app and pass in those contracts like so. Moving on, now let's create a function inside the home component that loads marketplace items. We're also going to need to store the items in the application state using the useState hook. Inside the load marketplace items function, let's first fetch the item count from the marketplace contract. Then we're going to initialize an empty items array. Next, we're going to create a for loop that will fetch every single item that was created on the marketplace. Then we create an if statement that checks if the item is unsold. Then we get the URL from the NFT contract for the unsold item by calling the token URI function on the NFT contract, passing the token ID. Then with that URI, use it to fetch the NFT metadata stored on IPFS. We do that using JavaScript's fetch API, passing in the URI. then we get a response, and on that response we call the JSON method, and then that returns the metadata. Then we get the total price of the item by calling the getTotalPrice function on the marketplace. And lastly, we add the item to the items array that we declared up here, calling the push method on it. And we pass in an object with the following properties: the total price, the item ID, the seller, and for the name, we get that from the metadata, the description from the metadata, and the image from the metadata as well. All right. And once we've fetched all the unsold items, then we add them to the state like this. We also want to keep track of when we are loading marketplace items. So we could do that using the useState hook. And then we'll set the loading to false at the end of this load marketplace items function. Next, we're going to create a buy market item function that allows users to buy market items. We'll pass in an item as input. And first, we're going to call the purchase item function on the marketplace, passing in the item ID from the item argument. And for the ether sent with the function call, we'll pass in the items total price. And that's going to return a transaction response. And we're going to call the .wait method on that transaction response. And what that's going to do is it's going to wait for the transaction to be confirmed. And once that happens, we're going to reload the marketplace items, which will remove the recently purchased item from the marketplace, which happens each time the URL path changes from one of these back to home, or when the user presses the refresh button on the home path. All right, now that we've created the function that loads unsold marketplace items and the function that allows users to buy those items, let's build out the user interface that will display the items inside of this return statement. But first, let's return a loading page if the marketplace items has not finished loading from the blockchain. Moving on, inside of the return statement that will display the items, let's first check if the items array length is greater than 0. And if not, then we're going to display that there are no listed assets. Next, we're going to map each item inside the items array to a card that displays the item's associated NFT image, the name of the NFT, the description, as well as the price of the NFT, and a button that you can press to trigger the buy market item function for that particular item. So that's going to look like this. We will display the item's image at the top, followed by the name, description. Then at the footer portion of the card, we will place a button that, when clicked, triggers the buy market item function, passing in the item. And we're also going to display the total price of the item in ETH. So to do that, we need to convert the item.totalPrice from way to ether using the ethers.utils format ether method. Alrighty, and that completes all of the home component. Now let's check out what the app looks like now. So here it is. Let's go ahead and connect our wallet for the first time. Awesome, and it works. So right now it's displaying no listed assets because we haven't called the make item function on the marketplace yet. And really quickly, let's go ahead and center this no listed assets to where it's located right here. We can do that quite easily by returning back to the app.js component, going to this div, and then setting the class name to app. Okay, let's see if that fixed it. It did. Awesome. All right, now let's finish building out the create, my listed items, and my purchases components. All right, now let's start building out the create. All right, now let's start building out the create component. So go ahead and, all right, now let's start building out the create component. So go ahead and open up create.js file. And we're going to paste in some boilerplate code. This time we're going to import the IPFS HTTP client. This will allow us to upload the metadata about the newly created NFT to IPFS. Let's set up the state of the create component. So we're going to need to keep track of the NFT image, its price, the name of the NFT, and its description. The name, description, and image will represent the NFT's metadata, and the price we will store on the blockchain. Now we're going to create an upload to IPFS function that will get triggered each time there's a change to the file input field on the create form. This is the field that users will use to upload the NFT image. So inside of here, we're first going to prevent the default event trigger from happening. And then we're going to fetch the file from the event and then the first element of the files array inside the target. Next, we're going to create an if statement that actually checks that a legitimate file was inputted by checking the type of the file and ensuring that it's not equal to undefined. Then we're going to create a try catch block to potentially catch any errors in the process of uploading the image file to IPFS. And if there is an error, we're going to log that to the console. So to upload the image to IPFS, we simply call the add method on the IPFS client, passing in the file. Then we await for it to return a result. We're going to console.log that. And then we're going to set the image to the link where you can find the image file on IPFS. Next, we're going to write the create NFT function, which will get triggered when the user clicks submit on the create form. This function will first upload all of the NFT metadata to IPFS, which will include the link to where you can find the image on IPFS, the name, and description. And after it's done interacting with IPFS, this function will interact with the blockchain to mint and then list the NFT for sale on the marketplace. First, we're going to check that the image, price, name, and description fields on the create form were all filled out. And if any one of them aren't, then we're going to return. Next, we're going to add a try catch block, just like we did for the upload to IPFS function. So we're going to add the metadata to IPFS in JSON object format by passing an object with the image, name, and description of the NFT to the stringify method. Then we're going to pass all of that to the add method on the IPFS client. We'll wait for the result, and then we're going to pass the result to a function that mints, then lists the NFT. Let's declare that function down here like so. We're going to pass the result to the mint then list function. We're first going to set up the URI URL that points to where the metadata for the NFT is located on IPFS. Then we're going to mint the NFT, passing in that URI data to the mint function. But first, we need to convert the user inputted price in ETH to Wei using the parse ether method, and then setting that to listing price variable. Then we're going to call the make item function on the marketplace, passing the NFT address, NFT's token ID, and the listing price. Alrighty, now we have all the functions we need to create and then list NFTs on the marketplace. Now let's start building out the form that will trigger these functions. The form's going to look like this. So at the top, we're going to have an input field of type file. And this is going to be the field where users will upload their NFT image. And whenever there's a change to this field, we're going to trigger the upload to IPFS function. Then below that, we have the field for the name of the NFT. And when there's a change to it, we're going to trigger the set name function, passing in the name on the input form. We're going to do the same thing for the description, except the input field is going to be of type text area instead of text. And we're going to do something similar for the price field. And the input field is going to be of type number instead of text. Lastly, at the bottom of the form, we're going to have a button that, when clicked, triggers the create NFT function. Awesome. And that completes the create component. Now, let's do one last thing before we check out what our app looks like. Let's go back to the app.js component. We need to pass the create component to the second route for the create path, just like we did for the home component. So we'll do that like this. Now let's take a look at our app. Okay, create. Sweet. Now let's go ahead and test it out. See if we can create and list an NFT that will be displayed on the home component. So let's click choose file. And I'm going to choose gov. We'll say gov majestic and blue for the description. And we'll set it to the price of 3 ETH. Now let's click create and list NFT. Hopefully everything works. Okay. We have the first MetaMask prompt. This is to confirm the transaction to mint the NFT. Okay. The next is to approve the marketplace to spend the NFT. And the last will list the NFT on the marketplace. Hope it works. Okay, let's check the home component. Awesome, woohoo. Here it is. Here's the image of the NFT, description, name, description, and a buy button. Buy for 3.03 ETH. We're displaying the total price of the NFT, so the price set by the seller plus the market fees, just so that users aren't confused when they click the button and they see, wait, I thought the price was set to 3 ETH. Why is it charging me 3.03 ETH? All right, all we have left to do to complete the app is finish building out the My Listed components and the My Purchases component. Both of these components will only read data from the blockchain, not write any data. So building these out will be easier compared to the home and create components. So let's go ahead and open up the My Listed Items file and paste in some boilerplate code. For the My Listed Items component, we're going to pass in the contracts as well as the account that's connected to the app. We need this account in order to filter out the marketplace items that the user has listed. For the state of this component, we're going to track when it's loading, the user's listed items, and of those listed items, which of them have been sold. Next, we're going to define a function that loads all of the user's listed items, and we're going to use the useEffect hook to call this function each time the myListedItems component is mounted. Inside this function, we're first going to get the item count from the marketplace, then declare an empty listed items array and an empty sold items array. Then we will create a for loop that will return every item created in the marketplace. Then we're going to create an if statement that checks if the seller of that item is equal to the account that we passed in. And then we're going to get the URL from the NFT contract and fetch the metadata in the same way we did for the home component. And then we're going to get the total price of the item from the marketplace. Then we're going to define a listed item object, passing in the total price as a property, the price, the item ID, the name, metadata name, description, metadata description, image, metadata image, like we did for the home component. And then we're going to push that item to the listed items array. And if the item has been sold, then we're going to push it to the sold items array. And once we have fetched all the listed items and sold items, then we're going to set loading to false, set listed items, passing in the listed items array that we filled. And for the set sold items, pass in the sold items array that we filled as well. All right, and that's all the data we need to load for this component. So now let's start building out the UI. Like with the home component, we're going to display a loading page if the data is still loading. And once the data is finished loading, we're going to return the listed items right here. But first, we need to check if the listed items array length is greater than 0. And if it isn't, then we're going to return a no listed assets header. When we do have at least one listed item, we're going to display a header at the top center portion of the page that says listed. Then we're going to map through the listed items array. And we're going to, for each item, we're going to display a card similar to how we displayed each item in the home component, except we're just going to display the image of the item as well as the total price in ETH of the item in the card footer. And below the user's listed items, we're also going to render their sold items if they have any sold items by calling this render sold items function. Let's go ahead and define this render sold items function at the top of the file above the myListedItems component right here. We're going to pass the array of sold items to it, render a sold header, and then map through the sold items array, displaying a card for each sold item, like we did for the listed item. But for the footer, in addition to displaying the total price of the item, we're also going to display the price that the seller set the item at. So the price that the user set the item at. And then we're going to say that's the received ETH. Alrighty, and that completes the myListedItems component. Now let's go back to the app.js component and add the myListed component to its corresponding route, like so. Now let's check out how our app looks like. Okay, let's hit the myListedItems. Sweet, awesome. So that NFT we created earlier, we see that it's displayed here as one of our listed items. on the market for a price of 3.03 ETH. All right, now let's try to buy back our NFT to see if the My Listed Items component will show it as a sold item. So go ahead and do that. Buy for 3.03 ETH. This will also test to see if we configured the home component correctly. Let's go ahead and buy it. Confirm. Awesome. So it's been removed from the home page as we expected. Let's see if it's all in the My Listed Items as a sold item. Sweet. Awesome. So it was sold for 3.03 ETH and we received 3.0 ETH. Nice. Okay, let's finish up this tutorial by building out the last component, My Purchases. So go ahead and open up the My Purchases file. I'm going to paste in some boilerplate code. And like with the My Listed Items component, we're going to pass in the contracts and the account connected to the app. We're also going to keep track of the purchases. So these are the items that the user has purchased. And we're going to load them from this function. And we're going to call this function each time the component mounts using the useEffect hook. Next, we're going to fetch purchase items from the marketplace by querying events with the buyer set as a user. So the way we do that is we call the query filter method on the marketplace contract. And then we have to pass in a filter. And this filter defines the specific events we're looking for. And we can create one by calling the filters method on the marketplace contract. And then on the filters, we specify the name of the event we're filtering for, so bot. And then for each of the bot fields, we input the value that we're filtering. If we're not going to filter for a specific field, we set it to null. So we're going to do that for all the fields except the last one, which is the buyer field. We'll set to account. Next, we're going to map through the results array in order to fetch the metadata and total price for each of the purchased items, and then assign the returned array to this purchases variable. Because this results.map method has to potentially perform multiple asynchronous operations, we have to cast it inside the promise.all method in order for us to assign the returned mapped array to this purchases variable. Moving on, inside the asynchronous callback for the map, we get the arguments from each result, and then we get the metadata from IPFS and the total price. Then we define the listed item object, which essentially combines the metadata and blockchain data about the item into a single object. Then we return it. All right, and once we've loaded all of the user's purchased items, we update the state to reflect that. Sweet, now that we've configured this component to load purchased items, let's go ahead and build out the user interface for it. So first we check that the purchases array length is greater than 0, and if not, we display no purchases. If the purchases.length is greater than 0, we map through the purchases array, displaying a card for each purchased item. The card will contain an image of the NFT at the top, and for the footer, the price that the user purchased the NFT for. Okay, and that's it. We have coded out all of the different components that make up our application. So the last thing we need to do, go to this our app.js file, and then add the My Purchases component to the final route right here, like so. Okay, save it. Now let's check out the completed app. Hopefully everything works as expected. refresh the page, connect it, home page, no listed asset, create, my listed items, okay. My purchases, awesome, awesome. So the NFT that we created and then purchased back for ourselves is listed in the purchases page, and it's also listed in the my listed page because we were the ones who listed it, and technically it was sold, but we were the buyers. So yeah, it looks like everything is working as it should, and of course there's no more available assets on the marketplace to buy. So yeah, that's to be expected. All right, there we have it. That's the completed project. You have successfully created Dapp NFT Marketplace, where you can create NFTs to be listed on the marketplace, buy them, and view the NFTs you've listed, the ones that have sold, and the NFTs you've purchased. You should give yourself a huge pat on your back. You have come a very long way since the beginning of this tutorial. You learned about blockchain, smart contracts, how to build an NFT contract, a marketplace contract, how to write tests against them to ensure that they are working as you expect them to, and how to build a client-side application in React.js that connects to the blockchain. There are a few ways you can improve upon this project. For instance, you could make it support multiple different NFT collections. You could also make it such that each NFT listed for sale, the price is not fixed. It counts down, sort of like in a Dutch auction type style. If you're trying to become a professional blockchain developer, you can add one of the features I just mentioned to this project, then showcase it on your portfolio. So if you want to check out this project's entire source code, the link to it is in the description down below.
So we're going to create a decentralized domain name marketplace called ETHDaddy, where you can list your blockchain-based domain names and other people can buy them with their MetaMask wallet, okay? So let's, talk about this. So, basically, this is obviously heavily inspired by GoDaddy. Okay, you can kind of see the similarities here. So GoDaddy is one of the most popular domain registrars online, where you can register new domain names, buy for them, renew them, all that type of stuff. But, and you can think about going back in time and buying a bunch of, domain names that were popular in the early Web 2 days before other people knew about them. Like, what if you had purchased a domain name for Instagram.com, back in 2011 or something like that, or even before the 2010s? That'd be insanely worth, it'd be worth a lot more money today, of course. And so, some of the things happening in blockchain, because we have blockchain-based domain names. The most popular services for this is ENS, okay? So essentially, think about your MetaMask wallet, for example. It has a really long, hard-to-read address, okay? If I told you where to send money and I tried to tell you what this address from start to finish, you wouldn't be able to remember it and put it down. But that's what, ENS is for. You can get a human-readable domain name for your blockchain wallet. If I said, hey, send me, money to yourname.eth, like jack.eth or john.eth, you'd know exactly where to send that. There'd be no real anything lost in translation. It'd be easy to remember. And so that's what we're doing here. We're basically creating something kind of like ENS. Okay, so it's heavily inspired by ENS, but also heavily inspired by GoDaddy. Okay, all in one place for this blockchain-based domain name marketplace. And one other thing I meant to mention is that this decentralized domain name marketplace is going to be completely powered by NFTs, okay? So just a quick recap on NFTs. These are just non-fungible tokens. So, you might think of NFTs as crypto collectibles. That's one of the most popular use cases. But there's so many other things you can do with non-fungible tokens besides just, digital pictures on a blockchain. You can also, represent any type of collection where the items in the collection are unique. And that's, domain names are a pretty good example of that use case. And so ENS domains is powered by NFTs, and our domains that we're going to list on our domain registrar website or our domain name marketplace, ETHDaddy, is also going to be powered by NFTs using the ERC 721 non-fungible token standard. All right, so let's go ahead and start coding. The first thing we need to do is get the project set up. So I've put a link to this code down in the description below. All right, so go ahead and grab this URL. All right, go to your terminal and type in git clone, all right, -b, starter code, starter_code, and then paste in that URL right after it and hit enter. Okay, so what this does is, this is a GitHub repository right here. And when you look at the final code for this application, this is the master branch, because Git supports branches. You can see them here. There's a master branch, and then there's a starter code branch, which basically sets the project up for us quickly without providing the final code solution. So I wanted to have that in this tutorial today, so we don't have to go through like HARDHAT setup, blah, 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 blah. I want to go straight to coding as fast as possible, and that's exactly what we're going to do. So we're cloning a specific branch whenever you run that command. If you had not done the -b starter code, it would just pull down the entire, master branch with the final code solution. And instead of doing that, it just pulls down the starting point. Okay. So, so now let's enter into that newly created directory. We can just say cd ETHDaddy. Okay. And so you can see we're on the starter code branch right here, not the master branch. So I'm going to go ahead and open this up in my text editor. I'm using Sublime Text. You can use whatever text editor you'd like. And I can see all my code for the project inside of here, right? It's got its README file. It's got a package.json. Okay. We got a place to write our tests. It's already set up for us. A place for our smart contracts. Okay. Our application. All right. All that type of stuff. Okay. So let's go ahead and start setting everything up in terms of our dependencies. So let's first of all talk about the dependencies that we need. You, of course, need, let's see here. The basic dependency is just going to be Node.js. That's the only thing you have to have installed in your system, because we're going to install all of the packages with Node.js. So make sure that you've got Node installed already on your computer. I'm using, which Node version? Let's see here. I'm using Node version 14.16.0. So if you want to make sure that you have the exact same results as what I have on screen, then make sure you use that exact Node version. Now, if you're an experienced developer and you know how to switch Node versions and you're pretty sure that yours is going to work, that's totally fine. But if you want to have as few variables as possible, I highly recommend using the exact same one. Okay. So now that we have that installed, well, that and the only other real dependency that you have to install manually is going to be MetaMask. Okay. So MetaMask, of course, is an Ethereum wallet, a blockchain wallet that connects our web browser to the blockchain, because web browsers don't support blockchain connectivity out of the box in most cases. And you need to have a place to store your wallet to hold cryptocurrency to pay for transaction fees. Okay, so just make sure you have Node.js installed. Make sure you have MetaMask installed. You can find this in the Google Chrome App Store. I highly recommend using Chrome as your browser in this case. Okay, so those are the only two manual things. Now, with Node.js, we can install everything else. Okay. We can install HARDHAT, which is our smart contract development framework. So HARDHAT lets us create smart contracts. It lets us write tests. It lets us write scripts for deployment, all that type of stuff, and so much more. We also need to install Ethers.js, which is the JavaScript library that's going to let us, basically connect our front-end application to the blockchain itself. And we also need to install stuff like React.js, okay? And React is going to be the front-end framework for creating our website that we'll use for this domain name marketplace, okay? So the good news is we can install all of those with our package.json file as developer dependencies, because we installed Node.js, and it'll automatically pull down all this stuff for us. We don't have to install it manually, just directly from our package.json file, and then run all our commands with npx instead of using the global npm dependencies. It's really nice to keep everything contained in the project that way. That way, I know that we're all using the same dependencies and we can all run the same commands without having to worry about any differences, okay? So we can usually just install those directly with the npm install command, but there's one quick change here, okay? We need to update our package.json file. So on that URL down below, click on this, make sure you're on this master branch right here, and then go to the package.json file and then click raw. All right. And then just highlight everything and copy it and replace whatever in your package.json file on your starter code branch with this code. All right. So unfortunately, I had to do some debugging and update these dependencies on the master branch before we created the starter branch, or sorry, after we created the starter branch, and instead of having to try to merge that in a backwards way, this is just the fastest, easiest way. So the source of truth for the package.json file is definitely going to be this, one on the master branch. So make sure what you're starting off with is exactly what's here in the final code solution. So that's an unfortunate consequence of this development process, but hey, just make sure you got the same package.json file. Once you do that, you can just install your dependencies like this. Just say npm install. All right, and everything should go smoothly. All right, so now that that is finished installing, let's go ahead and start working on the code. Okay, so again, we're going to do this inside of a project here, okay, that's got a HARDHAT project, okay, and it's also got, a React project inside of it as well. Whenever we did that starter branch code, we got some placeholders for free. So if you look inside the contracts directory, we already have the file for our first smart contract called ethdaddy.sol. Okay, this is the Solidity smart contract code. We just got this empty smart contract, say contract ethdaddy inside of here. We'll fill out all the code inside this file. Okay, we've also got some other placeholders like our tests. Okay, we'll write some tests for the smart contract. We'll see that in a second. We've got a deployment script, a placeholder, all that type of stuff. Okay, so let's just start off with a basic smoke test for the smart contract, this ethdaddy sol. Just to see that everything works properly, okay? And then we'll get it set up, all right? So what we're gonna do is go ahead and start writing the code inside this smart contract. So these curly braces, go ahead and put your mouse inside of here and hit enter to break this onto a new line, okay? So this is how you create smart contracts. This is your first one ever. You start off with the contract keyword, okay? And then you give it the name of the smart contract. In this case, that's ethdaddy, so capital ETH, capital D for daddy. All right, and then you put all of the code for the smart contract inside of here. So the first thing we're going to do is create a state variable, okay? So what is that? Well, basically, it's just a variable that's going to get saved to the blockchain, okay? And we can read that variable anywhere inside of our smart contract. And what we're going to do is just create a basic name for the smart contract saved to a variable. We can read that outside the smart contract, which we'll check here in a second. That'll help us just make sure that our project is set up properly. So we create our first state variable like this. We say string public, okay, name, okay. And then what we're going to do, let me just start there. So basically, what is this? This is how you create a state variable. So basically, Solidity is a statically typed language, which means that you have to give it the data type of the variable whenever you create it. So in this case, it's a string, which is just a set of characters that are put inside of quotation marks that you can run together, like words or sentences, for example. And then public is a visibility of this variable. Basically, this tells Solidity, can you actually read this variable outside the smart contract? Well, it's public, so yes, and Solidity is actually going to give us a function for free called name, which is the name of the variable right here, and then we can read the value of this variable name outside of the smart contract. So that's the last thing I want to do is put an equal sign here and actually assign it to the string ethdaddy. Okay, and that's going to essentially give us a name for the smart contract, and now we can check for this to make sure that it's set up properly. So we're going to develop this smart contract by writing tests simultaneously. As we're writing the smart contract code, we're going to write tests in JavaScript to just check that everything works properly. All right, so you can go to your test folder here, and you can look at ethdaddy.js. So this is a test file where we can write tests in JavaScript to make sure that our Solidity code works. So I'm going to put these in new panels. Okay, and then I'm going to kill the sidebar here, and here what I have is my Solidity code on the left side, and I've got my tests here on the right side. So let's talk quickly about testing. So basically, testing is not something that's specific to blockchain development if you're brand new. Testing happens in pretty much every aspect of software development, where you write code that's supposed to do stuff, and then you write tests that check that your code actually works properly as you expect. Now, this is particularly important with smart contracts because, the development lifecycle for smart contracts is a little bit different from most Web 2.0 applications. A lot of the philosophy of Web 2.0 applications is basically get something that works good enough and then just ship it as fast as possible. because you can update the code later, all right, and fix any bugs that you might run into whenever users actually interact with the application. Now, smart contract development is significantly different because, smart contracts by default are immutable, which means the code cannot change, okay? So basically, you want to really make sure that the smart contract works properly before you put it out there, because really you shouldn't be able to update the actual contract that you deploy the first time. And the other factor is a lot of smart contracts hold money, they hold value, and the consequence of a bug is, potentially millions, if not billions of dollars, if a bug is found in production. So for those two reasons, testing is high, is paramount with smart contract development, even more so than, Web 2.0 development or maybe mobile development or some other type, right? So anyways, how do we test with smart contracts? Well, basically, we write our Solidity code in the Solidity programming language, but the way that most developers do it is they write tests in a different programming language, JavaScript. That's what we're doing over here. And with HARDHAT, we have some libraries that we can use that are included, all right, out of the box. So this is another library. Let me just pull up the one that I want here. Give me 1 second. Okay, we can use the Mocha testing framework and the Chai assertion library. All right, let's pull those up on my screen here. So Mocha is basically a framework that lets you write tests in JavaScript, and Chai is an assertion library that lets you put these matchers and inside of your code. So we can see that Chai is already imported here at the top of the file. Mocha is already kind of baked into HARDHAT. We have a tokens helper inside of here. All right, this is something that I just hand rolled that helps convert your cryptocurrency to tokens. And then we also have this describe function that's describing ETHEREUM, which is the contract name that we're testing over here. So describe is going to be our main function that contains our tests, okay? And inside the, describe, we can write individual test examples like this. We can just say it, has a name. All right, and then we can do this function. And then we can basically just say, we can fetch the smart contract from the blockchain like this. We can just say const ETHDaddy equals await ethers get contract factory. And then ETHDaddy. Just pull this over here. And then we can get the deployed copy of it. ETHDaddy equals await ETHDaddy.deploy. All right. And then we can say let ETHDaddy. And then we can say const result equals await ETHDaddy.name. And then we can say expect results to equal, let's see, our name over here is ETHDaddy. Let's just copy it. I know it's kind of deterministic. It's not the best way to test, but hey, let's just get it up and running fast. So then we can run this test, see if it works with npx hardhat run, or npx hardhat test, sorry. That's how you run tests in HARDHAT. Okay, so we got a little bit of an issue here. This is await is only invalid in async function, so this needs to be async. Okay. Oh, sorry. All right, try that again. All right, so it works. So let's talk about what we did here. So again, describe is just contains all the tests inside of this function. It is just what you use for test examples. And we're saying it has a name. Okay, and then what we're doing here is we're saying const ETHDaddy equals await ethers get contract factory. That's basically getting the JavaScript version of the smart contract with the ethers.js library. We're deploying it to the blockchain right here because this isn't deployed yet. All right. We're assigning it to a variable once it's deployed to a blockchain. And then once we have that JavaScript version of the contract saved to this variable, we can call its functions. Okay, so we said here, ETHDaddy, which is now the JavaScript version of the smart contract, has a function called name, okay, which because we set this string public name over here, This is a state variable, but Solidity also gives us a function called name because we use this public visibility here. It exposes a special function called name for free so that you can access this variable value. And so we just called that function that Solidity gave us for free. We assigned the result here, and then we checked the result. We said expect result to equal ETHDaddy, which is the string that we set here, and it works. Okay, so that's basically our smoke test to make sure that everything's set up properly. All right, so now that that's done, let's start coding out the NFT smart contract. Okay, so let's explain what it does and how it works so that we can, code this out successfully. So here's a diagram of basically what we're going to do. So, our website, let me just pull up my diagram here. Our website is a domain name marketplace. So this is a website that's going to talk directly to the blockchain. It's going to talk to a smart contract that we're coding right now. All right, we're actually coding the smart contract that's going to power this website. And so what it does is it basically lets people list the NFTs and then purchase them. All right, and then the creator of the domain name marketplace can receive the funds for these. Okay, they can also list the NFTs, and I guess the NFT owner essentially receives the money for this. Okay, so let's talk about what this does, because this is all going to happen in the same smart contract. So I'm going to show this on my screen here. So the diagram looks like this. Basically, you have a user who's got their MetaMask wallet that's connected to the browser. Browser talks to the website talks to the blockchain, and on the blockchain is this NFT contract. And so the NFT contract, what it's going to do is it's going to create all the domain names from scratch. It's going to mint them. Okay, that's what NFT minting is. You create a smart contract that handles all the domains. And it starts off with 0. It mints them from scratch. Okay, and then those can be minted to an individual's wallet so they can own them. And then those domain names can be listed on the smart contract marketplace, because it's gonna be an NFT contract and a marketplace all in one contract. Okay, it's kind of blending the two concepts. And so once someone has the NFT, they can list it, directly on the smart contract. Okay, and then someone else can come to the smart contract and then buy the NFTs from the collection on that same smart contract as well. And then the ether goes to the domain name, creator or holder in this case. And now I know that's a lot of concepts all at once, but I think it'll become clear as we create this step by step exactly how this works. I think the best way to approach this is to just build one piece at a time, do this step by step, and it'll all start to click as we go through it. Okay. So one other quick thing that I want to mention is that, because we're creating an NFT here for our domain names, I want you to understand that NFTs follow a standard. Okay. So most NFTs follow the ERC 721 standard, which is basically just a set of rules that determines how an NFT should work so that it's compatible with things like, crypto wallets. It's compatible with different NFT marketplaces like OpenSea, for example. All right. So you can see this. This is a standard that's been around for a while. It basically just says what functions are you supposed to have on it, right? So, and then what type of behavior those functions should have, and the types of events that are triggered inside the smart contract as well. Okay. So you can see this, like, basically every NFT that follows the ERC 721 standard should have a balance of function, should have an owner of function. You should be able to send NFTs from one account to another with this transfer from. You should be able to approve the NFTs so that people can spend them. All right, all that type of stuff. It should have these transfer events, approval events, so that you can see all the history and also get alerts in real time for these types of operations. Okay. So we're gonna create an ERC 721 compliant token in this video. But what you want to do, instead of creating all this from scratch, okay, we don't want to reinvent the wheel. So we're going to use the OpenZeppelin library for this. So what is it? OpenZeppelin is an open source library that contains lots of different common smart contracts that you can use to create your project quickly. And they're also, community audited and community, battle tested in production, so that that they're, more or less probably safe to use. Okay. Now, I'm not saying that, I'm not warranting this for any, production project to say that if you use this, it's, guaranteed to work with no bugs. But the likelihood of you creating your own bug versus them creating their own bug is, that's pretty different probability there. So anyways, we're going to use this ERC-721 library from OpenZeppelin, mostly so that we don't have to create an NFT from scratch. And then we can customize it with all of our additional behavior inside of our smart contracts. So we'll do plenty of coding on our own, but we're going to use this to get started so that we can, do the important stuff ourselves and not the boring stuff. So let's go to our package.json file. You can see we've already got OpenZeppelin contracts in our project. We don't need to install anything, but we do need to import the contract at the top of our file here. So what we're going to do is at the top of the file, we're going to put this line here. So import OpenZeppelin contracts token ERC-721. All right. If you don't want to copy that by hand, you can look at it in the documentation here. They should have some instructions on how to do that. You can also just look at the final, code solution here. All right. On the final project, and you can see that line right here too. Now, I don't recommend copying everything, but if you want to just get that so that you don't have any issues, then basically do that. So you can make sure that that worked. You can always, make a change and then run your test just to make sure their code still works. All right, it still worked, compiled, because what you have to understand is you have to compile Solidity smart contracts before you run the tests, and you can see that it compiled them, and it started compiling more contracts because it just pulled in these OpenZeppelin contracts to our project. Okay. So the first thing we want to do is basically, wire this up to create an NFT. So we've imported this, but how do we actually inherit the behavior from this library? Okay. Because if you look here, you can look at the code. If you search for ERC-721 in your files, you should find this in your node modules. Here's basically this big old Solidity contract that we're going to get for free. That's dependent upon a bunch of other smart contracts. Okay. So how do we get all this into our contract here? Well, we've imported the file, but we're not, we haven't used it as a plugin, so to speak, in our contract yet. So what you have to do is inherit from this particular contract. So we've imported a contract called ERC-721. So we can inherit from that smart contract with our ETHEREUM contract like this. We can say contract ETHEREUM is ERC-721. All right. And then that is going to basically get all the behavior in our ETHEREUM contract. Now let's run the test and see what happens. I think they're going to fail. Yeah. Okay. So compilation failed. So why is that? So you can see it's yelling at us. I'm not going to try to explain these error messages. I know what it is because this has a conflict right here, but I don't want to get into the details. I'll just give away the solution. So basically, with this, you can see here that the ERC-721 file that we're inheriting from has a constructor function. So basically, we need to create our own constructor function and then pass in the constructor function from here. Now, let's kind of back up for a second. All right, let me explain what the constructor function is. So what I'm going to do is basically take away this. Okay, we're going to come back to that in a second, and I'm backpedaling here. But let's talk about the constructor function before we wire that up. So Solidity has a special function called constructor that's basically run once and only once. That's whenever you deploy the contract to the blockchain. Okay, so you can create a constructor called this, and you can set values inside of here. So for example, we could do this constructor function as we could take this ETHDaddy, all right, take it out here, and then we could set the name inside of here. We could say name equals ETHDaddy. All right, let's run the test again. All right, they still pass. So if you're going to do that, make sure you take off the inheritance line because it's going to fail. So what we want to do is basically set the name ETHDaddy, all right, but we want to set it with the library because one thing you'll notice about the ERC-721 tokens is they have a name state variable inside of it. They have a symbol state variable because, ERC-721 tokens have names and symbols, okay? So we had a name here, so let's go ahead and take it out. And let's set the name and the symbol from ERC-721. Okay, so we're going to put our thing back, say is ERC 721. And instead of saying constructor name like this, what we're going to do is basically pass in a name to the other smart contract. So basically how we do that is we're going to say, we're going to pass in this to our constructor, name, and string, memory, symbol. Okay, so these are constructor arguments that we can pass in. And actually, let's do this way. Let's do this way. Let's take this off again. I know I'm kind of backpedaling, but this is a good teaching moment, so I want to make sure I capture this. Okay, so let's kind of revert a little bit. All right, sorry everybody. Let's just do this. We've imported our thing, but we have contract ETHEREUM. We have string public name. Let's go ahead and do the same thing for symbol. All right, it's a good teaching moment. And we're going to do this. We're going to say, is this ETHD? Okay. And then we're going to just keep our constructor blank for now. Let's run the test again, just make sure it still passes. Okay. But now we're going to do is say, we're going to copy this line. And say result equals await ETHEREUM name. Expect the result to be named this. Let's also just check the name. Let's check the symbol. Okay. And we'll change this and say symbol and say ETHD. And let's run the test again. So it says a const, let's do let. Okay. All right. All right, so you see that's passing. And I'll let you pause the video if you want to copy the exact code that's on the right side there. All right, then also the left side. Okay, so what I want to show you is we can have our own name and symbol inside of here, okay? But what we really want to do is store the name and symbol in the library, okay? So that's why I wanted to, do this. So first of all, let's kind of do that incrementally. Now, what I'll show you is the constructor function can take arguments. So we can do string, memory, name, and then string memory, symbol. Okay, so string is data type, memory is the location, name is the name of the argument. So these two different function arguments, okay, name and symbol. And I can store those in name equals underscore name. And then symbol equals underscore symbol. Okay. And then I'm going to take these off of here. All right, similar to this. And then I'm going to pass them in here. So I'm going to say in the deployment function, I'm going to say, I'm just going to pass a name as ETHDaddy. And then symbol as ETHD. All right, then run the test again. All right, they pass. So now let's actually pull in the import, the library. So what I'm going to do here is say is ERC 721. I'm going to remove my state variables because they're going to get stored in the state variables for the library here. But you see the constructor function takes a name and a symbol. So we're going to likewise take a name and a symbol here. But what we're going to do is actually pass them into this constructor. So we'll take these out here. And what we'll do is we can do that like this. We just put the contract name here, ERC 721. And then we do open and close parentheses. And then we just pass along these arguments into its constructor like this. Okay. So basically we just say name and then symbol. We just pass them directly here. All right. And then we don't put anything inside the constructor function yet. Let's do npx HARDHAT test. And then boom, still works. Okay. So now we'll do a little bit of refactoring. I want to format this constructor function because it's taking up, it's really long. So what I'm going to do is just break this up on this new line here. And then I'm going to move this onto a new line. All right. And that is going to say, add code here. All right. Now let's do that. Let's run the test again. All right. It still passes. Perfect. So basically now we're saving the name and symbol inside of the actual library itself. That's one of the good reasons to write tests, is you know the code still works. And it saves you a lot of time. Like if you did this on a remix and you're sitting there pasting your contract code in, making changes, you got to hand test stuff all the time. That's another big benefit of testing, is it can speed up the development process whenever you're making changes, especially if you have a lot of behavior, okay? So, yeah, there you go. It has a name. And so it also has a symbol. So now let's refactor our tests a little bit. What I'm going to do is essentially, this, you know, we see this has a name is all inside of one example, but we're all sticking the symbol. All right, so what we want to do is have a different test. So we could say has a name. All right, and then say, you know, it has a symbol. All right, and I've copy and pasted these, but I want to take the name out of here and then take the symbol out of here. Okay, and now I can run the test again. I can see it still passes. Okay, now it has two examples. It has a name, has a symbol. All right, that checks for each of those. But here you can see a problem. You know, we have to deploy the smart contract each time inside of each of these test examples. That's duplication. That's kind of a code smell. It's bad practice. We don't want to have copy and pasted code inside of our file here that's duplicated. So how can we avoid that problem? Well, we can use something called a before each. Okay, so inside of our testing framework here, we can say before each. And what it's going to do is run some code before each of these test examples. Then we can basically do this inside of here, and we don't have to copy and paste it into each test example. So we can say async. Okay. And then basically we can do this. And then do this. And now that we've done that, we want to say let results, or we can say const. Okay. And then instead of do let ETHEREUM here, we want to do let ETHEREUM here. And now we should be able to save this and access it everywhere else. And so let's run the test and see if it still passes. Okay, awesome. Now, one more thing I want to do is we're going to write multiple test cases throughout this entire file, and I want to group them into logical groupings. So I'm going to put both of these examples inside of here, describe deployment. Okay, and then what I'm going to do is basically do this, and then I can put all the examples for deployment, just the basic, you know, the constructor function, what it does. I can put those inside of here. So you could call this, you know, describe constructor, right? I'm just calling it deployment because that's really the behavior that I'm checking. But notice that all I'm doing is checking what's actually set inside the constructor function, okay? Because then we can describe other, you know, cases like listing NFTs, minting NFTs, you know, grouped by the behavior itself. So let's do that. Let's run the tests, see if it still passes. All right, so now you can see it also really organizes things nicely in our test suite. You can say, here's the contract name, here's the deployment, it has a name, has a symbol, both of those pass just fine. Okay, so a couple of things I want to do here is I'm going to take this name, I want to set it to a constant, say const name, because we're going to reference this again, and we can just say const name equals ETHEREUM, and I can reference this as name here. I can also say const symbol equals ETHD, and then put symbol here. All right, let's run our test again. Yep, they still pass. All right, and so now what I want to do here is essentially create a way for the NFT developer to receive money whenever the NFTs are purchased, okay? So let's just take a quick understanding of that. So basically, let me just pull it up on my screen here. Basically, you know, whenever somebody comes to purchase the domains, what's going to happen is the developer's going to list them on the contract and the website. And when someone buys it, it's going to mint the NFT directly to their wallet. And then the developer is going to get paid for doing that. So we need to keep track of the developer. So inside of Solidity, we can keep track of the developer with a state variable called owner. We can say address public owner. All right. And then basically we can set the owner here. So inside Solidity, we have a global variable called message. All right. And then that has a property called owner. Sorry, not owner, sender. Okay. So basically, this is going to be the person who called this function, in this case, the deployer, because that's who's creating the contract and putting it in the blockchain. And we can basically just say owner equals message.sender, because this is the person who's calling the constructor function, who's deploying the contract to the blockchain. And then we can keep track of that in the state variable here. And we will, reference this person's address whenever we want to, transfer funds and do things like list domains. Okay. So let's finally check for the owner inside of the tests. So what I'm going to do here is, inside the before each, what we want to do is get all of the addresses that are associated with our smart contracts. Sorry, associated with the HARDHAT setup. So we can get all of the addresses from the HARDHAT environment like this. We could say await ethers, get signers. Okay, so a signer is basically just an object that contains the wallets of the users in this case. And so what I'm going to show you here is essentially whenever we're doing the test, like behind the scenes, let me just do this, npx HARDHAT node. So you don't need to do this. I'm just going to show it for demonstration purposes. HARDHAT has a test blockchain that basically gives you 20 accounts for free, and they all have addresses and private keys, and they all have, fake ether, 10,000 fake ether. So behind the scenes, HARDHAT's spinning up this blockchain whenever it runs the tests, okay? So we have 20 accounts that we have access to, and we can pull them out one by one. So basically what I can do is I can do await ethers get signers. I can show you that. I can just say const signers. All right, and then I can do console.log signers. And you can see that in the terminal whenever I run the tests here. If I run the tests again here, sorry, I misspelled that. All right, you can see they're logged. I can do get signers, dot length. You can see that there's in fact 20 signers. It's an array, so I can do signers, 0 to get the first signer. All right, here's an entire object, but I can do get signers.0.address. All right, and you can see here's the address, right? And you can see that's done twice because before each, it runs before each test example. Okay. And so what I can do is I can access each one, right? I can see signers, 1, signers 0, and it'll show me a different address each time I do that. So here's 0, here's 1, so we can list these. So basically what I'm going to do is I'm going to set up some different accounts in a test scenario because we want to find the owner, okay? So basically what I'm going to do here is set up some accounts like this. I'm going to say const. Well, let's set up two things here. So let ETHEREUM will also say let's deployer. This will be the deployer of the contract, and then owner 1. These will be 2 fake accounts, and we're going to set those up here. So instead of const get signers, we can break this apart in JavaScript like this. We can say deployer, and then owner 1. And because because get signers returns an array, we can just get the first 2 elements out of the array like this and save them to variables called deployer and owner 1. All right, now we've got these signers here, and we can also say deploy contract here. And then inside of here, we can also say, it has a name, it has a symbol. We can do it sets the owner. Okay, so we say result equals await ETHEREUM owner, and say expect result to equal deployer, which is this, which we saved here, dot address. Or make sure you call dot address on it because you want to get the actual address, not the entire signer object. So let's run npx HARDHAT tests, and boom, it passes. All right, so now let's start coding out a lot of the functionality of the smart contract. We've set everything up. We've inherited. We've got an ERC721 token. We got a name. We got a symbol. We got an owner. But there's, a couple of core pieces of functionality that we want to do here. So basically, let's put these in here. We'll say to do. We're going to do 1, list domains. Number 2, we want to buy domains. And number 3, we want to get paid our fees for whenever somebody purchases the domain. So let's work on step number 1, which is list domains right here. Okay, I'm just gonna put this separate file so we don't clutter up the smart contract here. All right, let's just do that. All right, I'm trying to get it to go over so it's not indented so much, but yeah, boom, there you go. That's what we need to do. All right. Okay, so to list the domains, we need to first create a way to track a domain inside of the smart contract itself. So what are we going to do? Well, we're going to create a function for listing domains. All right, so let's go ahead and do that. Say function lists. All right, so that's how you create a function. That's Solidity. Use the function keyword. You give it your name here. All right, then you put all of the code for the function inside of here. Just say code goes here. Okay. And so what we're going to do is make this visible to the public. So I say public. That's the visibility of the Solidity function, just like we did with this state variable owner and also the other ones here. All right, so that means we can call this function outside the smart contract. And what we're going to do when we list a domain name is we want to give it a name. So string memory name. That's the domain name, like, you know, gregory.eth, okay? Or uint 256 cost. All right, so basically we want to store the name of the domain and how much it's going to cost. And that's what we can see here on our mock-up. I'll save the screenshot here. You can see this, jack.eth, john.eth. We're going to say, hey, we're listing john.eth here. I'll pull it up so you can see it. And then actually, I think the old site's running. Let's just see it. Okay, like, john.eth, henry.eth, here's the cost. 225 ETH, and then click buy, right? So that's what we're going to do. We create a list, and the code for that list is going to go inside of here. Now, let me explain how this is going to work. So going back to our diagram here, there's several different things we can do. We can list NFTs, someone else can buy them, and then we can get paid when someone else buys the domain names that we created. So whenever we list the domains, we're not actually creating the NFTs just yet, all right? We're basically just saying, here's the NFTs that you are allowed to create. That's what the listing is going to be. And then when the end user comes to the website and buys them, they're actually going to mint the NFTs from scratch, okay? So basically, another way of saying that is when you go to this website, I demoed this earlier where I bought, jack.eth. Okay, now it's owned by this wallet. All right. And then you can see john.eth is for sale. So in this case, let's say this is a brand new smart contract. These 1, 2, 3, 4, 5 domain names have been listed, but they really haven't been created yet. All right. They only get created when someone buys them. Okay. And then in this case, there's 1, 2, 3, 4, 5, 6 domain names. Only one has been purchased. So only one actually exists, but there's 5 others that are listed but don't exist yet because no one has purchased them yet. So they only get created when someone else buys them. It's kind of like other NFT websites where you go to a drop and people mint them from scratch. They're only minted whenever someone actually buys them. It's the same case for this particular example, just to simplify things. It gets a little bit confusing, but it actually makes it a lot simpler. So now that we're going to list the NFTs, we need to basically create a way to store the potential domain names you can buy inside the smart contract. So what we're going to do is basically create, we need to model a domain. Main. We need to save the domain. And then, update total domain count. All right. So how are we going to model a domain? Well, we can use something called a struct. So the cool thing about Solidity is it lets you create your own, whatever data type you want to, custom data structures with structs. So you can say struct domain. All right. Then you can give it all these properties. So we can give it a string name. All right. We can give it a uint 256 cost, and then bool is owned. All right. So basically we're saying we're going to create this thing called a domain, which doesn't exist in Solidity, but Solidity lets us use a struct to do that. And we can give it, arbitrary properties. In this case, string is just a string like we saw here. Cost is uint 256. So what is uint 256? Well, uint stands for unsigned integer. So that's basically a number that's not negative. That's what signed means. So it's unsigned. All right, that's going to be the ether cost expressed in way. And the bool is just a Boolean value, which is just true or false. All right, so those are the data types. So name is string, uint is cost, and then is owned is a Boolean. All right. So that's the struct for how we're going to model each domain. Now, that's not creating a domain. That's just defining what a domain name looks like. Okay. So how do we actually create a domain? Well, we're going to do that inside of our function. And I say create a domain. We're going to add it to our list of domains, not actually minting the NFT yet. But we'll see that in practice as we go on. So we've modeled domain, checkbox, we've done that. All right, so now let's save the domain. So in order to do that, we can actually create a domain name struct like this. We just use a domain keyword that we created, domain, and we pass in the values. So the name is going to come from here. So this name is going to be the name here. All right, and then the cost is going to be this cost that's passed in from the function costs, and then is it owned? It's false. So basically, this is just going to say, hey, here's a domain that's for sale. No one's bought it yet, so it's not owned. And here's the name and the cost. Okay. So now that instantiates the domain name inside this function, but now we need a way to save it. All right. So how are we going to do that? We're going to use something called a mapping inside Solidity. All right, so I'll just type it on screen, and then I'll explain how it works. All right, so a mapping, it looks like this. All right, you use mapping keyword, you use open and close parentheses, and then you say the data type of the key, which is uint256, and then this little hash rocket, and then you say domain as the struct here, and then you give it a name, so domains, okay. So let me explain what a mapping is. So mapping is a key value pair inside Solidity that's saved to the blockchain because it's a state variable. So basically what it does is it gives it a key value pair. So a key is going to be an unsigned integer. So this is a number like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, et cetera, et cetera, et cetera. And then the value is going to be a domain itself. And then we can save it as a domain's variable. Okay. So you can kind of treat this like a database. All right, because this is saved to the blockchain because it's a state variable. And then basically you have a little domains table, kind of, if you come from a relational database background or, some other type of conventional database where you have IDs, all right, and they're sequential. So like, ID number 1 would, of course, be the key, and it would correspond to a record, which would be this domain right here that's got a name, cost is owned. And then that's saved in the blockchain so that you can retrieve it later. You can update it. You can do all that stuff that you would normally do with a database. Okay. So how do we save it? So now we've defined the mapping, but we haven't actually done anything with it. So basically, we could save the domain to the mapping like this. We just say domains, okay? And then let's just pretend this is the first time that we're calling this function. We can just say domains1 equals domain name cost. All right. So basically, we just say domains, here's the key, which would be 1 the first time we call this function. And we say equals to, this new domain that we created, and that would save it directly to the blockchain. Okay, so let's just kind of test that out. And then let's just see if that actually works. We're going to change this in a second because obviously we don't want to keep 1 here forever. But let's go to our code here in our test. And then let's do below deployment. Let's do this. And let's create a new function called describe. And we'll say describe domain. All right. And then we'll give this an arrow function here. And then we'll say say returns domain attributes async. Okay. And then inside of here, we're basically going to, say, let's see here. We need a way to get the domain. So for now, let's just make this public. Okay. And then basically we can just say, over here, we can just get just say domain equals await ETH daddy domains, and then we can pass in 1 and say let domain, and we can just say expect domain name to equal, and let's just say jack.eth. All right, that's right, the test for it. But let's actually create a domain name. So up here in our before each function, we're going to list the domain. So we'll do that like this. I'm going to move this over so you can see it better. We're going to say list a domain, and I'll show you. We'll do it just like this. So we say a const transaction equals await ETH daddy connect deployer. Okay, so this is the person who deployed the smart contract. And basically what we're going to say is, we're talk to the smart contract on behalf of this deployer signer. That's what this connect does. Okay, so basically it's going to give us the smart contract here. It's going to give us a smart contract that's connected to this because we have to specify which account is calling the function. We're going to call this list function. We're going to pass in a name, and then we're going to pass in the number, which is tokens. All right. And so we'll just do that for now. All right. And then let's go ahead and run the test. Let's just see if it passes, and we'll see if it actually works. So I could have some problems. We'll address those if we run into them. Next HARDHAT test. All right. No, it works just fine. Awesome. So that's good news. So I'll just pause the video here if you want to see the exact code that I have. All right. Here's the code on the left. And here's the code on the right. And I'll even put this up if you want to see that too. And this. Okay, so now let's change a couple of other, well, first of all, let's explain, well, so let's check, so we got the name here. Let's check the other things like the cost. Now what I'm going to do is just paste this in, and then let's do that. Let's also check, let's just check everything first, and I'll change some things and explain it. Okay. So let's update our test to look like this. Basically expect the name to be this, the cost to be this, and is owned to be that. All right, let's run it. All right, boom, awesome. Now they all work just fine. So let's illustrate a couple of things really quickly. So let's talk about the costs. So let's look at this tokens function and what it does. So first of all, you can see we got this tokens helper at the top of a file that we created already. What this does is it converts the human readable, well, I guess they're both human readable, but it creates this number 10 to something that the smart contract can understand. So what we're doing here is we're essentially listing a domain name called jack.eth, and we're saying the cost of this is going to be 10 ether. So you can see that here. So like jack.eth is already owned, but let's say john.eth, is 25.0 ether. Okay. And so if we're going to list this, we would say john.eth is the name, and then 25 ether is the cost. But you can't just put 25 into this function right here in terms of the cost. You couldn't just put the number 25 in here because you actually have to convert it to the way value. Now let me explain what I mean by that. All right. So basically, ether is divisible by 18 decimal places. Okay. So in my text editor, basically, I'll show you that. Like, think about the US dollar. US dollar looks like this. All right. So US dollar is $1 followed by 2 decimal places. That's because US dollar is made up of 100 cents. So if you were going to write out $1 in terms of cents, you'd write it like this, 100 cents. Now, ether is divisible by 18 decimal places. So like 1 ether looks like this, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. If you were to write ether out in its smallest possible subdivision, it would just look like this. All right, take away the decimal place. So that's a really big number, and that's what we actually have to store the value as in smart contracts. So this is what's called the way value. All right, so you can see this on a website like eth-converter.com. If you put in 1 ether, all right, it'll show you how much Wei that is. So similarly, if you put in 10 ether, that's what it's going to look like in terms of its Wei value. Now, why do we use Wei? Why do we care about it? Why do we have to do this? Well, basically with smart contracts, you know, this is a common computer science thing. Where basically, you know, at the storage level down here with the computational level, you don't use decimal places, okay? Especially for money. So we're going to use this thing called an unsigned integer, which is basically not negative, but it's also an integer, which some integers can't have decimal places. And so we store all the money cost, you know, side of things. Anytime we deal with cryptocurrency, we don't use decimal places. So we kind of convert everything to cents. So like if you had a financial application for US dollars, you might save everything in the database as cents. Similarly, with blockchain applications, when you're dealing with ether values, you convert everything. You don't use just decimal places. You convert everything to Wei at the smart contract level. So what I'm doing here, when I'm listing the cost, is I'm saying I want to cost 10 ETH, but instead of typing this out the long way, I have a special function that converts that ether to the Wei value. So let's just write that in the test so you can see tokens 10 is what I am going to pass in here. But instead of using the same function, let's actually go to our converter here, say we're going to do 10 ether and convert that to the Wei value. We can just copy and paste this and then put it inside of here and then make sure, you know, put the actual thing we're looking for and make sure that it works. And let's run the test again, make sure it still passes. All right, it still passes. So that's what it looks like at the smart contract level. This is what's going to look like on, you know, more human readable level. So let's just undo that. I just want to explain the difference here and why it matters in context so you understand. Okay, so that kind of covers that. Now so we've saved the domain. Now what we want to do is actually update the domain name count and make this function dynamic. So right now when we're listing the domains, okay, we're basically just hard coding 1. So if we call this function again, it's going to just overwrite this domain. What we want it to be is dynamic so that when a new domain is created, we're incrementing the IDs like 1, 2, 3, 4, blah, 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 blah. Now, unfortunately with Solidity, you cannot, ideal way would be to figure out how many domains are in here from the mappings called like mapping.length or mapping.size or something like that. But you can't do that inside Solidity because there's no way to know the size of a mapping. So what we're going to do is use a counter cache. Okay, so basically what we're going to do is have, a state variable up here above the owner. We're going to say uint256 public, not total supply, but max supply. All right. And we're going to use that as our counter cache inside the function. So what we're going to do is say max supply. All right. And then it's going to be 0 by default whenever we declare the variable. But we can basically say max supply equals max supply plus 1. And that's going to increment it every single time. So we'll say max supply. It starts off as 0. We just add 1. And so for the domain, you know, number 1, we'll just say this is going to be number 1. We'll use that as the key. And then we'll update this. Run the test again, see if it passes. All right, boom, it still passes. And now if we run this multiple times, it's going to increment it 1 by 1 each time. Now, the cool thing is in Solidity, there's a shortcut for adding 1 to a number. So instead of doing that, we can just do this. Max supply plus plus is going to use the increment operator and increase the value by 1 instead of having to write it out the long way. So we'll do that, run the test, and see if it passes. All right, boom, it passes. So now we are able to list domain names. We have modeled domain, we've saved the domain, and we've updated the domain count. Okay, let's just run the test again, make sure we're still good. Let's see if there's anything else I want to change here before we move on. Yeah, let's do one thing in the test. All right, let's actually check for the maximum supply. So because we list the domain here, we can check the maximum supply. All right. It returns the maximum supply. So basically we'll say ETHEREUM max supply, expect result to equal 1. All right, so there should be one domain name as the maximum supply once we've listed it. Save that, run the test. And boom, it passes. All right, now there's one more thing I actually want to do on this before we move on. All right, we're really close. But we want to restrict this function to where only the owner of the smart contract can list the domains. So again, our model here is that the owner who creates the website, the developer basically, is the only person that can list the NFTs for sale, and then basically somebody else can buy them. When they buy them, they mint them from scratch, and then they get the funds from the purchase. But then they're also the only person that can list them. So you could update this website to where anybody could list the domains and get purchased. But for now, for simplicity, we're basically saying the developer is the person who lists the domains for sale and somebody else can purchase them. Okay. So what we're going to do is restrict this list function to where only the owner can call it. So basically, we can do that like this. We can use a require function inside Solidity. All right, we can say require. Let me just say require. And then say message.sender is equal to owner. All right. So what require does is requires a special function inside Solidity that evaluates an expression. All right. If the expression evaluates to true, then you can continue running all the code below this line in the function. But if the expression evaluates to false, then it's going to stop execution and it will not run this code, and the function will basically just throw an exception. It'll just blow up. It's not even going to work, okay? So what we're going to do inside of here is basically say, require that message.sender is equal to the owner. Now, the good news is, inside of our test, we already connected the deployer, who is the owner in this case, to the smart contract. So this should continue to work just fine. Okay. All right, it passes. But you can see, you can make it fail. We have a second account here, which is owner number 1. That's going to be like an NFT owner, not a smart contract owner. We could say, connect list owner 1, change the person, it should fail. All right, so see it's transactions reverting. You could say, without a reason string, you could give a reason string inside of here. You could say, must be owner. Okay. And then you can do it again. You can see the reason string, transaction with reason string must be owner. Okay. So we'll take that out. I just wanted to demonstrate that that's possible. All right. And then let's change the owner back to the deployer. Run the test. Okay. All right, it's done. And now what I'm going to do is refactor this a little bit. So instead of saying require message.sender equals owner, I've got some other functionality that I want to restrict inside this application to where only the owner can call it. So what I'm going to do is create something called, and I don't want to copy and paste this line every time I do that. So I can create this thing called like a modifier inside of Solidity that we can apply to our function, a custom modifier like this. I can say modifier. I can say only owner. Okay. And then inside of that, basically I can copy this. Let's just take the line out. Oops, sorry. A little clunky today. And then paste it in here, require message.sender is equal to owner. And then I'm going to do this underscore here. I'll explain that in a second. And then I'm going to take this only owner modifier. I'm going to apply it to my function. So after this public keyword, I'm just going to say only owner, just like that. And then I'm going to run the test again and see if it still passes. All right, do that. You can change the owner just to see sure it's still working. Say owner 1, make sure it fails. All right, then revert it back. And then boom, it works. Awesome. So now we successfully restricted the access to the list function by the ownable or the owner address, and we can reuse this on other functions, which we'll see later. Now I want to talk about this underscore here. So basically this underscore basically just means run the function body. Okay, so basically what it's saying is it's specifying the order. you're saying require, do this before you run the function body and then run the function body here. You could alternatively do it like this. You could do it like that. All right. You could do it before and after. There's lots of different things that you could, do. Okay. So now we have listed the domains. Now we want to buy the domain names with another account. Okay. So let's just see here. We've talked about this, how this kind of works. Basically, we've got this contract to mint the NFTs. Well, it lists them from the deployer, and then now whenever someone comes to the website and buys them, they're going to create them from scratch and mint them. So what we want to do is create a function called mint inside the smart contract. Okay. And actually, before I do that, I want to clean up one thing. Instead of making this public, all right, I want to use a reader function for this. So we're going to take that away. Sorry, this is going back to the previous section, but what I want to do is have a function here called get domains. All right, so I'm going to put that in here. Basically, it's just going to say function get domain. We can give it an ID. It's a public reviews domain memory. It's a return domains. And then we're going to read it out of there inside Solidity. So we're going to do that. And then inside of the test, we're going to say get domain. All right. So that's a quick refactor. I meant to do that in the last section, but let's just go ahead and quickly get that done before we continue on. All right. Yeah. So sorry about that. If you want to grab the final code solution, you can, but that was just a quick refactor. We have a special function for that instead of using the shortcut. So anyways, let's go back to minting. So we need to create domain names, let people buy them. We're going to create a function called mint. So we say function keyword mint. It's going to accept an ID of the domain name. So uint256 ID public. Okay. And so basically we're going to take the ID of the domain we want to mint. All right. We can get it. We can basically see it listed here. We can see it listed on our site, and whenever we click buy, it's going to mint it, and it's going to pass in the ID of this domain name in order to mint it. So we need to pass in the ID, and then we're going to call the safe mint function from the ERC721 library. So that's the heart and soul of what it does. So if you look at the ERC721's file, there's a safe mint. All right, this is a function that essentially creates the NFTs from scratch. Okay, it does all this underneath the hood. I'm not going to get into all that, but just know that's what the library does. It creates new NFTs from scratch. So basically, we'll just say function mint. So safe mint. Okay. And then we'll pass in, it accepts two arguments. So the address that we're going to mint it to, and then the token ID. Okay. So basically, the address is going to be message.sender. So that's the person who's calling the function again. All right. And then also the ID is just going to be the ID that we pass in. Okay. So let's write a test for that in the smart contract. That's the basic functionality. So below domain, let's just copy this and say, describe minting. And then inside of here, we'll just say it updates the owner. Okay. All right. So basically what we're going to do is just replace this. We're going to say on its owner equals wait, ETHEREUM owner of the ID. And we'll say owner to be equal owner1.address. So let's save all that stuff. All right, let's kind of set this up. Basically, what we're going to do is we're going to save some variables inside of here. We're going to track the ID. So const ID is going to be 1. We're just going to buy the first domain name that's listed, which was this one here that we created. Okay. And for the amount, we're going to say 10 ether. Okay, just like we did here. And so we're going to say const amount equals ethers utils parse units 10 ether. Okay, that's going to give us the actual amount that we need to pass in for it. The amount of ether that we want to that we want to pay for the domain name. I'll get to that in a minute. But basically what we want to do is have this before each function. And then we want to say, inside of here, we're going to call the mint function. So we're going to say const transaction equals await ETHEREUM connect owner 1. This is the person who's going to be minting, not the deployer owner 1. And we'll call the mint function. We're going to pass in the ID, which is this 1 right here. And then we're just going to say await transaction wait. And then when that's finished, we should be updating the owner right here. Let's do that. Let's save it, run the test, see if it passes. And boom, it passes. So it updates the owner successfully. All right, so that's good. Now, this is a very basic and brittle function. We're going to change it a lot. But basically, right now, all it does, we can call the mint function, pass an ID, and it actually creates a new NFT that's assigned to us. The owner of function, where does that come from? You might be like, hey, you didn't write that function. Well, that's because it came from our library. Again, you know, this ERC 721 library comes with all these different functions for free. Okay, out of the box, you have to check the specific one you're using. But like ERC 721, right, this one, it has an owner of function already. We can basically just call that to see, you know, who did it. Now, there's a couple other things we need to do here. All right. There's actually several things we need to do here. One is that we want to get paid anytime that we are going to sell a domain. Okay. So how do we do that? Well, basically, you know, the user needs to pay anytime that they call the function. Okay. So we can see that on our diagram here, you know, user, you know, mints the NFT and they need to pay, and then we're going to get paid. So what's going to happen is they're going to send Ether in order to buy the NFT. They're going to buy it with Ether. They're going to create it from scratch. And that Ether is going to go directly into the smart contract for safekeeping. And then we can withdraw it later from the contract whenever we want to. So the first step is to make people pay whenever they're doing it. So we're going to say mint public payable. Basically, what that's going to do is they're going to be able to call this function, and they're going to be able to send Ether in whenever they call this function since it's payable. Okay, so I'll show you how to do that. You see this amount here, 10 Ether, that we saved to a variable. Well, we can basically send that in like this. After mint, we can do a comma and then pass in the metadata, which is value. And value is going to be the amount here that we saved as 10 Ether. So now it's going to do is going to call the mint with the function, with the ID, and it's going to send in 10 Ether with that function that's going to get stored in the smart contract. Okay, so let's just do that. Make sure it passes. All right, boom. And so now we can check that that was actually saved to the smart contract after it updates the owner. Okay, we can say it updates the contract balance. Okay, so now we need a function called getBalance. So what we're going to do is create a function like this down here. We're just going to say, instead of after getDomain, we're going to say function getBalance. And we say getBalance public view returns uint256 unsigned integer of 256 bits. You'll say return address this. So this is the address of the smart contract that we're coding inside of. Address is casted to an address type. Okay. And we can call .balance to get the Ether balance. All right. And then we're going to call that function here, ETHEREUM get balance. And then we'll run the test again. All right. So I need to save it. I didn't save the test over here. All right, but boom, it passes. So we can see that they're actually sending in 10 Ether with the transaction. It's getting stored into the contract. We can withdraw it later, but for now, it's just going to update, you know, the owner. All right, but there's several other things that we want to do. So additionally, we want to update the domain status. So after it updates the owner, we want to say it updates the domain status. So after we listed it and someone's bought it, in the list, we want the domain to not be owned anymore, or to be owned, excuse me. So whenever we created it here, you know, we said the domain is not owned yet, it's false, but inside of this function, we want to set it to owned. All right. So we'll do that like this. basically we'll pull it out of the domains mapping. We'll just say domains. We'll fetch it out like this, ID that we're passing here. And then basically we'll say is owned equals true. We can just update it simply in line like this. All right, run the test again. And boom, it passes. It updates the domain status to owned. All right, so that's the basic functionality of the mint function where we can get domains and then, basically update the status. Another thing we want to do is update the total supply of domains that exist. We know how many that have been minted so far. So inside the list function, we use the max supply, which governs the total number of entities that can be minted. But now we want to do is use the total supply. So we got the max supply. We want to have another state variable called total supply right here. So we'll say total supply. So this is the theoretical number of NFTs that are domains that can be created. This is the actual number that have been created. So inside of here, we're going to do total supply plus plus, just like max supply. All right. And so also here, we want to add the total supply to our deployment. So deployment has name, has symbol, has the owner, returns a max supply. We also want to say returns a total supply, which when we deploy the contract, it should equal 0. All right, we can do npx HARDHAT test. All right, boom. So that works. And so I check for the total supply whenever we update the contract upon deployment. But now what I want you to do essentially is check for that inside the minting function. And I'm not going to tell you how to do it. Okay, so this would be a code challenge for you, kind of like a homework assignment, where you need to check that the total supply was actually updated to the correct amount here. All right. Okay, so that's the basics of the minting function. Okay, but we want to do several other things. Remember I showed you how to do this require function inside Solidity to evaluate expressions? Well, we can do that to safeguard our Solidity file as well. So what we're going to do is say require ID is not equal to 0. Okay, because it can be unsigned energy. We want it to be, a number, but we don't want it to be 0. Okay. We also want to make sure that it's a valid ID. So this checks for validity, but we also want to make sure that the ID is less than or equal to the maximum supply. So the domain name should be there. Okay. The domain name that is currently being minted. All right, we're going to check to see if it's already owned or not. So we could say domains ID is owned. We may want to make sure that's false before we change it to true here. Because if it's true, that's going to break and we're not going to call the function. And then the last thing is we want to make sure that the amount of ether that's getting sent in is the correct amount. So we can see message.value, which is what you use inside Solidity to check the amount of ether that's getting sent inside the function. We did message.sender here. You can do message.value to check the amount of ether that's getting sent in. We want to make sure it's at least equal to the actual cost of the domain, which we set right here. Okay. So now I'm going to run the test and just make sure they still pass. All right, they still pass. And what you can do is you can check for these yourself as a homework assignment to see whether or not you can get these to fail. All right, you can write your own explicit examples, or you could just change values in your test just to see if they work or not. Okay. All right, so that's it. That's the entire mint function. So now what we want to do is create a way for the owner of the smart contract to get paid, okay, whenever they get, the owner of the smart contract to get paid. So basically what happens is we have this NFT contract here. Someone's minting the NFT, they're sending ether to the contract, and then it spits out the NFTs to their wallet. But in the meantime, all the ether stays in the contract. What we want to do is have the deployer here, the contract creator, withdraw the ether from the contract. So I'll show you the code for that like this. At the very bottom here, our last function is going to be a withdrawal function. All right, I'm going to paste it in and explain how it works. So we have function withdrawal. It's public, so it's externally accessible. Only owner, so only the person who created the smart contract can call this function. And then we do this owner.call, which is, there's several different ways to transfer Ether inside Solidity. You can use the transfer function. You can also use the call function, all right, which is basically just a way to send, a message inside Solidity. You can do things like pass in the value in this case, which is exactly what we're doing here. We're passing in the value of address this.balance. So again, this is the smart contract address. We're passing it to an address type and getting the Ether balance. We're sending a blank message, and this just transfers Ether to the owner. All right. And then it returns the success value, and we make sure that it was returned successful like this. So the reason we do this inside Solidity is just to make sure that this is worked properly. There's some security issues potentially with the transfer function. We see a lot of people in the Solidity community moving towards this type of pattern, so that's why we do it this way. Okay. So we do that, and I'm going to take this out because that should be the last of our code here. And then finally, I'm going to just drop in the test example for this. You can grab this from the final code solution if you want to, but I'll drop it in, and then I'll explain how it works because I want to move on to creating the front-end website and spend some more time there. We've already got a good handle on testing, I believe, so I'll just go through this quickly. So let me just save it. Let's run the test, make sure they pass. All right, they pass. And so basically what we're doing is say, describe withdrawing. We put in the ID, the amount, all right, balance before. And what we do is we get the deployer's address, we check the balance before, we connect ETHDaddy owner 1, we mint an NFT. We wait for the transaction to finish, and then we connect with the deployer's account, and we call the withdrawal function, which we just coded here, all right? And then basically we just say, we update the owner balance because we check the balance after, all right? And we say the balance after should be greater than the balance before, okay? And then it updates the contract balance. We get the result ETHDaddy get balance, and now the balance of the smart contract should now be 0 because we've taken all the Ether out of it. So when we run that test, it passes, and then boom. All right. So now we have a complete smart contract for our NFT domain website. So now let's talk about how to put that smart contract out there on the blockchain. All right. So now what we're going to do is take our smart contract and put it on the blockchain so that we can start creating our front-end website, okay? So I'm going to clear out all this stuff. All right, I'm going to open a new terminal tab. And what I'm going to do is start our development blockchain. So if you notice we're running the tests, we didn't really have any other, system processes running, at least we didn't need to. I personally did, but you didn't need any. Okay, so basically if I'm just going to close all my terminal tabs. They're all not closed, but there's nothing running in them. I'm going to show you, like, we did an NPX HARDHAT test. All right, not HEST, sorry. NPX HARDHAT test. Okay, and let's see, I misspelled HARDHAT. HARDHAT, I do that all the time. HARDHAT typo. And you can see it just runs the test, right? But you don't see a blockchain running. So what's happening? Well, it's running a blockchain behind the scenes outside of your awareness. And so we can use that same blockchain for development purposes. Okay, in a new terminal tab, I'm going to say NPX HARDHAT node. And what that's going to do is start a development blockchain on our computer. Okay, and now we can use this and point our website to it locally. And it's going to give us like 20 accounts for free, all with 10,000 fake Ether inside of them. And so what we want to do is take our smart contracts that we just created and deploy them to this blockchain. All right, so how do we do that? Well, we're going to use something called a migration script. All right, so our deployment script inside of HARDHAT. So if you look inside your HARDHAT project, you can see this file here. So scripts folder. You can see this deploy.js. We have a placeholder inside of here, all right, where we can write all the code for our deployment script. And so what we're going to do is write code that's very similar to what we did inside of this testing file. At the top, essentially, where we just got the contract factory and deployed it, and then configured the name and the symbol and got the signers and all that type of stuff. We're going to do a procedure very similar to this, and it's going to deploy the code directly to our blockchain. So let's go ahead and do that right now. So inside deploy.js, we're gonna get the signers, okay, So we'll just say at the top, we'll say set up accounts and variables. We're going to get the signers just like we did inside of our test like this, say const deployer. All right, we're just going to get the first item out of the array, say await ethers get signers. All right. We're going to set the name and the symbol, just like we did in our test. So const name equals ETHDaddy, symbol equals ETHD. And then now we're going to deploy the contract like this. Okay. We're going to do the ethers get signers just like we did in the test. ETHDaddy await equals get contract factory, ETHDaddy. I think I say get signers, I meant get factory. And then we're going to deploy it. Okay, just like this. And then we did that. We did the same thing in the test before. And then finally, we're going to say await ETHDaddy deployed. That's just going to make sure that it's finally deployed. Okay. And now we can log that to the console. We can say console log deployed domain contract at, we can console log the address so that you can see it. Okay. Now, there's one other thing I want to do inside of here that you could run this right now and it would go ahead and, put the smart contract in the blockchain. But what I want to do is also, list some domains. So I'm gonna put this in here kind of quick, but you could reference this from the final code solution if you want to. So inside this is just an arbitrary script. You can do whatever you want to inside of here. The main purpose of this is to deploy the contracts, but simultaneously, I'm going to go ahead and list some domains so that we can boot up our website and see some domains already on our website. So I'm going to list 6 domains like this. I'm just going to throw this in here and then explain how it works. You can grab this from the final code solution if you want to. Basically, I'm going to take 6 names, so jack.eth, john.eth, Henry, Cobalt, Oxygen, Carbon, and then the costs. This is also an array, tokens 10, 25, 15, 2.5, 3, and then 1. All right, this is the ether price. And then we're going to use a for loop in JavaScript. And we're going to call this, 6 times. Basically, ETHDaddy connect deployer, list, the first name and the first cost, and we'll wait for that transaction to finish. And you'll say that, okay, Louis listed this domain and then this price. Okay. So let's just save that. And then let's run the tests. Not run the tests, I just run the deployment script like this. We'll say npx HARDHAT run. That's how you run scripts. We use a scripts folder, scripts we say scripts are deployed as JS, and we say -- network localhost. All right, boom, there you go. See, the domain contract was deployed at this address, and then we listed domain 1 through 6, Jack through Carbon. All right, and you can see that listed here inside of this transaction list. All right, so now let's start coding out the front-end website. Okay, we've done the smart contracts. We've put everything on the blockchain. We've got our blockchain running. Okay, we've got everything out there. Now we want to actually cut out the smart contract. Cut the website so we can talk to the smart contracts. So, I'm going to go to my code here and just make sure all the files are closed, kind of clean house a little bit. I don't need all those files open. And I'm going to go to my terminal. And just like we ran a separate tab here for our blockchain, we're going to run a separate tab for our web server. So I've got my development workbench here. I've got my blockchain here. Now I'm going to run my development web server for the website. So let's start that like this. We just say npm run start. Okay. And that's going to open up a new tab here in your browser at localhost port 3000. You can say it says just welcome to ETHDaddy. So it started properly. All right. Now we can see that here. And I'm just going to go back to my development workbench and keep that out of the way. All right. So let's take a look at the website because clearly we have something here already. Again, we started off with this template, the starter code branch that's got some placeholder code in it. So let's go look at that placeholder code. If you go to the source directory, this is the file where we'll put all the front-end files for the website. So again, we've got a HARDHAT project here, and then inside the source directory, we've just put in the source files for the website. This is going to be the React application. So if you look at this app.js file, okay, this is the main component for the library. Okay, so this is a React component. This is React.js. We've got this return function inside of here. You can see that we've got JavaScript up here. We've got HTML inside of here. That's the beauty of React components, is that you can basically, mix HTML inside JavaScript into these files called components that you can reuse and, organize your application. So I'll just do a quick mention of React in case you're not familiar. Again, React is a client side, or it's a library for building user interfaces, primarily on the web. Okay, so basically you can write your websites, then we can make it connect to the blockchain. We can write this interface with React. We'll kind of dig into some of the details of React as we go through this, but that's the basics. Okay, so we have this basic HTML here that just says, welcome to ETHEREUM. All right, we could put an exclamation point here just to change it, click save, and go back to our web browser, and you can see that automatically changed without having to refresh the page. That's the really nice thing about using that development server, is it keeps the website and our code in sync. All right. So you can also see that some other stuff was imported inside of here. Like we've got these components that are already saved inside of here, loaded up into our project. We've got an ABI. We've got a config.json file inside of here. We've done a lot of stuff for you so that you don't have to create everything from scratch. We've already pulled this use effect, use state, pulled in the ethers library. You're probably going to see some serious linter warnings in your server. That's okay. It's because we have these placeholders in there. This is not the final code. But yeah, we've got a sort of hello world website pulled up there. Now, another thing you want to do is configure your MetaMask. So basically, we've got our MetaMask here. You want to make sure you're connected to the HARDHAT network. So inside of here, you're going to do add network. Okay. You want to put in the details for the HARDHAT blockchain. Let's see if it might have HARDHAT actually. HARDHAT. Okay, it doesn't have. I was going to see if MetaMask added a configuration for HARDHAT. But you're going to do add network manually. You can call it HARDHAT, RPC URL. Okay, it can just be localhost port 3000. Or not localhost port 3000. It'll show you here. Here, just copy this. Okay, so, and then chain ID is, let's just see here. Let me remember what the HARDHAT chain ID is. 1 second, everybody. Let's see here. Actually, it's in this config file. I'm going to show you the cheat code for this. We already have a file inside of here called config.json. If you look at it here, we've got the thing already, 131337. So we can go put that in here, 1337. And then currency symbol is ETH. Okay. And then I can't do it already because it's already got this added to my MetaMask, but it should work for you. Click save. And then inside your MetaMask, you should have a blockchain that you can select from called HARDHAT. So if you're on mainnet by default, you should see one called HARDHAT now. You can switch to it. Now you can see this. Now, you also want to import your account to this. I would recommend importing a few accounts. So you can take like account 1 and then copy the private key and then go here and then go to import account. Okay, and then paste in the private key, click import. All right, I've already done this, so it's not going to let me do it. Okay, but basically I did that for HARDHAT, and you can rename your accounts. So I'm going to do account details. I rename it to HARDHAT 0, which is the exact same name as this. So I just use it based on the index account 0. So I just call it HARDHAT number 0, HARDHAT number 1. And I would go ahead and do this for the first 2 accounts in the list. Okay, so account 0 and then account 1. HARDHAT 0, HARDHAT 1. I'm going to start off with HARDHAT 1. So 0 will be the deployer, 1 will be the purchaser. And one thing you want to do really quickly, if you've imported these accounts before and you've restarted your blockchain, I always like to reset my accounts. So I'm going to do settings, advanced, reset. This doesn't delete any data. This doesn't delete any cryptocurrency or transactions. Those are all on the blockchain. This just resets the information about your account inside the MetaMask app itself, because you might get an error whenever you're doing this. So you can see you got 10,000 Ether in there. Man, wouldn't it be nice to open your MetaMask and see 10,000 Ether just chilling there, about $12 million. That'd be a great feeling, but alas, this is fake Ether. So anyways, now you got your MetaMask set up. We've got the website rolling. Let's do a couple of the things. We'll go to this config.json file, okay? We want to import our smart contracts. So whenever you access the smart contract inside of the website, you need the address and you also need the ABI. So let's just double check our addresses. The nice thing about HARDHAT is, it essentially, let's look at our transaction history. You can see the address was saved here, contract address AA3. The nice thing about what I said a second ago is the addresses created of the smart contracts created by HARDHAT are deterministic. So whenever you deploy this, assuming that you're only deploying one smart contract, the address should always be the same. So you shouldn't have to change anything here, okay? So that's good. And then also the ABIs, we've already imported the ABI for you inside of here. But if you want to just be double safe, you can go to your contracts. You can go to artifacts, contracts, ethdaddy.sol. All right, and then take the ABI here and take whatever's in these brackets and then paste it inside of this source ABIs, and then paste in that one. Okay. I'm going to do that just to make sure that we're working the exact same code in both places. Okay. So the ABI, what it is it's basically just a JSON file that describes the interface for your smart contract, like what the functions are, and then what the functions are, and then what the arguments are, any type of events that the smart contract might emit. Okay. And so we need the ABI, HARDHAT creates it for us in our HARDHAT folder, but it doesn't expose that to our React application. So we got to import all that stuff from our React application inside of here. So we take the ABI, we put it in this ABIs folder, we take the address, we put it in our config.json file, and then with this ABI and then the address, we can create a JavaScript version of the smart contract in order to talk to it on the blockchain. So we'll come back to that in a minute, but just know that that's part of the initial setup process, okay? And that we want to actually, do that. So, and then we pull those into our app.js. We pull the ABI from it. We pull the config.json so we can get that. And then now we should have everything set up. So let's do a quick smoke test with our front-end application just to make sure that we can actually properly, connect it to the blockchain. All right, so we'll make it nice and simple here. All right, so what we're going to do is basically just take the account out of our MetaMask wallet and show it on the page. That'll be a nice, simple smoke test to make sure that everything is set up properly and that we're talking to one another. So what I'm going to do is open my web browser here. Let me put this back on the right place. If you look at, go inspect element or inspect, you can see this pop up. All right, this will show you like all the HTML on your page. It's also got a console down here where you can interact with the JavaScript environment. So in the console, you can see window is basically a global variable inside of JavaScript here that is a window object for the entire window of your browser. And you can look at window.ethereum, okay? And this is basically connection that is provided to your window browser from MetaMask. So whenever your MetaMask is talking to the blockchain, MetaMask attaches something to your browser called window.ethereum. Again, what's the purpose of this? MetaMask is to basically turn your web browser into a blockchain browser and to give you a place to hold wallets and sign transactions. In order to do that, it mounts this window.ethereum to the window so that you can do that. So we can call this window.ethereum directly to do things like fetch the account and among other things, and that's what we're going to do right now. So what I'm going to do is create a function called load blockchain data. Say function, or say const load blockchain data. All right, that's async. And inside of here, let me fix that. I'm going to say, window.ethereum, like we saw a second ago. I'm gonna say request method ETH request accounts. Okay. And so I'm just going to copy this right now and show you that inside the console. Like you can take that, you can run it inside of here, do window Ethereum request accounts, and you can see this. Okay. And what you want to do is say, actually, I don't think we can do the top level await here. Oh yeah, it does work. Okay. So you can do await and it will return the array, and you can see the array of accounts. So it's going to return an array of accounts from our MetaMask. Really, it's just the only one that we're connected with, but you can see that it's the exact same account here. 0x709 is this, right? So that's how we're going to get the account from MetaMask. But now we want to actually show this on the page. So how do we do it? Well, we do that function here, and we say await accounts equals this. Sorry, no const accounts. Await. All right. And then we're going to just format it. And then like this, const count equals ethers utils get address accounts 0. Since it's an array, we want to get the first one out of it. And we just want to use ethers, which is the library that we've imported right here. It's got a utils just to format the address. Okay. And then we're going to just console log that, console.log account, just to make sure it works. Now, if you notice, go back to our page and refresh. We don't actually see that logged to the console. So why is that? Well, that's because we, defined this load blockchain data function. We're not calling it. Okay, so how do we call it? Well, inside of React, you can see we're using this thing called a function here for our component. Well, functional components have these things called hooks, and we have something called use effect that we can basically call whenever the function is going to get, rendered, whenever the component's going to get rendered on the page. And we can see we have use effect already imported from React here. And what we can do inside use effect is we can say load blockchain data. All right. And then for now, we also want to provide a second argument, which is going to be empty array. I'll explain that in a second. But for now, let's just do that. Go to our page. And if we refresh, we can see that it is getting logged to the page. So we're actually displaying the account in our console. Okay. And so now this thing right here, this empty array, this is a list of properties that we want to watch for to see if they change, if we want to call this again, but we don't want to track anything, so we just leave it blank. But now we've got this load blockchain data. So instead of just saving this to an array, let's show it on the page. So what I'm going to do is use another React hook here called use state. So React has something called a state object, which basically is like a little database for each component. So if you think about it this way, you see a to-do list inside of React, right? How does this to-do list know which items are on the to-do list? 1, item 2. Well, it uses something called a state object. So you can see this right here. This is a class-based component. Basically, you have this thing that holds the items for the to-do list, and it just saves it. And anytime you add a to-do list to it, you can save it to the state, and you can read it out of the state later. So we're going to do that inside of our app with these, this use state hook. So we're going to talk to the component state of this particular app component. So what we're going to do is say, const provider, set provider equals use state null. So basically what it's going to do is say use state is just going to call the hook. Null is the default value for the provider. And actually I said provider. I don't want to do that. I want to do account. So set account and then set account. So account and set account use state null. Null is the default value. We don't want the account to be anything by default. And it's going to give us a variable, okay, to read the current account value from the state, and then also a function to update that value directly to the state. And then we do it just like this. So we can basically, instead of saying console log account, we can say set account and pass in the account. All right. And then here on the page, what we're going to do, let's just do another H2. All right. And then let's just do a paragraph tag. And then we're going to do it in JavaScript like this with these curly braces and then call account. And that'll show the account on the page. All right. Boom. There you go. It works. Okay, so we have successfully set the project up. Now let's continue on to the next task. All right, so now what we're going to do is create the Navbar. Okay, so you can see from our mock-up here, we've got this Navbar that's got the ETHEREUM, logo here. It's got the domain names, all this stuff, right? So let's go ahead and create that. Okay. So the cool thing is we've already got a few components inside of here. So we've got like the source components directory. We've got this navigation.js file already. All right. So what we can do is just import that into our top file here, the app.js. And we've already done that. So we've got navigation here. And we can simply render it onto the page like this. Okay. So what we can do is basically, let's say inside this div, we're going to do navigation. Navigation. All right. And we don't need a closing tag there. We can just do this. And what I'm going to do is go ahead and pass in the account. And then like this. And then I'm also going to pass in the set account function. Okay, so we can pass things down to our components like this. We can just say account is the account variable that we saved here. And then set account is this, which we saved here, okay? And then now in the navigation, we can see we accept an argument of the account and set account. Now we've got those because we passed them in right here. And what I'm going to do is take this paragraph tag out of this, and then I'll move it to the navbar, okay? And I'm just going to put it in here. All right. So let's see if they're talking to one another. Let's go back to our page, and then let's go to the actual website, and boom, there you go. We can see that we've got a nav bar up here. It doesn't look like anything yet, right? But we have a component inside of there that's got the address up here. We're successfully passing it down. Now, one thing I want to do is while we're here, I want to go ahead and, well, we'll do that in a minute. All right. So what I'm going to do is just take this out for now. All right, let's go ahead and sketch out the HTML that should go on the page in order to display the account. Let me close some of this stuff because we don't need it anymore. Hold on. It'll just eliminate confusion. All right, I'm going to put the website here and the mockup here. So let's just go ahead and fill out some of this HTML. So we're using some custom CSS. All right, so if you look at this index CSS file, this is all of the custom CSS to make this mockup. So I don't want to focus on writing CSS in this tutorial because we just want to focus on the blockchain side of things. But just notice that we're getting all of the CSS files for free directly from this index.css file that's already in here. That just go ahead and it adds all this styling for free. We've also got these images for free, like this and this. If you look at this assets directory, we've got like this these SVG files that, this is for the logo and this is for the background, which we've got right here, okay? So let's go ahead and sketch out some of the HTML. We can go ahead and add a new div like this. All right. We're going to have one div here. Okay. And then we're going to have an image here. All right. And then we're going to have, let's just leave that there. And then we're going to have an owner list. Well, sorry, we'll have an H1. And then an owner list. All right, so those are our main, we're going to have three main elements. So we have a nav. And then actually outside of this, let's do this button. Okay. And then for now, what we're going to do is just put in the account here. So anyways, let's just fill these out. So I just want to show you the high level scaffolding. So let's do that. We go back to our page. Still looks kind of funny. Like this doesn't make any sense, but let's fill it out. So I just want to show you the basic scaffolding so that we can, you're not confused and trying to see what goes where, but that's the starting point. So inside the div, we're gonna give this a class name. Okay, whenever you're using classes like HTML classes, normally you would do this in HTML, but React has a conflict with that. So you must use class name in React. And we say nav_links. Okay. And then for the image, oh, excuse me, that's not nav links, sorry. This goes to the div. And inside the image, it requires a source. So what we can do is just pass in the logo, which is already imported here, all right, from our assets. First logo. And React requires that we give it an alt, or the linter does. Okay. And H1, we're just going to call it ETHDaddy. All right. And then for the UL, this is an unordered list. We're going to say class name is equal to nav_links. I'm sorry, I said nav links up here. This should be nav brand. Sorry. Okay, so an unordered list is really just a list of items with no numbers. And so each one can be a list item like this. Okay. And we're going to wrap each of those in a link, a href. And we're just going to link back to the home page. Not actually going to go anywhere. It's just going to be for looks, but it'll look cool. Look just like GoDaddy. We'll say domain names. Copy that. And then we'll do websites and hosting. All right. And then we'll say commerce. And then email and marketing. Okay. So let's just save that and see what happens. All right, that's looking a lot better because ETHDaddy, domain names, website, they look like links, but they don't go anywhere, right? It's really just for looks so that our mockup looks like GoDaddy, right? That's exactly what our thing looks like right here, right? So now we can style this button, okay? We can just say button. Let's just break this up into multiple lines here. Okay, let's say button. We're going to say type equals button. And then also class name equal to nav_connect. And we're going to say, just going to put the account here. All right. And boom, we can see our account. But you can see it's clipping, right? Like we can't see it all, right? It's kind of annoying. So what we can do is we can truncate the account by just getting the first few characters and the last few characters, which is really common. So you can, like inside the MetaMask, you can see this. You can see it doesn't actually show the entire account. It just shows the first couple characters and the last couple characters. So we're going to do that like this. We use a slice method on the string, which is going to take these first characters. We're going to concatenate the string by just doing ... in the middle, and we'll take the last few characters and add it to that string. And then boom, there you go. That looks much better. Okay, so the next thing we want to do, we're almost done with the header or the nav bar. What we want to do is basically have a connect button here. When we connect, like when we visit the site for the first time, we should connect our MetaMask account. We should ask for access. So what we're going to do is basically, we're going to create something, all right, like this. All right, what I'm going to do is basically, it's kind of confusing, but let's do this. All right. I'm just going to take this code and grab it. You can grab it in the final code solution if you want to, but I'm going to just drop it in. I'm going to take this button. I'm going to backspace it. And I put this code in and you can grab it from the final code solution and I'll explain how it works. So what we're going to do is basically see if the account exists yet. And if it does, we're going to just display it on the page. But if it doesn't, we're going to display a button here that says, connect to MetaMask, okay? And then we're going to use this thing called a connect handler that's going to actually fetch the account from MetaMask like this, all right? So basically it's a connection handler up here, all right? So this button is an on-click event. We're going to click it, on-click, because I'm going to call this function connect handler, and it's going to do this. It's going to fetch the account just like we did up here, all right? See, inside load blockchain data, where do we fetching the account and setting it? We're going to take this out. All right, we're still storing the account at the top level here. And now into the navigation, when we click this button, it's going to fetch it from MetaMask and set the account here. So we took everything that was in this top component and just stuck it inside of here, and it's only going to fire whenever we authorize access and do this connect button. It's going to set it up here inside this component because we passed in set account to this component, we can call set account here. It's going to save it up in this component, and then we pass it back down to this component right here. Okay. So now if I refresh, I need a hard refresh in order to do that. So actually refresh your page. You'll see this connect button, and then boom, we can connect, and it fetches the account out of our MetaMask and shows it on the page. All right, so now that's done, let's go ahead and add some more content to the page. Let's kind of scaffold out the rest of the UI so that our application more or less looks like this before we go on to like listing the domain names and actually buying them, okay? So this hero bar right here, whatever you want to call it, with the picture and then the search bar, we've already got this done for you inside this other component, all right, called search right here. And you can see it's got this like content already for the search bar. So this is really just a placeholder. It's just kind of for looks, to make it look like you can search for domain names, to make the website look more like GoDaddy. You can wire this up to actually filter through to the domain names if you want to, but for now we just got a placeholder so that it looks slick, okay? So we can simply just render this component onto the page. Inside of app.js, we've already imported this search, okay? So inside of app.js, just below navigation, what we're gonna do is just render search onto the page. All right, save that. And then boom, there you go. We've got our header here. We can refresh the page. We can see we need to connect, and then boom, we've connected with MetaMask. Awesome. Now, for this mockup, we also want to have this why you need a domain name, sort of, you know, marketing pitch. So we can add that content to the page here. All right. So just below search, what we're going to do is create a div. We've got this div called cards section, this cards title that says, welcome to ETHEREUM. We're going to replace that with the text, you know, why you need a domain name, period. And then we're going to create a new paragraph just below that, like this. All right, paragraph. And we'll say class name equals cards underscore description. And then we're going to put in that text for that's on this mock-up here, you know, or yeah, this stuff, okay? You can grab this copy if you want to from the final solution, or you can just copy it off the screen here by hand. I'll go ahead and pause the video so that you can see that. Okay. And if you save that and go to your app, you should see that available. All right. And the last thing we want to do, last couple things, is we want to put in a horizontal rule here. And then you can see that, just like our mop-up. And then now we've got a spot, we just put a place to render those domains. And let's just create a div here, called div. And then we'll just say class name equals cards. And we'll leave that blank for now. We'll actually put all the domains inside of there. All right, and we'll do that. Okay, so that should be all our scaffolding. We can still connect, we can see this. And in the next section, we're going to list the domains on the page, and then we will let you buy them. All right, so there's one more thing I want to do here. You know, we're going to list the domain names on the page in the next step, but there's one little thing that I forgot that's pretty cool that you're going to want before we do this next step, okay? So you can see that we, you know, have loaded the account here inside MetaMask. What happens if you change your MetaMask account, right? What if you're here and you go to HARDHAT 0, right? HARDHAT 1, and I go to HARDHAT 0. All right. What I want to happen is for your account, like if nothing changes, but if I refresh the page, I can go through and now I can see the new account. What I'm going to do is create a special way for whenever you change the account in HARDHAT, or sorry, inside of MetaMask, I think I said HARDHAT a minute ago, it will automatically change the account. So what you can do inside this load blockchain data function is do this. You know, we did Ethereum, you know, requests, but you can also listen for change events. So you can say, window.ethereum on accounts changed, do something inside of this function. All right. So what we're going to do is basically take all this code here, and then just add it like this. Okay. We're going to go through that entire procedure again, and then just reset the account right here. So do that, go back to our page. Okay, we got a little problem here. Let's, we need to have a closing parenthesis. All right. So now if I connect, and then I go to my MetaMask, you can see 226 is the last 4 of this one. If we go to HARDHAT 1, we can see that it automatically changes to 79C8, which is this one. All right. So now you've got a special utility to automatically detect the new MetaMask account if you change accounts. That's a cool thing I want to show you. All right, so now let's get on to listing the domains on the page. So I forgot that in the last section. Let's just go ahead and do that now. Okay, so we need to wire up these smart contracts to our app. Okay, so we're going to do this primarily with the Ethers.js library and also this stuff that we've already imported. So before, remember I showed you that you need to save your ABIs into your file here. Make sure you've done that, and then make sure you've got the correct address inside your config.json file here. This is the address of the smart contract. So we're going to use the Ethers library to do this. So just like MetaMask, lets us connect our project, our web browser to the blockchain, Ethers is going to let us connect our client-side application to the blockchain. So I'll pull up the Ethers documentation here. What we're going to do is look for a provider. And if you search for Web3 provider, you'll see this in the documentation. Basically, let's just see here. I think I clicked the wrong thing. Sorry. Web3 provider right here. You can see this Web3 provider basically is going to take the MetaMask connection and give you a provider that talks to the blockchain. So that's the first thing we want to do. You can see you choose new Ethers providers, Web3 provider, and then you pass in the MetaMask connection here. So that's going to be our link to the blockchain is our Ethers provider. So basically, we're going to create, we do like this. Basically, we say at the very top of our load blockchain data function, we do new Ethers providers, Web3 provider, just like the documentation says. Okay, new Ethers provider, Web3 provider. And then we pass in window.ethereum, that thing that we were playing around with earlier, which is what MetaMask mounts to our window. And then we just pass that into Ethers, and that's going to be our link to the blockchain that we can talk to it from. Basically, this is connecting Ethers to MetaMask, and MetaMask talks to the blockchain. So we'll save that to a state variable, not a state variable, sorry, I'm thinking about Solidity. We'll save that to the React state object. Just like we did account and set account, we're going to have one for provider. We'll say provider set provider, use state null. And then we'll basically just say const provider here. All right. And then we'll say set provider like this, set provider. Okay. Let's just refresh the page. Make sure we're still working okay. Everything works fine. We can still connect. And then now what we want to do is basically set up our smart contracts. The next thing we want to do is get the network that we're talking to. So we could say const network equals wait provider get network. All right, that's just a function on the provider provided by Ethers. And we can say console log network. Let's just see what network we're connected to. We want to make sure we're on HARDHAT. All right, so you can see the chain ID is this. So that's what we want. We want to make sure we're talking to the HARDHAT network. So we got it. And now let's get a copy of our smart contract in JavaScript with Ethers so that we can start listing those domain names out. So if you go to the Ethers documentation and you search for ethers.contract here, you can see ethers.contract. Okay. You can see how to do that. This is going to show you how you can basically create a new connection to that contract. You do new, actually, hold on, let's do a different one. So deploying, connecting to a contract. That's what we want. Basically, you can do new Ethers contract, And then you just this is going to let you have a JavaScript version of the smart contract. You need two pieces of information. You need the address and the ABI, and then a provider or signer if you're going to sign transactions on it, okay? So we'll do that like this. We'll do exactly what the documentation tells us. So we'll just literally copy this. New Ethers contract. All right, and then we'll say const ETHDaddy. And so we need two pieces of information. Where's the address? Where's the address come from? Well, we saved it here inside this config.json file. So we could just copy and paste this address, but that's not a great solution. We want to read it from this, and it's contextual based on the network. So if you deploy this smart contract to multiple networks, you could save the different network IDs inside of here and show you what the smart contract address is on that network. So if you put this on a test network, you could have the network ID of the test net here. You could use the main net if you wanted to and just keep adding to this file. But for now, what we're going to do is get the actual address. So we're going to do config. We're going to read from the config file, which is imported right here. We're going to read the network ID. So we're going to read the key, which is this key, all right, which we got here, network.id, all right. And then we're going to get our network chain ID. Okay, we're going to get the address, ETHDaddy, address. All right, so it's kind of a long line, not the best code in the world, but at least it's explicit and you can see what's happening. We get the ETHDaddy, network ID, ETHDaddy, address is this, that's going to return that. So that's the address. Then the ABI is the next thing we need. So that's the address. The ABI is here. Okay, ETHDaddy. And then we need the provider, which we saved right here. Okay, that's the final thing. Address, ABI, provider. And then now we're going to save this in our state like this. Say ETHDaddy, set ETHDaddy, use state null. And we'll assign it to the state just like this. We'll say set ETHDaddy. Okay. And now we can actually, now that we have a JavaScript version of the smart contract, we can do things like get the max supply. So say const max supply equals await ETHDaddy max supply. That's a function on the smart contract. We did that inside the test, just like we did earlier. Let's just look at it. We have this max supply. All right. And then let's just go ahead and console log that. Okay. All right. So now you can see the max supply is this. We can call toString. And we can see this 6. All right, there's 6 domains. Okay. So now let's get all the domains. First of all, we need a place to store the domains. So we're going to say domains, set domains is use state. And instead of null, we're going to pass in an empty array. So we're going to create an array of all the domains that are in the smart contract. So what we're going to do is just go through the smart contract and fetch out the domains one by one. So we're going to just say, we know there's 6. So because we just pulled out the number 6 here. And we can basically loop through numbers 1 through 6 and call this get domain function, and then just save them inside this domains array. So we're going to do that in a for loop in JavaScript just like this, and then we'll set it. So basically, so for var I equals 1, I is less than or equal to the max supply, which we got here. So basically numbers 1 through 6. We're going to say domain is equal to await ETHDaddy get domain I. And then we're going to call the push function on the array and push that domain in. And then finally, once we've populated this entire domains array, which we also need to declare before we do that, let's put it up here, sorry. All right, once that's populated, we're going to push that into this right here. All right. So now let's refresh the page. And then, boom, that's working. So we could also console log the domains. Just so you can see it. And then, yeah, you can see it's an array. Then here's all the domains inside of it. All right, it's got the name, It's got the cost, all that type of stuff. All right. So now we have connected the blockchain. We've connected to our smart contract. We've fetched out all of the domains. And now let's list them on the page. So down here, inside the cards, we can loop through those and list them on the page. So basically, you can see that we've saved this into this domains variable up here. So we can read that variable down here, and then we can loop through them. So inside of JavaScript, we can do this, domains.map. It's just a function that lets us loop over it, and we can look at the domain. And then do this. And for now, let's just do a paragraph tag. Say domain.name. All right, let's just show that on the page. So it may not be working for specific. Oh, I know why. First of all, you got to use parentheses here because it's going to have explicit or implicit return, which you'd have to call return if you're going to do that. Yeah, so there you go. And then now domain.name. It's showing that, but that's because I'm not actually calling it in JavaScript. Let's change that. So let's put some curly braces around this. All right. And then boom, there you go. Jack.eth, John, Henry, Cobalt, Oxygen, Carbon. I'll pull this up in case you can't see it on the screen there. Okay. So now we need to change a couple things. One, if you look at your server here, it's probably going to be yelling at you. Well, the server won't, but if you look at your console here, it's going to say, warning, each child in a list should have a unique key property. So that's what's kind of annoying about React. It's not annoying, it's just, it's by design, but you need to change this. So the cool thing about map is you can have a optional second argument in this function, which is index, okay? So basically, we can just say key is equals to the index. And that's going to basically let React differentiate between these things when it renders them on the page. And it's going to make that error, that warning go away. And you can see, let me just refresh, it should go away. Yeah, it's gone. Okay, awesome. And now we can see all these listed on the page. So that is, that lists them on the page to see that we've actually got it set up properly. But what we want to do is use this thing where we can see them in this nice box here with a buy button and all that type of stuff. So we have this placeholder component inside of here called domain.js, okay, which basically is going to let us render a unique React component for each domain. And so that's what we're going to do. So we've already got that imported in the top here. You can see domain is imported here. So instead of this paragraph tag, what we're going to do is kill that. And then we're going to do domain. And we're going to pass in everything that it needs. So it needs a domain, it needs ETHEREUM contract, it needs a provider, and it needs the ID. So we can do that. We can say domain equals domain. Should do it like this. Domain equals this, okay. Domain is the exact domain name from this function. ETHEREUM is this, which we saved up here, okay. Provider is this, which we saved up here. ID is going to be the index from the iterator plus 1. And the key is just going to be the index. I'll pause that if you want to copy it down. All right, so now inside the domain, well, we can start filling this out. Basically, we have this div called class name card. We can give another div. All right, this will be class name. Oops. Card underscore info. And we'll give it H3. And for this, we'll just say domain name for now. Okay. And now that's looking a lot better. Okay. So I'll go ahead and put this back up on the page, make it full screen because we don't need to look at the bottom. But now you can see that looks a lot better. It's getting the CSS that we already have pre-written for us. So now let's do another paragraph below that. Okay. And inside of that, we're going to create a small tag. We'll say owned by. Okay, we'll break that up onto a new line. And then we're going to give this a break, line break. And then we'll say a span tag. And we'll say, actually, let's not do that just yet. Let's not do that yet because we haven't purchased the domains yet. Let's take this small tag, take it out. So what we're going to do here is basically just say strong. And then we're just going to say domain dot cost to string. That's a lot simpler for now. All right, now you can see this here. You can see domain cost is listed, but it's giving us the way value. Okay, so that's the number, that's the value that's actually stored in the smart contract. We want to convert this to Ether. Okay, so we can do that like this. We can use the utility from Ethers. And we could say Ethers utils format units, domain cost to string, and then say we want to convert it to Ether. Okay. And if you look at our website, it's formatted in Ether. Okay. Now we also, after that, let's just break this up onto a new line. And then we'll indent that. And we'll say ETH. All right, so it didn't look quite right yet. Let's do this. We're going to need this later anyway. You'll see why in a minute. Let's do this, and we'll pass it in like this. Let's look at our... All right, so this will look better once we get everything working properly. And then let's see what we want to do next. The last thing we want to do is a button to buy it. Oh, I see why. We need to take this paragraph, take it out, and then put it up here after the domain. It needs to be inside the card info. Now that looks a lot better. Awesome. Awesome. And I see also why. Yeah. Let's just make sure we format this properly. All right. That's looking a lot better. Looking like our mockup. Now we want to add this buy button right here. So let's do that. So after the card info, all right. So let's just take this, make sure it's before the second one. We're going to say button. And then we're going to say buy it. Get this button's properties. Type equals button. and then class name. It's going to equal card underscore button. And then we'll do on click yet. Let's just do that. And then boom, there we go. We have now listed all the domain names on the page. We can't buy them yet. We'll do that next, but now we have successfully displayed all the domain names onto the marketplace. All right, so now we've come to the final task, which is to buy the domain names from the marketplace. So what we're going to do is click this button and then talk to our smart contract and call that mint function that we created earlier. So that's our final destination, is to go to our smart contract and call this mint function and then pass in the amount of ether that we're going to do to buy the domain. Okay, so let's go ahead and do that. What we're going to do is create an on-click handler. Say on-click, and then some curly braces and pass in a function. Say buy handler. And so this buy handler is a function we're about to create that's going to actually purchase the domain. So at the top, we're going to use this function called const buy handler equals async. And inside of here, what we're going to do is buy the domain. So the console.log buying. So let's just make sure we wired that up properly. Go find a domain, click buy, and you can see this logged to the console. It is buying. It's not doing anything yet. We just want to make sure the buttons are actually accepting the handler. So we know the function is being called. All right. So what we're going to do is call the smart contract function. So we've got ETHEREUM. And just like we did in our tests, you see whenever we did mint, let's see here, we want to call this mint function. We basically want to do something very similar to this. So I'm going to copy this line, put it back in our app.js, or sorry, into our domain.js file. And we take this out. And we basically want to repurpose this to do that, okay? So in our test, we had an owner, but really what we want to do is get a signer here. Okay, so I'm just going to comment this out. So we want to get a signer. So in Ethers, we do that like this. Say const signer equals await provider, which came in here. Okay, get signer. This will get the signer that's connected with MetaMask, basically the address. And then we can pull this back in. Instead of connect owner one, we'll just take signer, replace that here. And we call this mint function. And the ID, instead of this uppercase ID, is going to be the lowercase ID, which is passed in here. And the value, instead of the amount variable, it's just going to be domain.cost, because that's already written to the domain from the blockchain. We can just pull it off there. Okay. So then whenever we want to wait for that transaction to finish, say const transaction wait. And that's really it. All right. There's some more stuff we got to do after that, but that will successfully purchase the domain. Or it should. Let's go test it out. So what I want to do is go check out my blockchain. First of all, we can see the server. Nothing's broken. We have some warnings. We can address those in a minute. But here, we can just look at our blockchain for all the activity. We've seen the calls like get domain. What we want to do is see the mint function successfully called. That's the first test to see if it actually worked. So we're going to refresh the page. Inside MetaMask, we're going to make sure that we're connected to the second account, which is the purchaser. So HARDHAT number 1. Okay. And make sure you've reset the account. And then we're just going to try to buy jack.eth. And what you'll do is you'll see this transaction pop up. You say it's going to cost you 10 ETH, a whopping $12,000. And you can click confirm. All right, and let's go check. You don't see anything on the page yet because we haven't coded that out. But let's look at our blockchain, and we can see that the mint function was successfully called. That's the account in MetaMask. That's the smart contract address. That's the value. So 10 Ether was sent in with the transaction. Here's the gas used, and here is the block that transaction was included into. So it worked. Now you can't see that it worked because we haven't wired it up on the page. So the last thing we want to do is show that it was successfully purchased and show the owner. So in our mock-up here, you can see that like Jack.eth is now scratched off the list, and you can see it's owned by this person. So let's let's wire that up. Okay. So what we're going to do, is basically create a function that determines whether the domain is owned or not. So we already have this inside of our smart contract. So you can see that the domain is owned. We populated that. So we can check for that inside of our domain.js. So inside this H3, so instead of just listing the domain name, we can basically say, we can add some conditional logic. We can use something called a ternary expression. So we can say domain is owned. All right, and we do a question mark here. And basically, if that's true, we'll do one thing. If it's false, we'll do another thing. So if it's true, we're going to break this up in multiple lines. Okay. If it's true, let me take this out. We want to show, we want to basically take this thing called deleted tag and put in the domain name. And if it is false, we just want to give it like this empty tag here. Say domain name. All right. So now, if we refresh the page, we can see that Jack ETH is scratched off the list and the other ones are not. So that's the first indication, is showing that. Okay. Now the thing we can check for is owned, or if it has an owner. Okay. So what we can do is set an owner. So at the top of our file here, above, let's do this. Let's create a hook, let's use state hook, and then say owner, set owner, and then we can basically do const. We can do a function for this, const get owner. So if domain.is owned or has sold, which we can set up here as well. Do has sold, set has sold. If domain is owned or has sold, we can get the owner domain, await ETHDADDY owner of ID, and do set owner. Okay, and then we can also, inside one of the component renders, we can do use effect. So down here, we can use effect and get owner. We're going to get the owner of the domain. And then we can check to see if as has sold changes, and we can fetch that again. Okay. So we're getting the owner, we're setting it. Now we can check for domain is owned or owner. All right. Now let's just open up our console, make sure things changed here. Still works just fine. I think we're still console logging the chain ID in the app.js. So let's take that out. Yeah. Let's take that out here. Okay, so we got that working. Now we want to do is, if the domain name is owned, okay, then we want to show this. We want to scratch out the price and hide the buy button. So let's scratch out the price and show the owner first. So basically, inside of here, we're gonna like kind of doctor up this section. Just gonna add some space here, and then say, domain is owned or owner, question mark. And if it is, we're gonna do one thing. If not, we're gonna do another thing. Okay, so we'll just do this And then inside of is owned, we're going to put this inside of it. We're basically just going to say, use this tag, say small, owned by, line break, span owner, and we're going to slice the address just like we did in the Navbar. And we're going to take all this code for the secondary case and then put it in here. Okay, so if you want, you can grab that from the final code solution, or you can just copy down what I have on the video. I'll give you a second. You can pause it if you'd like. All right. So now let's go back to the page, and we can see it's scratched off the list. It says owned by this. And then now what we want to do is hide the buy button. Okay. So at the very bottom, essentially, we can just replace what's in this buy button, and we can basically wrap it in a in this condition just like this, So domain is owned and owner. So we do bang, which is the opposite, and then we hide the buy button if they have already done that. All right, now it's hidden. But now what we want to do is, show that in real time. So if we click buy, do it again. All right, it's going to work. We can see it on the blockchain, but it doesn't automatically update the page. We have to refresh in order to see that, right? So what we want to do is update it in real time. So basically what we can do is after the buy handler, after that last line, we can do set has sold to true. All right, and because we're looking for changes on the has sold, like take this out, it wouldn't work. If we put it back in, if has sold changes, it's going to do use effect get owner, and it's going to go through all that again, and it should automatically refresh, or automatically update, I should say. So let's click buy, and let's watch it update in real time. All right, boom, there you go. All right, so you have successfully completed the project. You've created a domain name marketplace where you can list the domain names with prices. Someone else can buy them, and then you can receive the Ether for doing that. Now, one quick piece of homework I can give you here is actually getting the funds from the proceeds. Okay, so I'm not going to show you how to do it, but I'll give you some hints. There's a couple things you can do. One is that just like the, we have these scripts in HARDHAT where essentially, you can deploy smart contracts. You can write scripts to do anything that you want to. So you could create a new script inside of here that basically, talks to the smart contract and withdraws the Ether to your wallet. So that would be one strategy. Another strategy would be essentially recreating your smart contract so that whenever the mint function gets called, it automatically transfers the Ether to your wallet so that you don't have to do anything. Okay, that's another strategy for doing that. Of course, you have to update the tests. I would highly recommend testing your smart contracts to do that. I'll give you a hint. Basically, you do something like basically just copying this code and putting it inside of here. It's not exactly going to work. It probably will work, but instead of, storing the contract first, you could get it from the message value and then directly forward it to your wallet if you wanted to. Okay. And then you wouldn't need the withdrawal function anymore. Now you could keep the withdrawal function anyway, in case somebody sends Ether to the smart contract or somehow by some way. It shouldn't happen because there's no receive function on here, but you might want to keep it on there just in case Ether somehow gets sent to the contract. You can forcibly send Ether to contracts with like self-destruct and things like that. So you might want to keep that on there just to be safe. Anyways, that's something that you can do next. There's lots of other things you can do. You can deploy this to a test network. You can deploy your website live to the web. If you do that, be sure to tag me on Twitter. I'd love to see what you create. I'll pull up my Twitter here so that you can see that. So you can just find me on Twitter over at Twitter. Hold on, pull my profile up. Twitter.com/Dapp University. Go ahead and tag me. I'd love to see what you create. All right, so that's an introduction to blockchain development for 2023. So again, I really hope you liked this video. If you did, make sure you smash that like button down below for the YouTube algorithm. Subscribe to this channel. It's the only thing I ask in return for putting in the time to make this for you free of charge. And if you like what you saw in this video today, again, you want to take the next step, you want to increase your skills, become a professional blockchain developer, increase your salary past 100K. I can show you how to do that over at dappuniversity.com/bootcamp. Okay, again, you really don't have to be an expert to get started now. I've helped people with zero coding experience become real-world blockchain developers in a matter of months. So that's all I've got. Until next time, thanks for watching Dapp University.